Hello, hello. Hello. A very warm welcome to each and every one of you participating in this two-day workshop on organo and electrocatalysis for sustainable synthesis OECSS 2022, organized by the School of Basic Sciences, IIT Bhubaneswar, sponsored by DST SERB under SSR mandate for us students, researchers, and scientists. After the successful completion of day one of the workshop, we now move on to the day two of the workshop. I believe that we have gathered some great insights from the lectures delivered by our honorable guest speakers from all the three technical sessions of day one of the workshop. I am certain that you are looking forward to the fourth technical session of this workshop. Before we get started, I humbly request everyone to kindly turn your phone to silent mode. And if you wish to exit, please use the side doors rather than the front one for smooth functioning of the workshop. It is my immense pleasure to inform you that the session chair for this session will be our Honorable Professor Shantanu Pal, Associate Dean IIT Bhubaneswar, and fortunately for us, a professor at the Department of Chemistry, IIT Bhubaneswar. I humbly invite Professor Pal to take this session forward. Thank you, sir.
Hello. Good morning to one and all. So what I noticed is today morning that the you might have seen in the brochure that it should start at 9. But while I think you are coming from the hostel, you did not take the bus, but you came by walking, enjoying the campus scenery. So therefore, it might have taken little bit time, but your teachers were here in on time, you know. So time is a very important thing for everyone. Please give importance to all those schedules next time. So anyway, today is the second and final day of this workshop. And today our first speaker is Professor Shantanu Mukherjee from Indian Institute of Science, Bangalore. He is an eminent scientist. He does not need any introduction. But however, it is my duty to introduce. So he did his PhD, his MSc from IIT Kanpur in 2002 and then PhD from University of Cologne, Germany in 2006. After that, he worked with Professor Benjamin List at Max Planck Institute during 2006 to 2008. And then with Professor E.J. Corey at Harvard University during 2008 to 2010. Then he returned back to India and joined as an assistant professor at ISC Bangalore. And in the same institute, currently he is a professor in that institute. He has several awards and fellowships, just I will mention few, like INSA Award, NASI Award, ICT Young Scientist Award, A.V. Ramarao Abra Award, Young Scientist Award, SERB Star Award, CRSI Bronze Medal, and many more are there. And he was in the several scientific, he is serving in the several scientific community. He was the advisory board member of JOC Journal. Currently, he is associate editor of OBC Journal. His research interest is various aspects of asymmetric catalyst along with various applications. Today, he will speak on breaking symmetry, challenges, and opportunities. Please, Professor Mukherjee, please come.
Yeah. Am I audible? Oh. Is it better now? Yeah. Thank you, Professor Fall, for a very kind introduction. And And let me first begin by thanking Professor Tabrez Khan for a very kind invitation. This is my first visit to Bhubaneswar, IIT Bhubaneswar, actually, to be more precise. And I'm enjoying the fantastic campus and wonderful hospitality from the organizer. So my group is primarily working in the area of asymmetric catalysis during the past decade. And there are many areas of asymmetric catalysis that we touch upon. And we began actually in the area of organocatalysis back in 2010. Although my initial objective was to combine various modes of catalysis, but for that, first we had to be specialized in one and then specialized in another one, that is transition metal catalysis. And then we are trying to explore the exciting prospects that are there at the interface of these two catalyses, and sometimes within them as well. Now, we are primarily involved in reaction discovery, so which always works with a working hypothesis, right? And then to bring this working hypothesis to practice, so that's probably the longest journey in each of these efforts, and which involves a lot of screening of catalyst and reaction conditions and so on. And you need a lot of perseverance. So yesterday, Ramasastri gave a glimpse of what it requires to optimize, how long it takes, and so on. And more often than not, it takes sometimes longer. And once we have that, we actually go on to explore the scope and application of that. And this is a process which is also quite exciting. And you have a lot of unexpected findings, what you call serendipity. Again, something that you have experienced yesterday during Ramasastri's talk. We also take the help of spectroscopic tools and computational approaches to understand the mechanism of each of these reactions. And then finally, the knowledge that we generate in the process goes into the new working hypothesis for new reaction discovery. So this has been our approach, and I'm sure many groups across India and world, they're actually following the same approach. And today I will give you a glimpse of this journey over the last 10 years during the, let's say, the first 3/4 of the talk. So, and I will talk primarily about the desymmetrization reaction and remote stereo control. Now, symmetry is something that we are all extremely fascinated about. And this is probably one of the beautiful examples of how fascinating symmetry can be. But when it comes to the man-made world, you would also, we wonder like how difficult it would have been to create such a symmetrical object. However, when it comes to the molecular world, it is actually much easier to creating a symmetrical object rather than creating an asymmetry. Okay, that's actually the challenge. And that is something I'm going to talk about. So let me first explain very briefly what I mean by breaking symmetry. Okay, so think about a molecule of this type, which is a prochiral compound. So this center is not a stereo center, and you have two identical functional groups. However, these two functional groups are actually enantiotopic. So therefore, if you change one of the functional groups selectively, you convert the prochiral center to a chiral center. The same thing can also be done with the meso compound. In this process, you can actually generate even more number of stereo centers. So overall, this type of reactions are known as enantio group selective reactions, or in a simple word called desymmetrization reactions, right? And there are many advantages of this type of reactions. You can generate multiple stereo centers in one go, and sometimes you can actually generate them quite far from the reaction site, which is not so obvious, or not obviously can be done by many other methods very easily. Now the question is, like, if you are generating a stereo center very far from the reaction site, can you control the stereochemistry of that? And if you can do, then how far that can be so that you can still control the selectivity? And more importantly, we have to answer the question why we bother about breaking symmetry at all. Okay, and these are the questions I will try to address in the next half an hour or 40 minutes through the journey that I've already mentioned. So in 2010, when we started our group, we were interested in this type of gamma butynolides, particularly those containing a quaternary stereogenic center at the gamma position, because there are many natural products that contain that type of motif. That has always been our inspiration, whether we actually do that or not. Okay. Now there are many ways of making this type of molecules. You can start from a silyroxyfuran, you can start from conjugated butynolide, and so on. But we became interested in this type of deconjugated butynolide. The simple reason is that compared to the conjugated one, where you have to remove the gamma proton for analyzing it, you can remove the alpha proton here, which is more acidic. Therefore, you can easily analyze them, particularly with the help of this type of bifunctional catalysts. which contains a Bronsted acidic site and a Bronsted basic site, right? So Bronsted base will help in analyzing it, and the Bronsted acidic site will activate the electrophile. So therefore, there is a so-called intramolecular reaction can happen in the pre-transition state assembly. And this type of catalyst was pioneered by Takemoto's group back in 2003. And we actually used them for various reactions, like we use nitroolefin as the electrophile, we use maleimide as an electrophile, vinyl sulfone, and this is something else that basically combines phosphine catalysis and hydrogen bonding. So this does not really fall under the bifunctional catalysis that I just mentioned. However, it still goes through this type of dienol intermediate. Now, while working in this area, we came across this report by Koichi Mikami's group back in 2012. So this is a reaction where they are adding dialkyl zinc in the presence of a copper catalyst, and they're getting extremely high enantiomer selectivity and high yield. And what I'm not showing here, they have done, they use some cases 0.1 mole% of catalyst, which is like a dream for any practicing synthetic organic chemist to use that much of that low catalyst loading. Now the question we ask, can we desymmetrize this prochiral cyclopentene 1,3 dione through a vinylogous Michael reaction? We did, in fact. My first student, Madhusudhan Manna, he developed a very nice catalyst and for this reaction, and there you can see the enantiomer selectivity is actually very high. We also found something very interesting here, that this site of the catalyst, which we generally do not consider to be participating in the reaction, because they have the two functional groups that I mentioned, Bronsted base and Bronsted acid. However, we found that this side chain actually can play a major role. If you replace the R from H to methyl, you can see the ER drops from 99:1 to 3:1. Anyway, that's a very interesting mechanistic scenario, but we'll not go into that. But overall, if you look at the selectivity of the reaction, is pretty exciting. But we are not quite happy because we found that we felt this is not really an ideal desymmetrization reaction, because we are not only creating a stereocenter here, but also here, and more importantly, the unsaturation in the substrate is gone. So what we want all of them to be intact, and we will just convert the prochiral center to the chiral center. So if you look at Mikami's report, that is somewhat closer compared to what we have, but it is still not ideal. So we are looking at something like this. So you can see that all the functional groups are intact. You are just converting the prochiral center to the chiral center. And there is also a very interesting story behind that. I will not be able to go through the entire thing in details today. What we came across is that nitroalkane can be a good alkylating agent for this so-called sp2ch alkylation reaction. And this is a serendipitous finding, which we actually took up, that knowledge that nitroalkane under certain conditions can be a alkylating agent. And we tried to find out a catalyst for this reaction. Now, as I mentioned previously, that these two sites actually enantiotopic. So what you need to do is an enantio position selective Michael addition. And we chose this catalyst here. We thought again nitroalkane can coordinate, and that will enhance the acidity of this proton, which can be removed by this Bronsted basic site, and then you have the nitronate, and then that can further undergo Michael addition to get this type of Michael adduct. And now HNO2 can eliminate, and then this can isomerize to give the endocyclic double bond to get the final product. One of the problem was, of course, that we are getting a nitrous acid, which is going to quench the catalyst. We had to find a base to quench the nitrous acid without doing the reaction. After doing several months of optimization, we found that sodium carbonate is a good base for that. We're very happy because you cannot find something cheaper than that. And we can get the product with high yield and high enantiomer selectivity using this dihydroquinone-derived urea. Now, one of the problems with this type of catalyst is that you cannot find the enantiomer, so you have to find something that will give you the other enantiomer of the product. So we have something called pseudoenantiomeric catalyst that is derived from synchronidine, or quinidine rather, and we can get the opposite enantiomer of the product with somewhat closer enantiomer selectivity. Now, the scope goes beyond nitromethane, and as you can see here, various other nitroalkane can be introduced, in fact, the functionalized one as well. And so this is what we have done. That's basically the summary of what we achieved. Now, when we do that, it's a very nice reaction. sp2ch alkylation reaction, desymmetrization, you create a stereocenter in a almost ideal manner and so on. Now, how can we take this forward to solve something that is much more exciting? So while looking for that, we actually came across this type of quinone Diels-Alder reaction. So this is a reaction that was done by Diels and Alder themselves. in the early days of discovery of Diels-Alder process. However, if you look into the literature, you will find that when it comes to the monosubstituted parabenzoquinone, there are only very few catalysts known which can do this reaction and answer selectively, particularly with cyclopentadiene. And now, if this R is alkyl, it is unknown. So we thought, okay, this is a problem we can potentially look into. And we do not want to do the Diels-Alder because there are many efforts there has been there. What we can do is we can take this mesonorborninoquinone and we can break the symmetry of it to get this alkylated norborninoquinone, which is difficult to achieve by Diels-Alder reaction. So my student Rahul, he had done that, and you can see he can get very high enantiomer selectivity. Not only that, so this was the initial mechanism that we conceived, right? That there is the enantiomer position selective conjugate addition, followed by elimination, and then isomerization, 3 steps, right? And we thought the enantiomer position selective conjugate addition should be the determining step of the reaction. So in one of the substrates, Rahul could actually isolate the desired product and the intermediate. They can separate them. We can completely characterize this. This is forming as a single diastereomer with very high enantiomer selectivity. Now we can take this compound, isolated one, and treat with an acrylate base, potassium acetate and 18 crown 6, and that converts this compound to the final product with the same level of selectivity. So that very clearly shows that that is indeed the intermediate in this process, and enantiomer position selective conjugate addition is the enantiomer determining step, at least for norborninoquinones. Now, when it comes to cyclopentene dione, we could never isolate or detect this compound. So that raises the question, what is the mechanism of the reaction? Is the same mechanism as norborninoquinone followed in this case? More specifically, there are 2 questions. What is the rate and enantiomer selectivity determining step? And how is the catalyst controlling stereochemistry, which is 2-3 bonds away from the reaction site? Okay, so to understand that, we thought of combining some experimental tool with the computational method, more specifically, natural abundance 13C kinetic isotope effect. This is not something that you guys must be maybe familiar with. This is somewhat different from normal proton kinetic isotope effect that you come across. I think if you're interested, you can talk about it later. But of course, we did not have the expertise to do this completely on our own. So we tried to collaborate with Professor Jennifer Hirsch's group from Binghamton University. And this is a tool that was actually established by Daniel Singleton's lab back in 1990s. Okay, so what we did initially, we did an intermolecular 13C kinetic isotope effect. And here are the numbers you can see here. This is the carbon where we see a normal 13C kinetic isotope effect. So that shows that there are 2 possible enantiomer determining step or the rate determining step. One is the CC bond formation, that is the addition. Other one is the elimination of the nitro. 2 possible. Then we have done an intramolecular 13C kinetic isotope effect. At this site, we found there is an inverse 13C kinetic isotope effect. So the addition step cannot be the enantiomer determining step. So that basically leaves that elimination of the nitro group to be the enantiomer determining. So to find out more details, Jennifer actually screened the entire reaction pathway, and these are the possible transition states or the steps which could be the enantiomer determining step, right? Like 1, 2, 3, and 4. This looks like very high in energy. And we are looking at the elimination steps. So there are 3 possible ways the elimination can happen: E1, E2, and E1CV. And you can see the energy of the 3 pathways clearly so that E1CV is the most favored pathway for the elimination. Now, these are the other 3 steps which could be enantiomer determining, right? To check that, they did the calculation, or they calculated the 13C kinetic isotope effect for each of these steps, and they compared with the experimental one, what you see here. Now you can see only for U1CB, all the kinetic isotope effects are matching. So that shows that this elimination of the nitrous acid is indeed the rate and enantiomer determining step of this reaction. Now coming to the second question, what is the origin of enantiomer selectivity? These are the 2 competing diastereomeric transition states. This is giving the major product, that is R, and that is giving the minor product, S. You can see there is the energy difference of about 2.1 kcal per mole, so which is pretty close to the experimental one, that is 1.8. Now, to find out what is happening, initially what we realized that there is a CHF interaction that is there, which is pretty weak in nature, actually. And this could be one of the reasons, or one of the factors that which is controlling the remote stereo control. To find out the role of this CF3 group, we actually prepare another catalyst where these 2 groups are methyl. And you can see this catalyst B, which is the dimethyl catalyst, you get low enantiomer selectivity, somewhat low, not too low, but somewhat low. So this does have some contributing factor, but this is not the only one. To understand more, we try to see the conformation of the catalyst and the substrate. Now, when it comes to the catalyst, they are almost identical in both these transition states. So it is not the catalyst conformation that is contributing to this energy difference. So if we check the substrate now, you can see that this is the benzyl group, this is the methyl on the substrate, and this phenyl and the methyl, if you see here the bond, the dihedral angle is about close to 180, so it's like anti-periplanar. On the other hand, in S transition state, that is about 55, that is gauche. So clearly, anti-periplanar is the one that will be more favored, and that is the one that is actually contributing, along with, of course, the CHF interaction. Together, they are controlling the enantiomer selectivity in this reaction. Now, what is the knowledge we gain from both these reactions? That nitro can be a very good leaving group, right? Now, can we use this for developing new reaction? Because that was something that we were always trying to do. And this is what we have done, actually. We have done a so-called Umpolung alkynylation reaction. Now, this is the product we are getting. So let's focus on the product at the beginning. We are getting very high enantiomer selectivity. Now, if you do electrosynthetic analysis, you generally cut this bond here. You get a beta-keto ester and an enone. Now, both the alpha position of the enone and the alpha position of the beta-keto ester, they're both nucleophilic. So you have a mismatched polarity. You're not going to combine them. They're not going to work. So, but if you put a nitro group at the beta position of the enone, you are converting nucleophilic alpha position to the electrophilic beta. So now, because of the presence of the nitro group, there is a polarity inversion that is taking place, and that's what is favoring this reaction, because now you have matched polarity, and after the reaction, you have to use the base to eliminate the nitrous acid like we have done before, and then that gives the product. So we have more or less completed this cycle, right? And now, except that, we have not shown any application for this reaction so far. So while looking for application, we became interested in this type of compounds called ladder-end phospholipids. It's a very unusual type of molecules produced by this anaerobic ammonium oxidation bacteria. Now, this bacteria actually contributes to about 30 to 50% of the nitrogen that are produced in ocean. Okay, and it converts. So this is the reaction. What is happening here? It is basically converting ammonium nitrite to nitrogen through a series of reactions, and this reaction takes place in a large compartment in the bacteria called anamoxosome, and the other thing is riboplasm and periplasm. So this is why the reaction is happening. So the overall, the reaction is actually exergonic process. So initially, it was believed that the hydrazine and hydroxylamine are some of the intermediates of this reaction, and both of them are actually toxic. So potentially, they can actually damage the cell. So what was thought that this barrier, or the membrane of this anamoxosome, the green one, is actually preventing the transport or the leaching of hydrazine and hydroxylamine to the other part of the cell, and therefore preventing it from damaging it. So Noah Burns and Stephen Boxer's group in 2018, they have done a detailed investigation, and they have found that this type of lipids, which are consisting of this type of ladder-end phospholipids, they are no different than the normal lipid membrane. So therefore, the transport or the leaching of hydrazine and hydroxylamine happens at an equal rate through this membrane and a normal membrane. Okay. It is the proton and the hydroxide that transport is significantly different between these two types of membranes. So it does not prevent hydrazine, but prevents the proton transfer to take place. And if you notice here, you can see that inside the anamoxosome, the pH is about 6.3. Outside it is 7.3. So there's a 1 pK unit pH difference between the inside and outside. So essentially, it is creating something called a proton motive force between the barriers, or between the membrane, or across the membrane, and that proton motive force is driving the ATP synthesis. Okay, and that is the important part, which is running which is basically the energy currency, so-called, of the bacteria. Now, if you look at this is basically a bilayer, and that consists of this type of ladder-end phospholipids. There are two different types. So this is called 5,3-PC. It consists of this 5-ladderanic acid, and the other part is called 3-ladderanol. There is also a 3,3-PC. This is also an isolyl product that is isolated from this nature. Now, of course, this type of compounds would be interest for synthesizing them, but the first you have to answer, why do you want to make them if it is already produced in nature? Only problem is that they are produced in minute quantities by this bacteria because the growth is very, very slow. You can see it divides only about once in 2 to 3 weeks. And more importantly, the phospholipid or the lipid soup that you get, it contains many other type of lipids. So it's extremely difficult to purify that. So therefore, that purification and isolation and purification from the nature is not a viable way of accessing them so that you can do all these studies. So that basically leaves total synthesis as the only option to get this molecule. And not to mention that in 2002, when it was isolated, absolute configuration of this natural product was unknown. Okay, so this is basically the impetus for doing the total synthesis. Now, before I go to the natural ladderin phospholipids, let me tell you a bit of ladderin, how they were made historically. If you think about a ladderin of this type, of course, the compound is named because they looks like ladder, more like a stair, should be called stearin. But the simple way is that you just break it completely and you get these two olefin strands, right? You can do a photochemical 2+2 cycloaddition reaction. But to do that, you have some prerequisite which cannot be met easily, that these two strands has to come parallelly, close enough proximity that 2+2 cycloaddition can take place. Now, both these requirements are entropically highly unfavorable, unless you have a extra structure or a solid state where they are actually parallelly stacked. And there are some molecules that has been prepared where these conjugated olefins are so closely parallelly stacked in the extra structure or in the crystal, you can actually irradiate the crystal with a UV light and they undergo 2+2 cycloaddition. But that's a very special case. Only Henning-Hoff group in 1995, they prepared this molecule, and this is that they put this 2,2 paracyclophane spacer, and that basically brings these two olefins strand very close to each other. And now if they can irradiate with UV light, they can get this compound with very high yield. And this is done in solution, not in solid state. However, this is a very, very special case for the ladderin synthesis. Now, how you can make this type of concatenated cyclobutane rings? Over the past 50 years, there has been a few methods for systematically preparing them. It basically began in 1970s. And what initially they thought that cyclobutadiene, which is of course anti-aromatic, if it is produced in solution by some means, it will be so reactive, it can participate 4+2 cycloaddition with alkyne twice to get this type of compound. And if you just treat this with CAN, an oxidant, it will remove the iron and generate cyclobutadiene that will immediately participate in the reaction. And Meinwald's group showed that they actually prepared this compound. It's a very interesting name. You can see this called pterodactyl dienes because this resemblance, this flying dinosaur, it's called pterodactyl. So that's how the compounds were named. Okay. Now, Professor Mehta's group realized that if you do not have the alkyne and you still produce cyclobutadiene, it has to do something. It will dimerize or oligomerize, and they could show that it's actually oligomer. They can get a mixture of these three products, dimer, trimer, and tetramer. And of course, it's not always trans. Initially, it was cis and then trans and so on. But he has the extra structure of all three of them. But a more systematic approach came little later by Martin, or before Mehta, actually little later after Meinwald in 1981. So they found out that you can do this 2+2 cycloaddition between malic anhydride and an alkyne acetylene to get this type of double of the so-called 2-ladderin. Okay, and now in several steps you can convert this to alpha chlorosulfones and treat with potassium tertiary butoxide, something known as Rambach backbone reaction, and that gives this pterodactyl diene. So this can be a systematic method. But these are all unnatural ladderins, and they were basically steps for making ladderin scaffold themselves. Now, when it comes to this compound, there has been a lot of interest, and it was isolated in 2002. So Kore's group first reported the racemic synthesis of this compound. And there was no absolute configuration was reported. 2 years later, they made an enhancer selective synthesis of +5 ladderinic acid. Okay, but the natural one is minus. I will come to that in a minute. It took another decade for the next synthesis to come up, and that was done by Noah Burns' group from Stanford in 2016. Finally, in 2020, Kevin Brown group, they prepared the +ladderinic acid. When it comes to 3-ladderenol, Burns was the first one to prepare that, and then followed by Brown. In 2016, Burns actually combined this +3-ladderenol and -5-ladderinic acid to form this 5,3-PC, and he established the absolute configuration of this molecule through the synthesis. Okay, so now it was established. So I will not go in. So there has been few other syntheses, and Burns generally prepared them through this Rambach backbone route, coded it through the Wolff rearrangement of alpha diazoketones. And I mean, there are rich history. I will not have time to go through that one. So what we thought, we can actually clip this bond or cut it here, and we have this meso compound, whether it is a 5-ladder end or 3-ladder end here. And we can actually combine that through the symmetry breaking operation to get this molecule, right? So let's focus on the 3-ladder enol for the time being. And what we are trying to do here is an sp3-sp3 coupling between the two CH bonds, so-called cross-dehydrogenated sp3-sp3 coupling. There's nothing known. That type of methodology doesn't exist as of now. So we try to simplify our target a bit more. I mean, target means the strategy. So instead of having the alkane, we thought of alkene and then further put to functional groups. We can always unfunctionalize them afterwards. And now once we have this, we can actually cut this. And now we have these two fragments, more specifically, this type of fragment. So we can do an enantioselective CSPA2H alkylation reaction. Now, this is something that you are probably connecting to the something that I talked about. And that's when actually Sion, who was an MSc student of IIT Bhubaneswar, worked with Professor Tabraj Khan, and he joined my lab. And I told him, I want you to make this compound. Okay, and he immediately got excited. He said, yes, I will do this. And what I'm going to show in this slide is probably a very brutal way of showing his 3 years of work in one slide. Okay, so initially he had to prepare this meso compound. It took him probably 2 years to get that because we did not have any photochemical setup. We did not know how to do this, what to begin with, and so on. So initially he actually prepared cyclopropane fused cyclohexene dione, and he resymmetrized that. That also led to some of the natural product synthesis. And so that was basically a byproduct of this project, as you may say. But eventually, he actually made this, and then we got to this meso compound. Now he could actually do this CSP2H allylic alkylation, CSP2H alkylation reaction by combining a chiral tertiary amino squaramide and an achiral tertiary amino urea, because this helps the elimination process significantly, and we can get this product. Now we can form the hydrazone and chop them to get this diene. Treating with Crabtree's catalyst under, hydrogenous under Crabtree's catalyst gave this product, and just removing this protecting group gives us plus 3-ladder enol. And Sion actually prepared the corresponding 4-bromo carbamate or 4-bromo phenyl carbamate, and he actually got the extra structure of this compound. So once again, we confirmed the absolute stereochemistry through this extra structure. Now, some of the features of our method, I did not show Burns and Brown's method for synthesis. They actually introduced the chirality pretty early stage of their synthesis, and they take it forward to the next step. So if you want to make the other enantiomer, you have to go through multiple steps. So we actually introduced the stereocenter pretty late, and we have only 4 steps after that to go to the final compound. So we can actually make both the enantiomers, and also we can prepare some of the analogs of this, which we are currently working on. There are many questions that one can ask, that why nature specifically made this 6444, why not 4644 or 4464 and so on. So we can actually address that through synthesis, and that is exactly what we are currently Sion is trying to do. Okay, now, so I told you our journey through this so-called our catalytic cycle, and how we can actually, the knowledge that we have generated in a one process, along with the serendipitous finding, we can actually take them for designing new reaction, and how we can apply them for chasing some of the complex targets that are available. Now, let me change the stage, and in the final 10, 15 minutes or 10, 12 minutes, I will talk about chiral arenes. Okay? Now, when you talk about chiral arenes, the most common arenes comes to your mind. Chiral arenes are axially chiral arenes or planar chiral arenes. There are some helical chiral arenes and calyx arenes and so on. And there's some of the natural products that also contains this type of chiral arenes. What about centrally chiral arenes? So what I meant by centrally chiral arenes is that there are 2 different possible centrally chiral arenes. One is that you have a chiral arene where basically you have a stereocenter which is very close to the arene motif. Now, this type of compounds, the stereogenicity is independent of whether you have any substituent on the arene ring or where it is present. They're not important. Therefore, they are very, very easy to synthesize. There are hundreds and thousands of methods available for their synthesis. Compared to that, if you think of this type of a molecule, they are chiral only if R1 and R2 are not hydrogen and if they are different. Because the moment they are identical, they're actually meso compound, right? So that means the stereogenicity is now dependent on what is present on the arene ring and where is it present. Because if you exchange R1 and R2, you get this compound, which is actually enantiomeric to the other compound. So that actually makes it very difficult for their synthesis. Okay, and therefore they are rarely studied. So you can actually make them through desymmetrization reaction, and there can be two different strategies. One is you start with the meso compound and you site selectively, and of course enantio selectively by correlation. You can put a group on the arene ring through this, because these positions, these two meta and these two ortho, they're actually enantiotopic, and you can do that. But this is really challenging, and that can be done possibly. This is something we would like to look into that in the future. But right now, we thought of constructing the arene ring actually by desymmetrizing a meso compound of this type. So what we basically are looking at enantioselective de novo arene construction. Okay. And this type of strategy can be very modular because you can actually have various groups at different position of the arene ring by choosing the starting materials carefully. And possibly with the easier enantio control, but that is something that we are not sure about. And again, they was rarely studied. So this was our strategy. We started with the cyclohexene 1,3 dione, of course polycyclic, which can be either prochiral or meso, mostly meso. And we have an alpha-beta unsaturated aldehyde. So we wanted to use the dienamine catalysis for this type of enantioselective de novo arene construction. This is the catalytic hypothesis. You start from a secondary amine catalyst which can react with alpha-beta unsaturated aldehydes to form dienamine. Now these dienamines are very electron rich. They can easily participate in a Diels-Alder reaction with this type of electron deficient mesocyclohexene diones, okay, and give this Diels-Alder product. This can then eliminate the catalyst and form this diene that should spontaneously oxidize in the air, for example, to get the final product. And overall, what we will achieve is the desymmetrization of this type of polycyclic mesocyclohexene dione. Now, this is the optimized condition. I will not take you to the optimization. This was not too difficult one. We could achieve it pretty quickly. And overall, in an open air reaction condition, using 20 mole% of this catalyst containing the triphenyl silyl ether and paranitrobenzoic acid as the co-catalyst, we can get the product with 84% yield and 93% EE. And the feature is that it's a very simple reaction operationally. You can do it in an open flush condition, no precautions required, and it does not use any external oxidant. It takes oxygen from the air to do this reaction. The scope is fairly broad. I'm not going to the details. So these are some of the groups you can see here. You can put like arenes, heteroarenes, alkenes, even alkyls, and the E's are quite high. And again, we started with cyclopropane here, and we can put different substituents at this position here. And the moment the bulk goes up, energy selectivity also goes up in this case. As I mentioned, that by choosing the aldehyde properly, you can introduce substituents in different position of the arene ring. This is an example where we started with this type of what you call cyclohexylidine acetaldehyde. Unfortunately, the oxidation step in this case does not happen spontaneously, or it's very slow. We have to use DDQ. That's why it is a two-step process. In this case also, but some of the other cases like here, it worked spontaneously in air, and you can get the product with 90% EE. Using cyclic aldehyde, you can put the methyl group at this position here. And earlier with the crotonaldehyde, we could achieve this one. So now you can look at these two. These two are basically enantiomers. So you can use the same catalyst just by choosing different aldehydes. You get two different enantiomeric products. You don't need to prepare another enantiomeric catalyst, although it is not very difficult in case of proline or diphenyl prolinol. Now we can actually access both. So now using citral, we can get two possible products. We got one, and this is something weird. You can see this is not a mistake in drawing. This prenyl ring is absent actually here. So what is going on here? You can form these two different dienamine because you have two analyzable gamma protons. Right? Each of them can participate in a dienamine formation. You can get these 2 different dienamine. And now they can participate in a Diels-Alder followed by oxidation. And this is what you get. This one is not happening. So what is happening in this case is that initially, when you are forming the Diels-Alder adduct, instead of this proton participating in the elimination, possibly there is a deprenality elimination that is happening, and that is further undergoing oxidation. And so this is kind of a limitation. We are trying to find a way to bypass this so that you can actually achieve the other product. We can take it to the domain of non-Bournian quinones, and this is the optimal optimization. Basically, there was only 2-3 reactions we had to do. Same catalyst, very similar reaction condition, the reaction works. These are more reactive compared to the cyclopropane fused cyclohexene diones, and the reaction happens very quickly at room temperature. At low temperature, you can increase the selectivity very easily. These are some of the examples, and we have X-ray structure also that helped us with the absolute configuration. Now, with these compounds, you can convert them to some unusually complex chiral compounds. For example, we can actually oxidize these. This is not that exciting, but what we can do is we can analyze and put triplet on these 2 enols, so you can get this compound. And now, if you can do the hydrogenation with ammonium formate as the hydrogen source, by choosing the reaction time, either 16 hours or 48 hours, you can retain this double bond or you can reduce this one. So we call them chiral anthracene, and you can think of any other ways of making them. It will not be as simple as what I have shown here. Now, coming to the mechanism of the reaction. So this is basically textbook. You can recollect your BSc or MSc pericyclic reaction classes that when you have a Diels-Alder reaction, there are 2 possible approaches, like exo and endo. And you know the endo is favored because of the secondary orbital interaction, right, energetically. Now, in this case, since we are talking about prochiral compound or the meso compound, and we're generating stereocenters, there are 4 possible transition states. So these are the 2 endo, and these are the 2, these are the 2 exo, these are the 2 endo. And you can see, you can imagine that the endo one will be energetically favored. Now, this one will also be sterically favored because the CH2 or any other group will be very far away from the catalyst. In this case, this is actually bumping onto the catalyst, so therefore this will be sterically disfavored. So in this case, also the same thing. This will be both sterically and energetically disfavored. This is sterically okay, but energetically disfavored. So this was our drawing, basically, right? And to check further, my colleague's Garima student, Mahesh, actually helped us with the calculation. So he actually calculated the energy of relative energies of each of these transition states. And he found that this TS1, endo TS1, is indeed the lowest energy in this case. And these 2 are very high in energy. This is the competing one, which has a difference of about 2.4 kcal per mole. That is predicting to be 98:2 ER, and we are getting 97:3, which is very close in agreement. Okay, so now what about axial chirality? Can we take this concept to develop axial chirality? We chose N-aryl malimides. I think this Biju discussed a very interesting discovery from their lab using N-aryl malimides. Now, N-aryl malimides, there is a restricted rotation of this bond if you have a bulky ortho substitution here. And that basically breaks one of the symmetry elements present in malimides, and we left with only 1 sigma plane. Now, typically they are done, the desymmetrization is done through a conjugate addition of a nucleophile or a cycloaddition reaction, 3+2 or 4+2. Each of these cases, the double bond is gone and you are creating additional stereocenter. So this is so-called not ideal from our perspective. So we are looking to create only a stereogenic axis, not the center. So this is what we are trying to do. Biju's reaction was kind of unique because they do not create any stereocenter. Only chiral axis is created, but in that case also the unsaturation is gone. So we are trying to retain that. So this is of course unknown. And again, there are 2 ways you can do that by desymmetrizing oxidative 4+2 cycloaddition, what I just talked about. And these are the 2 regioisomeric or regio, you can say regioisomeric Diels-Alder reaction. And they're actually enantiomer, so therefore you have to control the regioselectivity of the Diels-Alder process to achieve high enantiomer selectivity. And this is the endo transition state we figured out through our working hypothesis and using a very similar type of catalyst. And there was one report, by the way, by Young-Rock Lee when we were doing the previous work, and that led to the formation of these achiral thaliamides. So we are, of course, trying to make the chiral one. And this is the scope of the reaction. This time the catalyst is somewhat different. And you can see there's two steps. We get decent selectivity, but the reaction times are awful. Actually, it's 5 days and 6 days and another 2 days. So it's not not something that we are very proud of yet. And more importantly, you have to have this nitro group. If you do not have, you can see the yield and terrible. So I probably should not even show that. And so the requirement of the nitro group is a key limitation of this method. But you can remove it. For example, you can reduce the nitro with tin dichloride to get the amine. I mean, these are some of the other functionalization. We can acetyl protection, we can do an iodination by diiodization and so on. And finally, we can actually remove this and we can get this product that we could not access directly. Now, one of the things you have noticed in this case, we are starting from 95% EE, and all the cases the EE has gone down. So there is an erosion of enhancer selectivity. So what is happening now? Is there a barrier that is easily achievable? So we checked that at different temperatures. Up to 60 degrees, there was no erosion essentially, and then it goes down. And 120 degrees, it is happening very fast. So we did this reaction over different time at different temperature, and at 90 and 100 to be more specific. And using this Dennis-Courant's method, we found the rotational barrier to be about 30 kcal per mole. So that effectively translates to about 18.4 years of half-life of racemization, if you consider room temperature. But if you think about 70 degrees, it's about 7.5 days. So that means racemization can happen, or the CN barrier can be, or CN axis can be rotated at room temperature. So this is the reaction we are doing at 70 degrees. So it's possibly the reason for erosion of enhancer purity. Of course, when you go to this type of compounds, which is not the same as this one, so you calculated using this. The rotational barrier ought to change, so therefore that can also be the reason for erosion of enhancer purity. So overall, so again, like we began, so again, this is something that so far all the reactions I talked about, they're basically in dione type of motif, right? Cyclopentene dione to be one example. So they're now pretty well explored. There are many other ways of desymmetrizing them. Compared to that, if it is saturated one, cyclopentane 1,3 dione, these are much less explored. Although one of the oldest desymmetrization that was reported, at least organocatalytic one, was this hydrospheretic reaction that used this cyclopentane 1,3 dione. We have done that through a Fischer internalization reactions. I will not go into that details, but this is a summary of the work so that we can actually do this. So these two carbonyls are actually an enantiomer topic. So therefore, you have to do an enantiomer group selective desymmetrization reaction. And this is actually takes place through a DKR process, dynamic kinetic resolution process, and gives very high enhancer selectivity. Now, at the beginning, we asked this question, like, why even bother about desymmetrization reaction? Now, let me show you some glimpse of some of the things, whether it is a synthesis of ladderine and some of the molecules that we have made, what I've showed you today. Now, try to think about making this molecule not by desymmetrization, but by other means. You will find them to be extremely challenging. So I hope I was able to give you the answer of the question that we asked, that why we need to do the desymmetrization reaction, and what are the challenges, what are the opportunities, and so on. Finally, all the works that I have showed today are done by Sion, Subhajit, and Vicky. This is Sion here. He is in the final year, so I'm expecting him to submit his thesis sometime next year. I also should thank my former PhD student, Madhusudan Mannai and Rahul Sarkar. They are the one who actually not only began the work, but also laid the foundation of whatever my current group has done now and are currently doing now. I should also thank my collaborator, Jennifer, for this wonderful collaboration he had for the mechanistic investigation of the CSP2H alkylation reaction. And also, Garima Sidide, she helped us understanding the mechanism of the Fischer internalization, and also her student, Mahesh, helped us understanding the mechanism of this oxidative 4+2 cycloaddition reaction that I mentioned. Finally, I must thank the funding agencies who has been very generous over the years, particularly SERB. We have our major funding source during the decade. And more recently, I got some money from Syngene through their CSR project, and that is helping us going. And finally, thank you all for your attention, and I'll be very happy to answer any question that you may have.
Hello. Hello.
So,
Hello. Hello. Thank you very much for the wonderful talk. Now, hopefully, we will be able to take two questions. Please, sir.
Yes, Ravi.
okay, Shantanu, excellent work and excellent talk as well.
Thank you.
And I'm just curious to know, how did you do that natural C13
Okay.
AIE?
So, okay, what it is, so let me tell you a little bit about C13's natural abundance, right? So, you take a compound which has natural abundance C13, right? Now, statistically, when you do the reaction, C12, more of C12 containing compound will participate at that particular center, right? So if you recover the starting material, that should be enriched in 13C. Okay. Now that's called normal 13C kinetic isotope effect. Now, if the reaction is reversible, there can be a possibility of getting that inverse one. So what is done typically in this case, for this intermolecular one, we took this benzyl nitromethane excess, and we did the reaction, make sure that it goes to completion as far as the cyclopentene dione goes. After the completion of the reaction, we recovered the unreacted benzyl nitromethane, and we compared from the same batch the 13C NMR or the 13C content in the starting material and the recovered one. From there, we can actually get the natural, normal 13C kinetic isotope effect.
But I have a question, because
Yeah.
13C is not quantitative, like NMR, proton.
Yes. Yes.
So how do you tackle
Yeah.
that?
So actually, so these NMRs were measured in Binghamton. So normally we use like 10 to 15 milligram sample for 13C. They have used like a really concentrated sample with a very long scan. So effectively, and that's what Daniel Singleton also showed, that if you do it at that concentration of that much, you can actually get almost like a error-free quantitization of 13C.
Did they also increase the pulse delay sufficiently longer?
Yes.
So
Yeah, that is one thing.
everything
Yes.
gets relaxed?
Of course.
Okay.
Yeah.
Okay, I just have another
Yeah.
quick question. That you said in one place the prenyl group is going out of the system. So you said that that's what you believe.
Right.
But you don't have any proof like that.
No.
So,
Well,
what
proof is only that in the product it is not there.
product
That's
is
the only
not-
proof.
Yeah, yeah. So one of the possible way could be you could do this GC of the headspace as well as the liquid for that molecule. Then
So-
you can detect that.
What is that? What I didn't get-
GC.
Oh, okay. Oh, to detect that. Yeah,
The
that is a
reaction
good
mixture.
idea. That is a good idea. We can-
Otherwise, you can add iodine and trap that olefin.
Right.
And check it in HRMS.
Yeah.
That is
We
also-
have not done much of investigation
Okay,
on
okay,
that. We were just putting more focus on how to solve
Yeah.
that. But yeah, we should do that.
Yeah.
Thank you so much. Yeah.
Thank you. Nice. Yeah.
Yes.
Wonderful all work and great presentation.
Thank you.
I have a question on your ladderane synthesis.
Right.
If you please go there, you actually converted that indione to diene
Yeah.
and then hydrogenated.
Right.
Why going through that strategy? I mean, you could have opted, of course, several methods to get rid of oxygens, and then you could actually end up having only one olefin.
Yeah.
Because you potentially would have risked making that a benzene ring. It may not form because of steric reasons. You have a diene, but you're lucky that you have sterics playing there, stopping from going to benzene ring.
Right.
But that is one thing.
Yeah.
Next is you use Crabtree to get rid of the diene system. Crabtree usually chelation controlled hydrogenation. In that, it's more of a hydrocarbon. I don't know how actually Crabtree worked in your favor.
So, okay, let me answer the first part. So we have, initially, our idea was not to go through this. Initially, we have this indione. We thought we can selectively reduce the double bond, stereoselectively, to get the required stereocenter. And then you have the diketone. We can reduce them to the diol, put methyl, and LH.
Right.
So we tried all sorts of ways of doing that. Nothing works. And when we had the double bond, like indione, we tried to reduce them. We got everything but the final compound. Okay. And so initially we had 646 system, which we are trying to desymmetrize and get to the final compound, which is basically an analog. So in that case, simple palladium charcoal, palladium on charcoal under hydrogenation, that works. But when it comes to this 6444, if we do the palladium charcoal hydrogenation, that one of the two of basically the 4 fuse ring that actually breaks, we get 646. So what we had originally, and so that's why we had to go with the Crabtree one.
Okay, but it would not cause any problem with the stereochemistry,
No,
neurogenesis,
no,
etc.
no.
Whether you use palladium or Crabtree.
Right.
Okay,
Yeah, that does not
great.
help. Yeah.
Thank you very much.
Right, yeah.
Yeah, one more question from student side.
I think he had.
Yeah, a very nice presentation. So I have a question about your latrines. I mean, so it's a natural product isolated from bacteria, this lipid.
Right.
So did they also isolated some intermediate, and have you looked about how the biosynthesis is taking place?
No. Okay. So no, no, we have not done. We have just completed the synthesis last year. There has been a few proposals for the biosynthesis, mostly by computational chemists, Dint and Tilo, to be more specific. I mean, two strands coming close to each other, 2 plus 2 plus 2 plus 2, that is not happening. Okay, that is too unfavorable. There are few other ways of doing that, but we have not gone into that. What we are, I mean, that is of course a very, very difficult to address challenge. So what we are more interested in doing that, you have this 5-ladernic acid, right? And then you have the other part is 3-laderinol. So 1,4,4 fuse ring is actually open to get a 6-member ring, right? Now, why that one is opening? Why not the other one, right? So that is something we are trying to figure out. I mean, we feel that if we can make those compounds and prepare the lipid, we might be able to check the permeability of that. Because like when nature does something, they make a lot of mistakes. Okay, so nature is not perfect. I mean, we tell that they're perfect in making the molecule nature. They don't, they make all sorts of molecules. And then finally from that, whichever works best, they picked it up, the rest are eliminated and they followed that one. So it is possible that all those compounds were prepared and then none of them could prevent the proton permeation through the, or the proton transport through the barrier. And only in this case, it gave the best one. So we need to do that. Okay. Coming with the entire biosynthesis is probably more challenging. It's probably a long shot. Okay. I'm not sure whether how we can do that. So we have to figure it out. Okay. Right. Thank you so much. Yeah.
Okay, just I have something.
Yeah, sure. Yeah, there. So unless you have the OA, the alcohol or the acid functionality there, they are very nonpolar, of course. They're more so that, yeah, I mean, we do try to do all sorts of purification before the final hydrogenation step. Once we do the hydrogenation, then it becomes difficult. So, and hydrogenation generally is very clean, quantitative almost, and the protecting group cleavage, so that we had to make sure that the compound is clean before it goes to the hydrogenation.
Okay, let's put hands together to thank Professor.
Sir,
okay.
I have a question, sir.
Somebody?
Yeah.
Okay.
Yes. Please.
Yeah. Sir, can you go to the slide number 42? Somewhere you mentioned bacterium.
Can you go to 42? Yeah. Yes.
Yes, sir. Sir, actually, I am not a chemist, but I am a more biological person. So my curiosity about the bacterium you used.
Huh?
I am curious about the bacterium you used. Why you choose that particular bacterium? That particular bacterium. Is it
a particular bacteria?
Yeah.
I didn't do that. I mean, they have isolated it. We are just trying to make the compound. I mean, I have no experience with the bacteria on how to work with them. So there is this Dutch group. Oops. There is this Dutch group. They actually isolated this compound, and I mean, probably they have been trying other things as well, and they found this unusual looking compound. So that's why they isolated that.
Okay.
Thank you.
Yeah, thank you. Just a token of memento. Huh? Hello. Now we'll move to our next talk. That is by Professor Soyod Masood Hussain from Center of Biomedical Research, Lucknow. He has done his MSc from IIT Bombay and then PhD from University of Munster in 2008. After that, he worked with Professor Michael Muller at Germany during 2009 in the field of enzyme catalysis and biosynthetic pathway of natural products. Then he returned back to India and worked with Professor Krishna Group at NCBC TIAFR Bangalore in 2014. After that, he joined CBR Lucknow as assistant professor. Currently, he is associate professor there. Professor Hussain has several awards such as SP Suri Memorial Award, World Environment Day Award, etc. Currently, his research interest on enzyme discovery, development of new biocatalytic reactions, enzyme-based biosensor, etc. Today, he is going to speak on biocatalysis and heteroenzymatic synthesis of complex molecules. Professor Hussain, please.
Thank you so much. Am I audible? Is it okay? Should I put up or down? Is it okay? So thank you for the kind introduction. And I'm really thankful and honored like to be here and invited by Professor Tabriz Khan. And it's really a tough job for me to, present here after so many eminent speakers. They talk about their work. And so, yeah, and this is my first time at IIT Bhubaneswar. And I met so many people from like 20 years back whom I met. I mean, it's really, it's very nice to be here. So I'm Syed Masood Hussain from Center of Biomedical Research, and I'm going to talk about our work on biocatalysis and chemoenzymatic synthesis of complex molecules. So this is the overview of our research. So one focus of our research is to develop strategies, chemoenzymatic biomimetic synthesis of polyketide-based natural products. And that requires us to identify a step in the biosynthesis which can be performed using an enzyme. And the rest of the steps can be done using simple like chemical reagents. And this also requires us to identify new enzymes sometime, or maybe we can also use which are already known enzymes. And then recently we are also started working on to apply enzymes towards the development of biocatalytic methods, more general, which can be applied in any chemistry lab, just like you use any other reagent. And if required, we can also modify the enzymes just by doing the mutations so that we can increase their substrate scope as well as modify their function. So enzymes, I think we all have studied during school, and we all know that enzymes are biocatalysts, which are basically proteins. And these enzymes catalyze almost all the biochemical reactions in the living world. Even when I'm talking and you're listening, every moment of our life, enzymes are working non-stop to make us what we are. And what is so remarkable about enzymes is the selectivity that they provide in terms of chemo, regio, and stereoselectivity. And nature has evolved enzymes to work under mild reaction conditions, such as ambient temperature, neutral pH, and water as solvent. And although it has been thought that enzymes are highly specific, as you remember lock and key mechanism, but that is not always the case. I mean, enzymes can also have a broad substrate scope and they can catalyze different type of reactions. Now, so my talk is about a class of enzyme called NADPH dependent reductases. So as the name goes, they are dependent on NADPH for reduction. So the hydride for reduction comes from NADH, and these enzymes belongs to a family of superfamily of enzymes called short chain dehydrogenase reductase or SDR family. And they're recognized by the presence of Rosamond fold, which is a binding pocket for these cofactors like NADH or NADPH, and they're usually 250 to 300 amino acids long. And the enzymes that I'm going to talk here are naphthol reductases, anthol reductases, ene reductase, and imine reductase. So as the name suggests itself, what kind of a function that they will be doing, that is they are reducing these bonds. Now, so I would like to start with the most, let's say, fascinating as well as challenging work that we have done so far. It is the chemoenzymatic synthesis of bisanthraquinones and what are its biosynthetic implications. And bisanthraquinones, just to show you that these are dimeric natural products which have been isolated from various fungus, and they are present in, so here these anthraquinones are connected with each other by 1 bond, 2 bonds, 3 bonds, and even 4 bonds, as in case of plus rugulin. And they differ with each other in terms of substituent that are present in this position, as well as the stereochemistry. And if you just look closely, that you can really understand that maybe it has 2 bonds, maybe this is an intermediate for this particular compound. For example, this minus fludoskyrin. Same thing is minus deoxyriboskyrin could be an intermediate for minus deoxylutoskyrin. And it was only that minus flavoskirin is the only natural product of this type of a structure that has been isolated. This only one, despite the isolation of all kind of different more complex bisanthraquinone. And interestingly, it was only minus ruglosin, and its enantiomer is also isolated from different fungus. So they display a lot of biological activities. I mean, that is for sure because they are natural products. And if you look at the costs, because they are isolated in small amount, they're highly expensive. For example, if you want to buy minus ruglosin, it is $230 per milligram. Same thing is with plus ruglosin, which is $275 per milligram. And because of this complex structure, biological activities, and their chemical sensitive nature that I will talk later, and low abundance and high cost, they're really valuable for chemists to work on their synthesis. And this is just kind of a history how this field came up. So these molecules, some of them were isolated almost in 1950 and 60s, in the early 60s, and it took some time to give their correct structure. Another another decade or so, and it was only in 2005 that the first total synthesis of plus ruglosin were reported in 16 steps. Then when we started working in 2015 and on this chemoenzymatic biomimetic synthesis, so what we have done and achieved so far, that we could do this in just 3 steps. Some of these natural products were synthesized. Not only that, we could also identify the enzyme which were directly related to the biosynthetic pathway that might be involved in the synthesis of these natural products in nature. So it all starts with the retrobiosynthetic pathway. So all the metabolites that you have seen have been isolated from different fungus that you just put together. And with some sense of chemistry, you can just break every bond one by one. And what you arrive, you don't have to look at this complex structure. What you arrive is at this simple dihydroanthraquinone. So the idea is, if you can get such a molecule, you can just lead to dimerization, and then you can perform few more reactions to get up to ruglosin very easily. That was all the idea, based on the feeding experiment as well as the biosynthetic studies that were done. Although no such molecules have been isolated, as you can see, it could be very sensitive. For isolation, it may dehydrate and form the aromatic compound. But several scientists have proposed that such a structure might exist in nature. So it was Shibata who worked for several decades on these kind of natural products. And he proposed in 1956 itself that such a molecule might exist in tautomerism with another molecule. And same thing is with birds. When he gave his polyketide theory, that such a molecule might be formed in nature just by joining the ketides. And then in 1973, Shibata showed that it is possible to convert that minus flavostyrene, this structure. Yeah. So minus flavostyrene to minus ruglosin just by adding pyridine to it. And it follows a cascade, although did not isolated any of the intermediates. And then it was very clear that if you can have this kind of a dihydroimidine intermediate, you can convert it to flavostyrene, and that can lead to minus ruglosin. And for that, you can start with simple anthraquinone, which is widely occurring in nature, very cheap to buy also, imodine, which is the starting precursor. And inspired by this biomimetic, you can say synthesis, not complete one, Snyder was the first one who made these analogs for ruglosin, but in just 3 steps. But they started with this kind of a hydroquinone without this particular, this important, this hydroxyl that is crucial for the formation of minus ruglosin. And it was in 2005, same year, Nikolov was the first one to synthesize these natural products, the first one to plus ruglosin in 16 steps. So what they were able to do, they could synthesize this particular dihydroanthraquinones. It's not, this one. So they could synthesize this dihydroanthraquinone in protected form. And that what they wanted actually, that they deprotect it and oxidizes to get this S-configured dihydroimidine, and that could lead to the dimerization and formation of plus ruglosin. But that did not happen. So what they did, they first did the dimerization and followed by deprotection. And that is how they synthesized plus ruglosin in 16 steps. Following the similar strategy, they also synthesized another natural product, 2,2' epicytoskyrine A, which was only isolated later in 2006. So even before it was isolated, they could synthesize this molecule. So, and if you just look more closely at this synthesis, they also use an enzyme called porcine liver esterase for this enzymatic resolution in this synthesis. So by this time, it was very clear that if you have access to this kind of an intermediate, you can easily make this kind of a complex natural product, for example, plus ruglosin. And that is what we thought, that can we do it using an enzyme? So there must be an enzyme present in nature which can reduce imodine directly to S-configured dihydroimidine. So we started looking and to this enzyme. So first thing we got to this fungus, Coccolobulus lunatus, which is known to produce this lunatin and cytoskyrine, another type of like bisanthraquinone, where it is, you can clearly see that it is lunatin can be modified by several steps and then form the dimerized cytoskyrine. So there must be an enzyme which can be involved in the biosynthesis. And we found that it is one of the enzymes which was known for a long time, 17-beta hydroxydehydrogenase, which has been shown to reduce this astron in 17 position. And when we performed the phylogenetic studies, we found that this enzyme was very closely related to this MDPC of Aspergillus nidulans. And so what we need to get is to get this enzyme. Now, several of you, you can buy reagents in the, from the market when you do chemistry, but how to get an enzyme? So what you need is just the gene, that codes for that particular enzyme. And once you have that gene, you can order the synthesis of that gene cloned into the vector. And once you have this kind of a plasmid, this kind of a plasmid, you can actually put it in bacteria, and then it is the bacteria which produce a protein for you. And it is just, you can purify, similar to like you do column chromatography in your lab. And then you can also check the purity, just like TLC. Although there is an SDS page where we look at the size of the protein that have been purified. And then once we have this enzyme in our hand, then we tested this reaction. And that is the reduction of imodine, and where we use NADPase as a cofactor, but that expected, or this product that we expected, that did not form. So then what we did, we added sodium diethionate to it, And that forms a kind of a hydroquinone tautomers. And one of the tautomer was taken by the enzyme to get up to R configured dihydroanthracinone. So we did not get S configured, but we got R configured, which was opposite enantiomer of what we expected. At the same time, we also isolated chrysophenol, which is another natural product, as a side product, which is formed after the oxidation and dehydration. And another important fact in this, that how you get NADPH. So we actually don't use NADPH. What we do is we use NADP plus, which is much cheaper, and we use only 0.1 equivalent or in the reaction. It is actually the glucose which we use in higher amount, 5 equivalent or so, and another enzyme which is glucose dehydrogenase. So it is used to regenerate NADPH in the reaction. So glucose get oxidized to gluconolactone, and the GDH, it converts NADP plus to NADPH. So this cycle goes on until the reaction is completed. So that is how we are generating NADPH. And then using that enzymatic transformation, we established that it is possible to make not plus ruglosin, but minus ruglosin starting with imodine in just 3 steps in a biomimetic fashion using this chemoenzymatic strategy without any protecting group. So we started with the reduction, as you see, the same that I have shown previously, and then we oxidize it using lead tetraacetate. Although it took us some time, so we, for the very first time, we isolated this putative biosynthetic intermediate, which is R34, R-configured 3,4-dihydroimodine. And we also found that this was existing in equilibrium with another tautomer, which is this one. And then we also, from the same reaction, we also isolated minus flavoskirin, which is the dimeric product. And that we believe that was formed by the heterodyl reaction between this particular tautomer, as it is shown here. Okay. And then this minus, in addition, we also isolated chrysophenol as a byproduct. And then this minus flavoskirin was converted in presence of pyridine to get minus ruglosin. And for the very first time, we also isolated these intermediate, as you see here, which were formed during the cascade. So you just pyridine and you get minus ruglosin directly. In addition, we also isolated dianhydroruglosin. Again, every side product that has been isolated, they are all naturally occurring, natural products. So as I mentioned that, the price was very high, but over the years, we have optimized this procedure, not only, by changing the reagents and conditions, and now we can prepare this just a much, like 1,000 times less cost of this particular minus ruglosin at a very low cost. And this also implies that a similar biosynthetic pathway might be involved in nature in fungus to make minus ruglosin. Now, then we applied the same strategy to make analog, which is minus 2,2' epicytoskyrin A, starting with lunatin in these 3 steps. We also converted citrullozine to this minus ruglosin, although plus ruglosin was reported, but we made minus ruglosin. And we also look at the cascade, that is conversion of minus flavoskirin to minus ruglosin in pyridine D5, that how that starting flavoskirin get converted to the product through the intermediates. And then we also perform the heterodimerization. So what happened if you mix 2 different reduced and hydroanthraquinones? So we started with imodine as well as this reduced, citrullozine. We mixed them in 2:1 ratio. We got a mixture of minus flavoskirin B and B prime, and the mixture which was inseparable, and then we use this mixture to get up to minus ruglosin B in 3 steps. And then that was also converted to make a ruglin analog just by further oxidation and forming another bond. So, and there also we observe this, this conversion of minus flavoskirins to minus ruglosin through NMR experiments. And then we wanted to go a step ahead. Can we relate our chemoenzymatic biomimetic synthesis to the natural one, to the fungus? So we focus on this particular fungus, which is Stellaromycia lendicus, which is also previously called Penicillium islandicum. So And as I've shown that, and this fungus is known to produce these metabolites even more, but I'm just putting these one. So we already synthesized minus flavoskyrine and minus ruglosin, but we also wanted to make other more complex natural products starting with catenarin. I'm sorry that the font is too small that maybe you can't see it. I mean, so this work was done by these three people all together. So we identify from, because this particular fungus was sequenced, so we identified two biosynthetic gene cluster. And that might be involved directly in the formation of these natural products. And we identified two different reductases enzyme present in these gene cluster. And with the same procedure, we purchased the gene and we transform, and then we got these enzymes and purified enzyme. Then the first thing that we did, we used the same enzyme, these two enzymes, to check whether it can reduce imodine in the same manner. And of course, it did take place in the same way, like we got the R-configured dihydroanthraquinone here. And for the very first time, we also look at the substrate scope. So we took all the naturally occurring anthraquinones, whichever were possible. We synthesized them, and then we reduced them using this, especially the first one, from this gene cluster, ARTI, which we name ARTI. And we got these reduced dihydroanthraquinone, except this, where this is an ester, which was a non-natural analog. And when we tested this physione and question, they will not get reduced because of the presence of this methoxy in this position. And this also led us for the very first time to develop a method for the synthesis of racemic dihydroanthraquinone, because to determine enantiomeric axis, again, when you synthesize a natural product with particular stereochemistry, how do you determine their enantiomeric axis? That is one of the biggest challenges. So we were lucky that by replacing enzyme with sodium borohydride, we could get this racemic, and then we found that most of these products that were formed were completely, like, more than 99% enantiomeric axis. And because these enzymes can reduce like anthrol or a hydroquinone or hydroanthraquinone, we were the first to name these enzymes, this class of enzymes, as anthrol reductases. Now, very recently in a paper, I mean, they have proposed the mechanism. So it is not the hydroquinone, but it's the keto form that is binding at the active site. And it is NADPH which is getting it reduced to form this R-configured dihydroanthraquinone. Now, then we applied this particular enzymatic transformation using other, further, optimization. So what we did, so I have shown you that we dimerize and we form flavoskyrine using lead tetraacetate. So since it is a natural product, so we thought what other condition could be taking place in nature that can lead us to minus flavoskyrine. Can we do it with oxygen? And after a lot of optimization, what we found that in pH 6 and using just molecular oxygen by bubbling it, we can make flavoskyrine types compounds. And so we use those reduced compound, and we make several of these flavoskyrine analog. Some 6 of them. I'm just showing 4 of them, and the mixture, inseparable mixture of heterodimers also we got in this. Just by bubbling oxygen, starting with this reduced compound. Then we also converted this to this deoxyanthraquinones, although it seems very simple. But it is the way that how the regioselective oxygenation takes place in nature. So you start with anthraquinone and you reduce that to get this compound and then to get this 3-deoxyanthraquinones. So these are all naturally occurring deoxyanthraquinones that are isolated, and they have also medicinal significance. And we also make this simple, this diacerine, which is the osteoarthritis drug, in just 2 steps starting from anthraquinones. And that also has implications on the biosynthetic pathway that shows that how in nature, so if you are isolating this deoxyanthraquinone and anthraquinone from the same source, fungus or plant, maybe this is the way that formation is taking place. Now, coming to the more complicated, this anthraquinones, which is minus rubroskyrine and minus deoxyrubroskyrine, which appears to be the precursor for this particular molecule, and the catenarin. which might be involved as a biosynthetic precursor for the synthesis of these compounds. So when we perform the same reduction, so we started with catenarin, we added sodium diethionate, and we expected to get this kind of a reduced compound along with the this dehydrated product, islandicin. What we also got these two side products in large amount, and that happened because of the addition of sodium diethionate. Although we tried a lot to replace sodium diethionate with other reducing agent, we also try to do this step using an enzyme, but nothing works. So ultimately, we optimize these conditions, and finally, we got at best 45% yield of this one, which we use as a starting precursor for the formation of minus rubroskyrene. So when we added, as I showed that when we oxidize this, this particular reduced compound using lactic acetate, what we got is minus rubroskyrene. But here we could not isolate any of the intermediate which we expected, which is like flavoscarine type intermediate. And that was also not isolated in nature also. But then we can also assign the reason because of the formation of the hydrogen bonding and because of the formation of the presence of this extra keto group, they form the hydrogen bond, and that is why no flavoscarine intermediate was formed. But when we got this as a side product, but when we did the same reaction using oxygen and using molecular oxygen in buffer, what we got is this minus rubroskyrene in 55% yield, and we isolated this intermediate from the reaction mixture. And based on this, what we propose, it is not taking place through heterodiesarter reaction anymore in this case, but it is taking place through radical oxidative coupling. And that radical might have been formed because of the generation of ROS, because it's a quinone hydroquinone system, redox system, and that is quite a high possibility, which is also supported by some of the biosynthetic studies that I will talk later. And then we just converted minus rubroskyrene to minus lutoscarine by adding pyridine in presence of oxygen, which goes through this intermediate, which we expect that it might be formed. So this is the first synthesis of these, some of these natural products. Then making it more, then also we got plus iridioscarine, a dehydrated product by adding concentrated sulfuric acid. Then going to the more complex, this heterodimeric bisinthraquinone, we started with reduced imodine as well as this reduced catenarin. What we expected is the formation of these two tautomers after oxidation. And again, because of the formation of the hydrogen bond, we expect that this flavoscarine might not form. And we did succeed in isolation of this flavoscarine analog, which was formed where this could act as a diene, and this was acting as a, that alkene. And then this was heterodimerized, and then we could convert it in presence of pyridine to get minus deoxyrubroskyrine analog. So we did not get here the naturally occurring deoxyrubroskyrine. But when we did with molecular oxygen, we indeed get this deoxyrubroskyrine, which was naturally occurring, which shows that our condition that we develop, using molecular oxygen, most probably are the one that is taking place in nature. And there also we showed that, most likely that it is working through a radical coupling. And we also get this rososcarine as a side product, which is also a natural product. And in addition, we also isolated all the homodimerized natural products. And then we converted first the naturally occurring minus deoxyrubroskyrine to minus deoxylutoscarine via this intermediate, which we propose to form. And then it is minus deoxyrubroskyrine analog also get converted in presence of pyridine to form minus deoxylutoscarine. And then to finally validate whether it is really what we are getting. So we try to look for the intermediate that we have synthesized in the lab, whether they are also present in fungus. So we could purchase this Penicillium islandicum, which is the known producer of these metabolites from MTCC. Then we grew this fungus, and then we extracted some of the metabolites, which were confirmed either through mass or NMR. And then we could detect this presence of dihydroanthraquinone, which was again very difficult to isolate from natural sources, but we synthesize and through mass. Now coming to the original question, can we make plus triglycerin? I mean, that is because we were not getting S-configured dihydroenthism. So the logical thing is that we have to go to the fungus, which is producing plus triglycerin. And so luckily we found that this Phalanxophila scopiformis was sequenced. And then we tried to look at perform the sequence alignment. And we tried to look a similar enzyme like 17-beta HSDCl in this fungus. And we got one hit with 54% sequence identity. And we got this and we produced this enzyme. But what we found that this was not able to reduce like imodine or even imodine hydroquinone to our expected product. Another possibility is that we can modify the enzyme, which was known, and that we'll try to look at the active site, and we prepare these two mutants, and we found that even, the enantiomeric axis remain unchanged. So we had no hope, that how we can get plus triglycerin, and we struggled for a long time. And so this was very surprising. So today we know at least 10 of anthrol reductases, but none of them give this S-configured reduced compound. And today we know the reason. Very recently, Tan and co-workers, they identify the biosynergetic gene cluster of plus triglycerin. And what they have shown that these two enzymes, RUG-G and RUG-H, so it is the first the dimerization is taking place through oxidative coupling, and then it's the reduction. So that is why it is following a different biosynergetic pathway than what we expect for minus triglycerin. And then, so that was all about bisindraquinone. So let's make it a little bit more simple, which is about the chemoenzymatic synthesis of natural ketodiols and naphthalenones. So here we use an enzyme called tetrahydroxynaphthalene reductase, which is also called as naphthol reductase. So it is just 274 amino acids, NADPH dependent. And so this enzyme was identified from melanin biosynthesis. So melanin, and it was produced in fungus Magnopotha gracia, which is also the causal agent of blast disease in rice. And those studies have shown that T4HNR is capable of reducing this naphthol or this 1,3,6,8 tetrahydroxynaphthalene, and another enzyme T3HNR, trihydroxynaphthalene reductase, can reduce this trihydroxynaphthalene to form arvamilone. Then there is an extended version of melanin biosynthesis where several metabolites have been isolated, and if you look at this hydroxyjuglone, which is a hydroxynaphthaquinone, and it seems to be a reduced product, and another 3-hydroxyjuglone, and here it's a reduced product, but it was not known that how these metabolites are formed in nature and what kind of enzymes are involved. So we thought maybe it, because T4HNR, this tetrahydroxynaphthalene reductase is coming from the same fungus, maybe we can use that enzyme to get access to these natural products. So that is how we get 2-hydroxyjuglone, which was synthesized, and then it was reduced using this tetrahydroxynaphthalene reductase using NADPH, which was regenerated, and we got this cis-ketodiol. Similarly, we also reduced this 3-hydroxyjuglone to get up to this 2,4,8-trihydroxytetralone using this enzyme. And then we also look at other natural products, which were some of the toughest tasks we handled, and that was to synthesize these kind of substrates. So Tonaya spent nearly 3 years, and we were not very successful in getting this substrate. It took really a long time, but ultimately, we got some of these natural product, although we could not get the substrate for this one. But that is how, these hydroxynaphthaquinone are reduced. So it is a double reduction in this position as well as in this position. So they got reduced to get cis-nodulone D, which were only isolated in 2016, as well as we also reduced this particular, hydroxynaphthalene. And although it has not been isolated, but we expect that these molecules will be isolated, and we also make this R-configure nodulone C. Now, then we were also looking, can we, reduce these kind of get these kind of a natural products. So if you look at these two compounds, that is plumbagene, as well as these isoshinolone, it's easy to guess that these bonds are getting reduced to form these natural products. And luckily, even the dihydroimodine, which is the intermediate, that has also been isolated. So this is the proposed biosynergetic pathway, where it involves the first reduction where this alkene bond is reduced, and then there's a keto reduction, second bond is reduced. And then what we thought that maybe we can use ene reductase as well as a keto or naphthol reductase to get up to these kind of a natural products. So this work was mainly done by Arijit and Tanaya. And so first thing was to check, we use Plumbagene because it's commercially available. We use it as a, model substrate, and we screen different ene reductases, what were known already. So what we found that this Nostoc ER, it gave us 93% yield in presence of oxygen to get up to this dihydroplumbagene, which is this intermediate. And then we took this intermediate and tried to look at what enzyme fits best to get up to isochinolone. And we tested these naphthol reductases, T4HNR, T3HNR, LBADH, and HLDADH. And these enzymes showed that T4HNR works best for us, and it gave us 98% conversion. And then we put both the enzymes in one pot, starting with Plumbagene, and we tested it as a cascade. And what we found that Nostoc ER and T4HNR combination works best for us, and we got 99% enantiomeric access for this particular cis isochinolone. We also look at the, did the docking study to see that how the substrate is binding at the active site and what will be the configuration that will result in. Then we applied this cascade to various formation of these various natural products as shown here. So it started with Juglone, we got this isoscelerone. We also started with this particular where we, don't have the methyl group. We got shinanolone, both, enantiomers, as well as this these natural products, and even this teratosferin B also, where both have been isolated from the same fungus. And that is how we also, somehow confirmed that that is how similar way the biosynthesis also takes place. We also perform the kinetic studies with starting with Plumbagene just to compare that how these enzymes are working. And it shows that Nostoc ER is really efficient in doing the reduction for alkene bond. And then the intermediate was also tested, but it gave at least T4HNR gave us a higher efficiency. Now, after working for a long time on the chemoenzymatic synthesis of natural product, we thought, can we use enzymes to develop general bicatalytic methods? And that is where we started looking at anheterocycles, and they are really significant as we understand that they are highly biologically active. Many drugs, as you see here, tetrahydro 1-benzazepine, 2-benzazepine, and 3-benzazepine, they all, this substructure is present in several drugs and natural products. So that is why we thought, can we use enzymes to get access to this substituted anheterocycles? And so I'm just showing one of the reaction here where, that is for the asymmetric synthesis of this 2-substituted 3-benzazepine. And here, that's the only bicatalytic method that has been reported for the synthesis of this 1-substituted 2-benzazepine using monoamine oxidase. And what we thought, can we use imine reductase just by reducing the imine bond? Can we get access to various chiral substituted tetrahydrobenzazepines? And that was the work was mainly, the idea was also conceived by Anshul and Tanaya, and they did very well. And just to show you that this was my PhD work actually. So during my PhD, I work on the synthesis of substituted 3-benzazepine. And after so many years, I never thought that I will ever do this same thing again. But then we did quite a lot. So we first make this imine, which is methyl substituted, and we use it as a model substrate for the reduction of with various imine reductases to get up to this. And we use various imine reductases from different organisms produced in the same way as I showed you earlier. And then this is the optimization. And what we found that these two enzymes, IR4 and IR6, which is Cystobacter ferruginous and IR4 coming from Cribella catacombe. And these two gave us the best results in terms of conversion and enantiomeric access. And we confirmed their structure by crystal structure, single crystal structure, and we got both the enantiomers. Then can we have the substrate scope? So then we synthesize various cyclic amines in the same, starting with tetralone, and we first made various alkyl substituted benzodiazepines. One benzodiazepine. In bulkier, when bulkier groups were present, we only got one of the enantiomer. Then we also tested aryl substituted for reduction, and we got results as shown here. Only with the bulkier substrate we got less yield, but the enantiomeric access in one of the cases very, excellent, but in other case it's good, good to high. And in case of benzo substitute, we found we got only one enantiomer using the library of enzymes that we had. Then we also made chiral tetrahydro 2 benzodiazepine. We made these kind of a substrate which was present in equilibrium with this open form, ketamine form. And then they got reduced. We also confirmed the crystal structure for both the enantiomer using IR4 and IR6. We got these results. And then we also look at the substrate scope of these, for 3 substituted 2 benzodiazepine. And we, in most of the cases, we got both the enantiomers with good enantiomeric access. And then coming to the chiral tetrahydro 3 benzodiazepine, this was also synthesized, starting from 2 tetralone. And what we found that here, we got only one enantiomer. Aryl, substituted, cyclic amine, we could not get it because it was forming some other product. And that is how, then we also look at the kinetics with starting with this methyl substituted, alkene substrate, and how, efficient these enzymes, at least 3 enzymes that gave us the best results. Then we also, for example, there were some exceptions. For example, when we started with this methyl substituted 1 benzodiazepine, we got different enantiomer using 2 different enzymes. We look at that how this cyclic amine was binding to the active site, and that shows that how it is giving us the expected product. But when we have the fluorosubstituted substrate, we got the same results with using both the enzyme, where we have shown that how this, this is the NADPH and how it is getting transferred to form the same enantiomer. It is transferring. So in conclusion, that is what I have shown. We have used different enzymes, okay, like 4 different class of enzymes, and demonstrated that how we can, plan and execute chemoenzymatic synthesis. I showed you multi-enzymatic cascade as well as the development of a bicatalytic method. And what I believe that we have just started to stand up. This is completely new for, us, and it took some time for us to establish, but I think we are here at the moment, and still we have to start walking. So thank you so much. And this is my group and some current group members. These are the former group members who have mainly worked on these, and some of them are still there. Our collaborators and our funding agency, especially SERB and CSIR, who have really funded us, to make it possible what I could do here. Thank you so much.
Thank you very much, Sam. Now, I'll look at few questions. It's a very different journey. Organic, synthetic organic chemist, please.
Fantastic demonstration
Thank
of
you.
enzymatic catalysis. Just a general question first. I'm not sure if I missed it. So, do you use the purified enzyme or the wholesale?
So we can, once we check that people, so if there is a background reaction, then we don't use wholesale or crude.
Right.
If we have a background reaction, then we use purified enzyme. That is how we, because bacteria can also have its own enzymes.
Right.
So that we have to check.
And if you use the wholesale, you have to use this glucose, right? To get the.
Right.
What about purified enzyme in that case? You don't.
No, there also we use glucose.
You have to use
Yeah,
glucose.
right.
Okay.
For the regeneration.
Okay. Other thing is that in slide 35, if you can go there.
Oh, sorry. 35, please.
Yeah, go to the absolute configuration. I think you have determined. You just with your
Yes.
with your. Yeah. How did you determine the absolute configuration with this compound by X-ray? Because there is no heavy atom or anything there.
Right. So that is a problem, but we have some support from optical rotation actually. So it is not.
It is known. These compounds are known.
No, not these one, but some other derivatives are known. Like.
Yeah, but then you cannot compare the optical rotation. I think this is something you need to be careful.
Yeah,
about.
that I mean I really
Yeah.
I mean I agree with you
Yeah.
completely because yeah that we have
Yeah,
to
other
justify.
case you
that.
have a bromo something. there,
Agree,
that is
agree,
fine. This
completely
case, yeah.
agree. Right.
Okay,
We
thank
that
you.
we have to check more carefully.
Thank
yes.
you.
Thank you, Dr. Hussain, for your excellent talk.
Thank you.
I'm wondering, with such excellent work, you are saying you are the first this is the first invited talk. I
Yes.
think with this, talk, this should set the stage for many invited talks,
Thank you so much.
throughout the country. So yeah, I saw that, for your oxidation of 1,4-diol, you use lead tetraacetate. So I'm wondering what was the reason behind using that? Because, for oxidizing a 1,4-diol, there are other, very well-known reagents available like CAN or MnO2,
Right.
or in that case, sodium
Right.
periodate. So
Right.
is there any specific reason
Right.
for
So
using?
actually we had to perform this reaction at low temperature. So we were using acetic acid and lead tetraacetate mixture. We also performed with MnO2. But that was the, I mean getting giving dehydrated product more. So like this crizophenol.
MnO2.
Yes. I mean, because it's highly sensitive. I mean, we have to keep temperature like at 5 or 10 degrees for most of the, transformations, so that otherwise it is getting dehydrated.
Because our experience is, MnO2 is the mildest in, oxidizing this
Yeah.
one for.
Yeah, we tried that, but that did not work well for us.
Okay, fine. Other thing I saw that, in presence of Bock, you could successfully open the lactam ring using methyl magnesium bromide.
Right.
So this reaction works nicely. I see the yield is a bit low, I guess, 47%.
I mean, yeah, I mean, that's right. Yeah, I mean, it worked, but I mean, again, so we were not focusing mainly on the like substrate synthesis. So I haven't shown much of the substrate synthesis, but yes, I mean, that's the only reagent that we are using to make all the substrates. Because that was a common strategy to get up to these substrates.
Thank
Yeah,
you very
yield
much
is
for
low,
your
definitely.
excellent talk. Thank you.
Thank you.
Yeah, excellent talk. Can
Thank
you
you.
go to slide number 21?
21, please.
20.
20.
Yeah, here you told radical 20.
Yeah. Sorry, I'm doing it. Okay, just a moment.
Slide number 20.
Yeah, just.
No, go to here. Here it is. If it is a hetero-Diels-Alder reaction, it is hetero-Diels-Alder reaction is a inverse electron demand reaction. So in that case, how that particular double bond is electron deficient, where you are showing the 4+2. So, and the below one is electron rich. Then how hetero-Diels-Alder reaction orbital, matching is happening?
Yeah, that. Yeah, I'm not sure about it actually. But I mean, so we expect.
Because LUMO of dipole interacts with the HOMO of dienophile.
Right.
So in that case, your this HOMO will be raised, the below one, that enol, and the upper one is the LUMO is down. If it is inverse electron demand, that the below one should react. It's not homologous. That is the alpha beta unsaturated. No, you see that one. That is a keto.
Yeah, that's, yeah, I mean, these tautomers are in equilibrium. Maybe that's how it is shifting. I mean,
Top one is also on 3-diketone. No. Mm-hmm.
could be right.
Yeah, yeah.
Sorry.
So, a very nice talk, Syed. I have a question here.
Yeah, please.
In general, the enzymatic reactions has issues with scalability. Typically, what scales you pursue these reactions versus what extent you evaluated the scales of these reactions?
So I think we can easily do 1 gram, although we don't require,
1
but
gram?
1 gram also we can do.
Okay.
I mean, if required, there's no problem because enzymes that we are producing in the lab, we can produce at any amount.
So typical methodologies that you have shown, what
that
scales?
can be scaled up.
What scales you have established?
So usually, I mean, 100 to 200 milligram, that's what we do. I mean, so for example, this minus fructose, we have checked up to 500 milligram or even 1 gram, just to show that we can make this enough. But I mean, there's no issue, I mean, that I feel that should be with the scalability.
Yeah, it was a nice talk.
Thank
So
you.
I just have kind of curiosity. So we know enzymes are quite specific, but when I see some of the reactions where you see the shows selectivity is quite less.
Right.
So what could be the reason, even though they have kind of fixed three-dimensional structure?
Yeah, I think so. It depends on the how it binds. I mean, so because these imine reductases, they are dimers. I mean, they are not like monomers in like I have shown in the beginning also. I'll just go at the end. Yeah, so these are actually dimers and the reaction takes place at the surface in between. So again, the previous enzyme that I was talking, they are coming from the biosynthetic pathway, directly related. But these enzymes are not. So, I mean, nature is not making these substituted, I mean, like benzodiazepines. So we are, I mean, again, every enzyme with some difference, in sequence, amino acid sequence. I mean, so they have a different enantiomeric axis binding mode. So it's very difficult to pinpoint that what is the reason. But of course, when we have different, like less enantiomeric axis, they can bind in both ways. I mean, that is the possibility. But it is also always possible to find an enzyme which will works best for a particular reaction. I mean, we can find it, but we have a library that we check, and most of 3 enzymes work best for us. I mean, if there is a requirement that we have to make one particular enantiomer in high, that is the possibility. I mean, it is always possible to get it.
Okay, so I have one small query. For your this naphthoquinone natural product, along with the ketone, you have some more hydroxyl group. So how stable are those functional group? Because they can go elimination and give you the aromatic compound.
Yes, I mean, that's, you mean the intermediates?
Yeah, so like even the natural product also. You have a dihydroxyl.
Yeah, I mean,
ketone.
so, I mean, for us, because we do most of it in water and we are not removing any protecting group, so it works. I mean, we can easily extract it. It's not, I mean, they are stable most of the time.
Most of the even
Yeah.
under column chromatography.
Very, yeah, quite stable.
Okay, thank you.
No problem.
It's fascinating actually. Yeah.
Thank you.
So I just wanted to ask like how easy or how difficult to those things to do inside lab. So as a non-expert, so can we do in our lab?
Everyone can do. I can tell you. I can send you all, I mean, our enzymes in the vial, and you can just make buffer and add your reagent, and that's it. And then you extract it. I mean, it's only that expertise to, again, we also had failures. I mean, when we identify some gene from biosynthetic pathway or anywhere else, it has a quite fair chance that it may not work. I mean, what I was showing that were the successful. So we had a library. Again, some of them are really not doing anything. So, I mean, so the one, for example, nostokia, it can reduce any alkene bond. I mean, that's what we believe. I mean, not any alkene bond, but of course, something similar to what nature like naphthoquinones or something like that. That we believe. So, for example, is latrines also. What I believe that there might be an ene reductase involved at the end. I mean, that is what I mean, when I'm looking at that kind of a structure. Oh, I think it's easy. I
So
mean,
once we have the enzyme, so simple organic chemistry.
simple, just like any other reagent, just in water and buffer, and that's it.
Okay, so I hope it is as simple as you say. So we'll try actually. It's very
we
fascinating
add-
actually. Yeah.
So like solubility issues, so we solve it using different co-solvent. So you have to add a small amount of co-solvent to dissolve your organic substrate. So sometimes it is DMSO, sometimes it is isopropanol, acetonitrile. You can even use hexane, whatever is soluble. So it is but we have to use in a small amount so that our enzyme don't get denatured. If you use in large amount, then it has a problem. But 5 to 10%, it is fine.
Yeah. Then let's thank Professor Hussain.
Thank you so much.
Sir, 1 minute. Sir.
Yes.
I have.
We can have at the tea also.
Tea break, while tea break, we'll discuss that.
Okay.
Yeah, thank you so much, everyone.
Now, felicitate Professor Hussain with the moment. Thank you.
Thank you. Thank you. Thank you. Thank you.
I would like to request Professor Perucharal from IIT Bhubaneswar to felicitate Professor Pal for chairing this session. Thank you, sir, for the gesture. With the conclusion of this extremely insightful lecture by Professor Mukherjee and Professor Hussain, we now come to the end of first technical session of day 2 of the workshop. We will now break for a blue ocean tea break, which I am sure will keep us zestful for the sessions ahead. I invite you to kindly take your tea and reassemble in the hall in another 10 minutes. Thank you.
Hello, there is an announcement. Please come inside because we are going to start soon the session.
Suggested me this. So thank you very much. So let's assemble before the lunch break for a group photo. So please take a note, Badalji. Yeah.
I once again warmly welcome you all. I request all the participants to kindly be seated so we can proceed further with the next session of the workshop. I hope we are all rejuvenated after the tea break. Thanks to Blue Ocean. Let us resume session 2 of day 2. This session will be chaired by our Honorable Professor Rama Sastre from Aizer Mohali. I humbly request sir to commence the proceeding of this session.
Good morning, everyone. The shock of the day. So in the last minute, I was rather asked to chair this session. Let me introduce my friend, Dr. Madhusudan from IIT Kharagpur. I know Madhusudan during my student days when he was integrated PhD student at IISc Bangalore. He used to work for work with Professor Mehta that time. it was brief. We moved on to pursuing PhD to University of Münster, Germany, with Professor Tudor. Then he has held a couple of postdoctoral stints with well-known chemists Professor Ruping and Professor Martin Ostrich both from Germany. Currently, he's associate professor at IIT Kharagpur. He's a very well-known chemist for his contributions in catalysis and also total synthesis. Consequently, received several recognitions, prestigious awards. Some of them are Faculty Excellence Award from IIT Kharagpur. Recently, he has been awardee of Swarna Jayanti Fellowship, Merck Young Scientist Award, Aura Scientist Award, TIMI Chemistry Journals Award, and few others. I can go through a big list of awards that he has received. With this very brief introduction, I now invite Professor Madhusudan for his lecture.
Thank you very much, Professor Ramasasti, for your very kind words. And I'd like to thank Professor Tabrez Khan for giving me this opportunity, and also Professor Roy there and whole organizing team. This is my first ever visit to IIT Bhubaneswar. So I have been some couple of times in Bhubaneswar, not in the main campus. So okay, going without much details. So today. Okay, today I'll be discussing about our work on mostly focusing on the cobalt and rhodium catalyzed CH bond functionalization, and the special emphasis will be given on the ketone and amides. Okay. So our group at IIT Kharagpur, we started exactly 9 years before, and we mostly focus in this area where we work on the functionalization of indole, pyrrole or carbazole and their application in total synthesis. But today I'll not talk in this area because I'll talk on other side here, like CH bond functionalization. As I mentioned, it will be mostly focused on the cobalt and rhodium catalysis. Before I go in detail, so let me just briefly introduce how these mechanistically work. There are two types of CH bond activation mechanism we can think of. One is outer sphere mechanism, where like metal involved but not directly in the CH bond activation step. Mostly it work under the influence of the ligand attached to the metal, and metal most of the time is a high valent. So like one of such example, the CH rhodium can go there and it can form the rhodium carbenoid and it can undergo CH insertion there. So this is the one which I am not going to discuss. We are not focusing there. Another one is the oxidative addition of this RH bond, like this one of such example, or sigma bond metathesis under the inner sphere mechanism, where metal carbon bond formation occurs and metal directly influence the bond formation. So one of such like oxidative addition I already mentioned, sigma bond metathesis. Okay, this exchange occurs, and another one is the electrophilic substitution type of mechanism. This is the reaction mostly I'll be focusing throughout my whole presentation. We are particularly interested. There are several tangential metal, considerable number of work, amount of work has been already reported. So we are mostly focused on this group 7 tangential metal here, and cobalt, rhodium. We are mostly focusing, but our special emphasis is always given to the cobalt. We always try to work with the cobalt, and time to time we also explore with the rhodium, because rhodium has a very interesting reactivity. It's a quite robust and many reactions can be done, but cobalt relatively more challenging, particularly this first row tangential metal, considering their cost. The reason is you can easily make it out from here, like CP star cobalt, the precursor is cobalt dicobalt octacarbonyl, like 1 gram cost only 600 rupees approx. For rhodium, it's really expensive, and iridium also quite expensive, but not as much as rhodium. So the cobalt, in terms of cost, it has advantages. All the cases we have to add CP star, that can be common. Another interesting property with the cobalt is their cobalt carbon bond electronegativity differences. If you see here, it is around 0.67. Okay, it's quite a lot compared to carbon rhodium, carbon iridium or ruthenium or palladium. There is approx 0.27 to 0.35, which means the cobalt carbon bond polarity is quite high. And when the bond polarity is quite high, it can be reacted quite efficiently. Like you we do like Gigner reaction. So it can attack to several electrophile which may not be possible with some other these cobalt other tangential metal carbon bonds. Not only that, cobalt also is a small because it's a fast low tangential metal, so it can fit or it can have the steric effect also. Okay, and it can also trigger the selectivity which has been observed in several cases. So cobalt carbon bond is quite polar, so it can easily attack as a it can easily attack to many different to 1-2 addition to several electrophile, and in many cases it has a like a complementary reactivity what we found in our reactions. All right, the story is this about this cobalt complex is quite, I don't know. Not the pointer. I don't know. I cannot. Either possibility like I can change. Yeah. No, it's working, but the pointer is not. Laser is not working. First one, but it's very mild. Okay. No. Okay. Maybe I'm holding wrong. Yeah. No. I'm closing this, so that's not the right way. Sorry. It's fine. It's my mistake. All right. Okay. Sorry for the interruption. So the cobalt, this complex, it is not something new. Though this area appears more recently, like in 2013, about 9 years before, this first complex of the CP star cobalt 1 was isolated by King et al. In 1967. It's a long back. And if someone treat this intermediate with iodine 1 pot, it gives us this very stable, bench stable complex cobalt CP star. Okay, it's a cobalt 3. Okay, cobalt 1 is quite reactive under oxygen. So this is quite easy to make it. And until recently, its application was not reported. So until recently, like Professor Matsunaga and Kanai, they have reported a cationic version of such complex for the CH activation followed by addition to this imine, like your nucleophilic atom. After that, they also reported another nice work, which is seminal work, like making this complex for the CH activation. They showed that this CP star cobalt, this is bench stable, can also be used. Since then, this become the most popular because it's easy to make it. One can make in several grams in 1 day only. So it's very easy. So since then, there are several groups who are involved. And if I consider like Professor Matsunaga Kanai, they are the pioneer. Then Glorias, Ackerman, Elmans, others are there. And from India also, Bhaskar, then our group, Prabhu, Anvarsan, Power, Upendra, and Ravi Kumar is also in the audience. So they're also heavily working. And so a good number of group has been joined this venture, and considerable number of interesting reaction has also been developed. So we'll focus about what we did and what is our contribution here. So if we think like ketone is a very interesting functional group, but other way, like if you do Friedel-Crafts reaction or whatever, it goes to the meta or not ortho. So we thought ketone as a directing group can we use, but there are of course some other metal has already been used, but with the cobalt it was not used until we published this one. This is the first time we did. So then ketone has two problems. So it can undergo easily enolization. Not only that, after it analyzed, though aldol reaction is quite challenging, but there is a possibility. Not only that, under the CH activation step, we use several oxidant. If we use several oxidant, it can undergo dimerization, and not only that, it can also go alpha hydroxylation because we reagent we use as an electrophile. Also, it can undergo 1,4 addition. So ketone has several like limitation in terms of side reaction. But if we can overcome those side reactions, we can do some nice transformation. As shown here, another challenge with the ketone is it can undergo cyclometallation, but this, because this is a base metal and ketone is weakly coordinating, these complexes are not as stable as rhodium versions. So that makes the complex fairly unstable, and we need to tune the reaction condition properly so that we can do some transformation. So what are the reactions we are interested, like amidation, also alkynylation or hydroarylation or allylation. These are the majorly we are working in this 4 transformation. So I will be now discussing about the CH allylation reaction as shown here. As shown here, like ketone directed, several functionalization has been reported. Okay, halogenation, CC bond formation. I'm not going like halogenation, hydroxylation, alkylation, arylation, all the things. But alylation was not reported, and also cobalt in combination with this ketone was not reported. So we combined these two, and we wanted to develop one ketone directed alylation because the product has several applications. As shown here, without going in details, we could do this ketone-directed alylation with excellent yields. Catalyst loading is 10%, but with the cobalt, there is one limitation, I would say, like the catalyst loading generally goes to 5 to 10 more %. As shown here, we could do several examples, like we can have the several linear or hindered one. We can have electron withdrawing group or electron rich, different other like aromatic like naphthalene or anthracene, indole without protecting group, that is also interesting and quite like it was quite nicely done. We can have say, gram scale reaction, chalcone can also be used for the alylation chemistry. We have several examples, some of the selected we are presenting here. We also saw the application of this method. If we have the allyl group, the beauty of the allyl group is it can be, we can, like this is allylic position, we can do functionalization. This can be also used. As shown here, we just simply chop it up, treated with ammonium. We got this azatetracene, nice molecule. Also, this molecule can be made in grams. From there, in one like reaction, and we can do this intermediate, which is used for this type of materials, and it's very, I would say, needs several steps. We can do in few steps only. And also from here, if you do the occur oxidation from the starting ketone in 2 to 3 steps, we can get here. From there, in one step, this natural product synthesis is there. So we can say that formal synthesis is achieved from here to there. Another alylation chemistry we also develop is indole alylation, particularly I would say prenylation. So there are several prenylated natural products, particularly indole or carboxyl based, already reported in the literature. So there are more than hundreds of them. So if we can develop one nice method, we can achieve several such alkaloid synthesis directly. As shown here, Professor Matsunaga and Kanai, they reported this alylation, they need to use this directing group. So using this allyl alcohol. So we thought, can we go with the cobalt and can we use a relatively, we are working with the thiocarbamate as a directing group for quite sometimes. This is very cheap. We can, it's like acetate. Okay, we can protect it in several grams and also removal also easy. So if we can do this condition, we don't need any silver. Okay, access to several other interesting molecule like 1,3-diene. This is cobalt we are using, and easy deprotection and easy removal. Okay, so protection and deprotection of this directing group. That was the advantage of our method. As shown here, with the reported method, what happened? It's very difficult to control both sides of the alylation. Like it generally give mixture, like 2 to 1 mixture. Even you use one equivalent of allyl alcohol as electrophile, very difficult to get monoalylation. But under our condition, probably this thiol group may be poisoning the catalyst to some extent. That helps to stop the reaction exclusively at the mono. That doesn't mean we cannot do the dialylation. Yes, we can do 1-fold, 2-fold dialylation also if we want. Okay, so just both are possible, but first it do the monoalylation selectively, then dialylation. Not only that, reaction work with several other examples like prenylation also can be done, geranylation. We can do 1,3-diene, several examples are there. We can have substitution here, so it goes away from the steric. Not only that, we can have, when cyanide is there, we can get here. We can have several like pyrrole, indole also good substrate. We can get this such a functionalized one. Alkyne can also be placed. So scope is quite broad and functional group tolerance also quite nice. Another alylation chemistry we did with the aniline. So aniline alylation, see, looks simple, but there is some problem. What happened? Once the alylation work, if the conditions are not mild, these double bond undergo migration and they are very difficult to isolate. And this is the problem with the reported method. And also, when acetate used, like it also further react to give this indole. So getting this alylation product was challenging. So it was actually first of the work we did at IIT Kharagpur. So we thought, can we use one directing group, which is like quite good coordinating. At the same time, can we make it weakly coordinating by putting one very electron withdrawing group like trichloro acetonitrile we can use to protect this one. So trichloromethyl group here, which indeed work well. I'll show you, which is very rare to do CH activation at very low temperature, -20°. So that work quite nicely at -20° with the rhodium here we use 3 mole % catalyst loading we can get. We can also use this one to do the selective monoallylation. The selectivity again is a problem. We could do selective monoallylation. This is the allylating agent we introduce for such CH activation. And if we use the carbonate, then we can do the dye. So using the same catalytic condition, by tuning that, we can do a low temperature, we can do mono or dye, all possible. But there is one limitation. This project we could not carry forward. The reason is deproduction was little bit difficult that time. Now I'll be discussing about the ketone-directed CH alkylation reaction. We know the CH alkylation reaction can be done by Heck type of coupling or Fujiwara Moitari type of coupling reactions. Okay. So in this line, CH activation has also been used quite extensively, but with the ketone, in combination of cobalt, we checked we could do several alkylation reaction as shown here. And like we can do the ketone directed with simple acidophenone, or we can have the electron rich system, we can have the free hydroxyl group, we can have several other like heterocycle, chalcones, or phosphonate, sulfone, all can be used for our reaction. But again, we struggle with the catalyst loading, so we could not sort it out yet. With the, it's quite high, I would say. We can also do the synthesis of cinnamic acid directly, because it's very difficult to use this as an alkylating agent. It doesn't work. We tried, but we thought if we use one protecting group on the ester, which can be deprotected under the reaction condition, that can solve the problem. The yield are in the moderate, but we can get the directly acid, but reaction work followed by the hydrolysis. So we can get this several cinnamic acid derivative, which are quite challenging to get directly. Also, we can do this sulfone. Like first we need to add the electron withdrawing this acidophenone, the CH activation, one side, and then one pod we add another ketone, we can go the both, okay, directly. Also, we can make this gamma PP AR antagonist by doing this alkylation, and this was the reported only, we follow their protocol, and we can get this one directly in 2 steps from here. Vinylation reaction, very simple, but the problem with the vinylation reaction, they undergo polymerization. We know polystyrene. If you take anything in a bonded acid or base or radical, they undergo rapid polymer formation, polystyrene synthesis. So that vinylation with the ruthenium and rhodium catalyst was reported. So we introduced one nice method under redox neutral condition to get this vinylation reaction under cobalt catalysis. So here, this is our leaving group, and the functional group can be changed. I'll show you the scope. As shown here, we can do several these vinylation reactions using this under this condition, 5 to 10 mole% catalyst loading, depending on the reaction we are using. So we can do the vinylation at this position because of this secondary effect of this coordination effect here. We can have the free OH group, amine, even the sulfur also not a problem. We can have the carbazoles and several other substrate. I am not going in details. If we change this electrophile here, instead of hydrogen, ester under the redox neutral condition, it's not a Fujiwara Moitari type reaction, but it's a redox neutral condition. The similar product can also be isolated under the similar reaction condition. Now, the one of the major area we are working is the amidation. That is where we work quite heavily. And we found, we actually choose some target and we want to achieve them using our strategy. If we check this all natural product, there is one thing common, there is one ketone group, okay? And there are 2 CN bonds. The strategy will be how to get this natural product in few steps without without much pre-functionalization. That is possible because ketone-directed CH amidation can be one solution to that. So this is ketone. We can do directed CH amidation and 2-fold CN bond formation, like one and another one CN bond formation, that can give this type of advanced intermediate. From there, we can get such alkaloids. The strategy to execute, so we took the ketone-directed CH amidation, and here what we did, we want to see the complementary nature of the cobalt and rhodium. So we check the scope with both the catalysts. As shown here, this is the amidation product. We can have excellent scope. I will show briefly the scope here. And each and every example we conducted with both the catalysts, the yield are reported. We found like both the catalysts have their own role. Both are good. Okay, for some substrate, like as shown here, this case, cobalt gave 91% yield, rhodium gave 20%. Rhodium here did not give any product, but cobalt gave quite nice one. Here, cobalt provided at least some product where it is electron withdrawing group, but rhodium did not give any reaction. But at some other cases, rhodium was slightly better than the cobalt. But the cobalt was more reactive and it worked with almost all the substrate. But rhodium failed for some substrate. So that says the cobalt has some specific or it has own nature or characteristic in this catalysis. Now, how to make this natural product? So we use here rhodium because cobalt also we can use, but rhodium gave slightly better yield for this substrate at least. So we could do this CH amidation, and we can see there this is electron rich side. So that gave us the major product. We got the mixture of 3 to 1. Then we deprotected this one. We got this free amine, and then under this condition using tertiary butyroxide in DMA, so another CN bond formation work, we get this total EFN A, and then mom protection of this NH provided total EFN D. In a similar way, we did the methylation followed by the hydrolysis of this benzoate. We got these two. Okay, and from there we again did this copper catalyzed CN bond formation here or there. We got this intermediate. From there, arborenin natural product also synthesized. Now I'll discuss how we could make this natural product, at least formal. Until here we got it in 4 step using cobalt catalyzed CH amidation. I'm not going details about this because it is quite similar. We got this natural product intermediate. From there, formal synthesis is reported. This amidation work was done by Saurabh, is one of the fantastic students I had. He already graduated doing postdoc. Also, these products are very important because we can use them for several synthesis of several other heterocycle. I'm not going like indole, isoquinoline. This is anti-tumor agent. So this is we showed the demonstrated the application. Also, we checked that how the reaction work. Like we did the what type of mechanism. So electron withdrawing or donating group we use. Like it gives the electron donating working better. It is base assisted electrophilic intermolecular substitution. I'll discuss at least one mechanism in details later on, not this one. Also, deuterium labeling experiment shows that it is not reversible, the CH activation step. And here also we did also by competition and parallel experiment, it shows primary kinetic isotope effect more than 4, which means the CH activation step in the rate determining step. We also invested quite a lot time to check, isolate such intermediate. We never got the crystal structure. Last few years we're working on this, still we are not successful, but we could detect in mass spectrometry such intermediate. At least we can detect them. So this using all these things, we propose on catalytic cycle. Before that, I want to, because students are there, we want to show how this primary kinetic isotope effect work. You know this vibrational energy level, it has a like 0 point energy. When the mass is more, okay, like deuterium, mass is more, reduced mass is more means vibrational frequency will be less, so 0 point energy will be much lower. So the bond dissociation energy for the heavier atom here to there, okay, under some conditions, it will be much more. So when you incorporate the deuterium, it doesn't show the primary kinetic isotope effect, means it is not in the rate determining step. Okay, so this is the catalytic cycle. As I mentioned, the CH activation is not reversible. Okay, we got this one in detected, and then this undergo coordination, and we could get the CH migratory insertion here, and then we got the product, and catalyst come back and again take part for the second catalytic cycle. All right, now I'll be discussing about the bienol. Bienol is one of the molecule many of our like interested, and particularly considering the asymmetric catalysis. It has a tremendous role. It has played for several decades. Okay, the way we get the bienol is, or derivative of the bienol is just like we do the functionalization here. So we do the directed lithiation, and then we do the CH like functionalization or whatever, bromination, Suzuki coupling. So we thought, can we use this one like this type of directed CH activation for bienol functionalization? Okay, so that we can use them directly. One of the way is the lithiation, and then we can add several other functional group as listed. It's almost reported, but directly CH activation there was only few reports. So we thought, can we do this one? So our most of the interest was focused on the amidation reaction here, as well as alkylation reaction, which are quite challenging on this substrate, and this can lead to the other catalyst development or ligand development. As shown here, when you use this thiocarbonate as a directing group, first to develop the method, we could do this amidation reaction. We have several examples, only few are shown here. Like we can have this one 64% yield. We can do the twofold bienol monoamidation. We can do octahydrobienol. Also, we can do this amidation. Also, we can do this twofold. This is a really interesting example for us because it's quite high yielding. Okay, and catalytic is still 10%. So we could do this one. Also, we can have this like acylichiral, this type of molecule. Also, spinol or like tyrosine derivative. We can do this amidation reactions. Now I'll be discussing about the alkylation reaction, mostly done by Suzuki or Kumada coupling reaction. Can we do by using CH activation method? As shown here, again we use this, and here when you use the sulfur reaction did not work for this alkylation. So carbonate was the better directing group, and this is quite cheap also. So we can do this CH1,4 addition type of reaction using this acrylate. We can get this one, also several others like iodine also, like which Suzuki reaction will not be possible. We can have this biphenyl system. We can have this bienol. We can do the twofold also, spinol, or this estrone derivative. So we can do this alkylation on all these substrates. There is some nice stories here. I'll discuss a little bit. If we take this carbonate one side, or let's say we are taking both as thiocarbonate, so diamidation work. But if we do this alkylation, it did not give any product. So thiocarbonate doesn't work for this alkylation. If we have one side thiocarbonate, other side carbonate, this is interesting one. It selectively for the amidation, okay, with the condition we could do selectively amidation. For this one, I'll come here. With this carbonate only, it did not give, but the alkylation can be achieved, okay, with the carbonate. But if you mix it, one side thiocarbonate, let's say you want to do selectively here, okay, you put with this one, okay, and you can get the selectively amidation at this stage. That's interesting, and it doesn't react at all here. But if we cannot do the alkylation here, but if we simply deposit it, then it will work here. So we can two different sides with the phenol can selectively be functionalized. That is quite challenging actually. We could do it. And also when we have this, it did not react with this one as I mentioned earlier. And this play the, even with the carbonate, if we mix this one intentionally, it did not give any product because probably it poisoned the catalyst at some stage. All right. So amide bond formation also quite challenging, and particularly for the student I want to mention, see if we say like sheaf-based synthesis, you take the aldehyde, amine, mix it, water goes away, you get the imine. But it doesn't work the same way for the amide synthesis. Then our life would have been much easy, particularly for the peptide chemist. If you, what is the problem? Can you tell? Like if you take the acid and amine and mix it, it doesn't, what it happens? It's just like acid-based reaction. So it will be ammonium salt, it will be the carboxylate, and this get deactivated. So it doesn't react at all. So the limitation, you have to use the stoichiometric activating agent. It produces a lot of chemical waste and functional group tolerance. So this is the issue. Okay, so amide synthesis is still one of the research area many of synthetic chemists work. So we use this benzoxazole for this directed amidation for such substrate. We can have the salicylaldehyde or amine also here. We can do all this amidation chemistry quite efficiently. But the interest we had particularly instead here like this enamide synthesis. Okay, so how to make such enamide, which is a key features for several natural product as well as bioactive molecules. So getting this enamide and particularly the selective way, either E or Z, is always challenging, and we want to address this challenge. And here Subhankar comes to the picture. Like he came one day, he want to use this as instead of benzo. So benzening, if we use like remove it, we have this isoxazole. So he smartly choose this electrophile and did the same chemistry here, and it worked beautifully. Okay, and what actually happening? We are harnessing the enamide by reducting NO bond cleavage using under the CH bond functionalization strategy, and also because this is already cis and that geometry stays in the product, so we could get this Z enisomer selectively, and this chemistry was inspired by our previous work here. So the scope was again quite nice. Catalyst loading 5 more %. We could do further optimization. So as shown here, we can get several enamide selectively Z, and the functional group here or there, like we can have several aromatic group as shown here. We can have the heteroallyl group. We can have the chalcone. Even the more conjugated system, we can have this side also. So we can get several examples. Only few are shown here. So I'll discuss on final amidation reactions, which we recently published here. This molecule is very interesting. I did not show that slide because of time. So this type of molecule, either C double bond H both side or oxygen both side, or one side sulfur, one side oxygen, is very challenging to make, and it has interesting biological activity, and making it, as I mentioned, quite challenging. So we thought, can we do it like this? amino carbonylation. Actually, it formed the carbonyl and amine. So in between this CH bond, this introduce. Okay, we just incorporate this amino carbonyl group. So we can get this amide product directly by nucleophilic attack like this. So cobalt was again the catalyst for us. It worked with much lower catalyst loading, 1.5 mole%. Now we are happy a little bit. So we could get this example, and if we just simply, without isolating the product, continue the reaction for another 12 hours, like 26 and 36 hours, another 10 hours, we could get this product also in excellent yield. So we can get either this or this, depend on the reaction time. Here are the scope. Pyrrole can be used. We can do also in gram scale. We can use several substitution here. Indole also good substrate. We can also get this type of product directly in quite good amount, and also several substitution can be placed. Okay. Now here is another one in other way. Here amine comes here. Can we do the other way? So NCO. Okay. Other way of connecting this amide group at the both side of the pyrrole or indole. Here, this chemistry was very efficient using this thiocarbamate directing group. As shown here, catalyst loading was decreased as low as 0.5 mole%, which is very, I would say, rare in CH cobalt catalysis. Okay. Not only that, when you use the 0.3 mole% catalyst loading, the yield was 75% and turnover number was 250. Still, it is one of the best, I would say, in this cobalt catalysis, and we could do this one. Here, I will discuss this chemistry a little bit in details about the mechanism as shown here. Like if you take this thiocarbamate group and we did the intermolecular competition experiment with the deuterium, so Kh by Kd was again, we mix it together and did the reaction was less than 2. So the CH activation was not involved in the redetermining step. Same by parallel experiment also. Also, this reaction is reversible because we found a considerable amount of deuterium incorporated. Also, if you take it, it also lose when you use the water. Okay, so the CH activation either not rate determining, and also it is reversible. And this is the first time we also involved in DFT studies by our own research in our research group only. So as shown here, the first step of the mechanism, it undergo coordination to this active catalyst. Once it coordinate, it will be doing this base assisted, means acetate assisted CH activation through transition state 1 to get this cyclometallic species, which we have a nice HMS spectra as well. So this is the mechanism we are proposing. So this acetate will be taking this proton and this cobalt carbon bond will be forming. You can see this. This is your acetate which take this proton and cobalt carbon bond forming. Okay, we get this cyclometallic species. So it is energy is quite is not redetermining, as I mentioned. Also DFT calculation strongly supported this one because activation energy is only 1.585 kilocalorie per mole. All right. This is the intermediate we got, and first time after 5 years of hard work, we got a beautiful like this spectra HMS. Okay, so this is very much there. Still, we are waiting for the crystal structure. Now, how the amidation work? Okay, so amidation there can be possibility of two ways. This nitrogen can coordinate to the cobalt. Okay, then this carbon dioxide extrusion occurs to get this cobalt carbenoid. This can be the step. At the same time, it can undergo insertion there. So there will be transition state 2 here. So carbon dioxide going away. You can see this carbon dioxide going away and this nitrogen coordinating here. So you get this cobalt 19 bond. Okay, or it has the activation energy around 19.6. At the same time, transition state 3, as shown here, it has activation energy much less, this insertion. Okay, this can be the redetermining step. So as here this cobalt 19 bond undergo the insertion. At the same time, this is actually we cannot compare the energy because we use a different function group because we could not get this energy. Okay, with B3LYP function basic. So here it can be also concerted. We saw that concerted also possible from here to there, but energy we cannot compare because we use a different function. All right, so Subhendu was the student who really worked hard and to establish this in our group. We are now involved there. So now also another, as I mentioned, the amino carbonylation reactions. Here, nitrogen undergo coordination. It can be transition state 5 here. It can be concerted like this, like nitrogen coordination occurs, and this cobalt carbon bond insert to the actually two way it can insert. It can insert to like cobalt nitrogen or cobalt carbonyl, both give the same product, okay, after the tautomerization. So first we thought nitrogen coordination, can it give the product? This is the activation energy as shown here. You can see this cobalt carbon bond insert to this NC bond by N coordination to the cobalt. So it is around 14 kilocalorie per mole. If we check the oxygen coordination, there are two possibilities. It can be like this cobalt side, phenyl can comes, okay, or it can be other way, phenyl goes other way. Both energy as shown here, this case it is 21.8 kilocalorie and this is 14, okay. But still this is much lower energy. So nitrogen coordination and the reaction, this is what we are proposing for our mechanism. All right, this is the whole energy profile. It's quite complex because a huge work has been done from our side. As shown here, energy like two-way, the blue and green. So because the two reactions we are presenting all together, whatever I discuss, all summarized there. And these are the transition state, and these are the intermediate. We also check there each and every product energy. All right. So now I will be discussing the another amidation chemistry, which is really challenging, because if we see about the CH amidation, what we do generally, we take this directing group and we do mostly the mono CH bond functionalization. Okay, sometimes we could do also both sides. Okay, but the problem is how to do iterative CH activation. Like you do take one directing group, you do one CH activation, that help to another one, that help another one, all exhaustive CH activation. That would be really amazing and very challenging. Only report was reported by Professor Chang for this amidation. They could do 4 CH amidation using this as a directing group. There is NMR yield, okay, 99%, okay, not isolated yield. Recently, we are working in this area for last 3 years. So recently, this Lee group, they could also do directed twofold CH amidation. They also published just recently using ruthenium. Both are ruthenium. There's still no report on the first row tangential metal for such reactions. We are interested here. We have like studying, as I mentioned, several substrates. We did not leave anything, whatever available in our lab. As shown here, in roll, we could get the mono amidation, not here. We could not get the chemical science paper, whatever they in under cobalt condition. Also, this ketone, we got the mono one. Thiophene here also, pyrrole only mono. This did not work. This also starting material was decomposed. Also, even this thiophene did not work. This thiophene mono provided this amide. Okay, without going in details, naphthalene also did not work. Indole. Finally, we found it has some steric as well as electronic. Both has to work in concert to provide us this manifold CH amidation, which I will be presenting the code. This only work, and we could do the exhaustive CH amidation. Not only that, we also check several other electrophile which was not successful except this amidation one. As shown here, we could do this one exhaustive. All CH bond was amidated. Okay. But the problem in this chemistry is the scope, how to build up the scope. One way we can think about like this changing these amidating agents, which we did. In this bracket, the yield based on the recovered starting materials, partly this ketone was recovered, this substrate. And here is without considering anything, like this is the yield. Okay. Also, we could have this ortho-substituted, this oxazole, naphthyl, or furyl. We also check the scope of the ketone as shown here. We can have this simple isopropyl, this 64%, this like cyclohexyl, several other quaternary group we can place in adamantane also provided is quite sterical hinder. We could do exhaustive CH amidation. I will not discuss much about a mechanism, which I'll discuss another day. So I have only 3 more or 4 more minutes to complete. So I'll tell the last few slides about our hydroarylation chemistry. So hydroarylation chemistry is one of the first work we started in our lab in when we started like in 2014. So we could do selective like a dihydroarylation or selective monohydroarylation. Also, if we can do the intramolecular function using this tether. So CH hydroarylation under cobalt catalysis, we could get this benzofuranon and benzofuran. Not only that, if you take this product and add another electrophile, okay, in one pot we can get 2 different CH activation like intramolecular hydroarylation, intermolecular, altogether 54% yield, hydroarylation, alkylation, hydroarylation, alylation, or amidation. Without optimization, we could get this product in good yield. So this work was also like we got features in cover article. Like one of my student again, Kundu, is an excellent painter as well. So he helped us to draw this one. You can see he's playing with the C2 alkylation, hydrolysis, at the same time playing with other functional group. This was the concept, and CP star is the cap. Okay, cobalt is here. So this is the person who is doing the job. All right. So as I told in final story, I'll discuss another one which we are going to communicate soon. The functionalization of the pyrene or synthesizing the polyaromatic hydrocarbons is really excellent area, which I am also quite passionate about. The problem is synthesizing such molecule looks very simple or very challenging, particularly isolation also. So if you think about the pyrene, it has a huge application. If you check their application, there is one problem. Most of the time you see they are only connected to this position, the green side. Because if you want to functionalize, it work here, okay, not other places. Like 2 or 4 and 5 are very difficult to functionalize. So we thought, can we develop one method under this hydrolysis condition to get such molecule? What are the reported one? Let us go to literature. If we can put the directing group, because you know this is easy to functionalize here, directing group can be placed here. So the CH activation can be done here, not here. Okay, some of these report which are there. Also, if we check the Itami's work, they use this boronic acid and could get this hydroylation, allylation at this mono or di, but they cannot place the two different. They have to place the same. So I am almost done. But how to get this molecule? Okay, one of the way to get the Diels Holder reaction using dienophile. So someone also check Scott et al. That what will be the activation energy? If you take the phenantine, the activation energy quite high. So Diels Holder reaction to get this pyrene are difficult at this Bay region. This is called the Bay region. This is, however, for this polyaromatic one, it's okay, possible, but not for the phenantine. So we came with a simple solution to this problem, or good simple idea. CH activation, hydrolylation, so alkyne insertion, then it attacked as a nucleophile, and then water elimination and oxidation. We get this pyrene, and all ketone goes, again ketone is our focus. So we get this polyaromatic hydrocarbon with several substitutions. As shown here, you can see the scope. It's work with several one. You can put two similar group, two different group, aromatic, aliphatic, dialiphatic, even both sides can be done. Yields are also good, and we can also have substitution here. Also, this is the mechanism as I mentioned. So it undergoes it is not like cobalt I am not presenting. I am presenting with the rhodium. So this rhodium, we can use it and we can do this hydrolylation. Okay. So and also we can get this quaternary alcohol intermolecular addition. This is actually a rate determining step for these reactions, which also we check in details by DFT studies, which also supported this. So water elimination, okay, here followed by the oxidation, it all work in one pot to get this beautiful pyrene molecule. But this molecule, this is the energy profile. I'll not go in details as shown here. This is the activation energy, like this is that 18. This is the step from like to intermolecular addition. This one, okay, ETS. So this is your activation energy rate determining step. Sorry, activation energy is 23 kilocalorie per mole. This is the highest one. All right, going into details, this is the scope. I really feel happy because getting such axially chiral molecule are always challenging, and how to build a new one. Okay, this is what we thought. If we can do the, let's say you have the binaphthyl, okay, and we can do one apex here, annularity pi extension. So we get this here chiral, okay, axially chiral one. We can have several aliphatic group or aliphatic group, aromatic group. Not only have, we can have the twofold, okay, both sides. We can get 1,1 bis-fire in optically pure form, and reaction can also be done in gram scales, not a problem. We can have several other substitution here, and this example you will also like is the other way. Here it is 1,1. We can also get here. It's a 1,1. Here also 2. Okay, pyrene position. We are also working on the dimerization, which will be like about to get the product. Okay, so we can get several such axially chiral compound for other catalyst design, which we are currently working. All right, so this is the one final slide I want to say, that we've developed method and we want to show its application for the total synthesis, and we have achieved more than 40 and some more. I did not add it here. It will be added soon. Okay, which we have already. So this is the guys. This is who did the job. So Raja, okay, here Shubhendu, okay, he also recently graduated. So our most other students, they have already in postdoc, like Shubhendu is there, and here, okay. So I did not put the alumni here. So, and from this place, like here is Orpita, and also I'm trying, Obisek is there. So both of them did master with Professor Tabraj Khan. So they joined my group recently. And I'd like to thank her and Swarna Jayati Fellowship as well, Inspire, CSR India, IIT Kharagpur for their generous funding. And of course, thank you all for this opportunity and listening to me. Thank you.
Thank you very much. We have time for a couple of questions.
Yeah, fantastic talk, Moza.
Thank you.
I have question regarding the last part. So when you show that activation energy for the Diels-Alder reaction, so these anthracene molecules.
Yes.
So is there actually any report is there that anthracene actually?
No.
Okay. So
Actually,
then these
not our work.
These are computed numbers.
Yeah, computed. See, this is the actually we took this data from this paper. Activation energy calculated for Diels-Alder reaction or acetylene. If you can see the acetylene, okay.
Because anthracene, as we know that 9-10 positions.
Yes, you're right.
Active one.
This is a very challenging position to functionalize for anthracene. Very challenging.
And then final slides when you show those all big polycyclic molecules. So I have a question regarding the solubility. So
they're quite soluble.
They're soluble.
Yeah.
Okay, fantastic.
Because these two guys are helping us to soluble. Because this is not the problem is solubility when they undergo pi stacking. Okay, here they cannot do pi stacking so much. Their soluble means is of course not like normal. We for the NMR purpose 10 mg we can make the soluble. Okay? Like aliphatic one.
Normal solvent like CDCl3.
CDCl3. Okay, but of course not like normal compound 40 mg to be soluble. So 8 to 12 depend on the substrate. Enough for our properties.
Thank you, sir, for the nice presentation. So I have one question regarding that. So if I'm not wrong, the role of silver hexafluoroantimonide is to scavenge the halide from the pre-catalyst to generate the active catalyst.
Yes.
So technically, it should be required in 2:1 ratio with the pre-catalyst. But in one of your projects, you were using 50 mole% of the HESB.
You're right. I just want to say here one limitation with our present infrastructure. So silver, when you open it, immediately catch moisture. It's very tough to control for us. If we do inside the glove box, whatever you mentioned, we could then we have to do all the reaction in glove box. But silver hexafluoroantimonide is not that expensive as well. So for us, we try to add less, but sometimes 10 mole%, 20. You're right. We should be more precise, but you need really anhydrous condition to weight it. Like we are waiting in the common, like here it said we can wait. That's the reason. But you are right.
Yes, thank you.
What a very nice talk. Just one short question. I think in one of the DFT calculations, you mentioned the activation energy is 1.85 kcal per mole.
No,
it looks too small, right?
It's too small. That is not activation energy. The activation for that step. So there are several steps. Yeah. That is not the rate determining step. It's like almost barrier.
Oh, that's a spontaneous.
Okay. Spontaneous. Like there are, let's say 6-7 steps.
Okay. So that is you are calculating individually, and that is one of the steps.
Yes.
Okay.
For that one, 14 kilocalorie is the like rate determining step.
Yeah. Other thing is that you had one of this compound. I'm just curious. Like you said, what is it called? Bay area. And
yes.
Where does this name come from?
Okay, I can say at least one.
L I can
it's
understand.
Like a bay, like an ocean bay.
Okay.
Okay. This is K. Okay.
K I did not understand.
Okay, but L at least you can understand.
L is fine. Yeah.
L is fine. So there are some names which we just adopt, like it's given already.
It's fine.
Yeah.
Thanks.
For polyaromatic hydrocarbon chemistry is quite common.
Thank you.
Thank you.
Have that question later. Yeah.
Okay.
We'll move on to the next speaker. Thank you very much.
Thank you very much.
On behalf of the organizers.
Thank you. Thank you. Thank you, Saskia.
We have another professor student here coming onto the stage.
my dear colleague, Professor Nathaniel from IIT Bhubaneswar, my neighbor as well. Yeah, Nathaniel did masters from IIT Kharagpur and then went on to pursuing PhD under the he held a couple of postdoc stints, one with Professor Melchior in ICIQ Spain. And now I think he moved or he going to move to Italy. Then with Professor Ostrich again, and so Indranil's research interests are in catalysis, especially Lewis acid catalysis and subsequent applications. You are now going to see his work on making and breaking bonds using visible light photoredox catalysis. Indranil?
Yeah. Yeah, thank you, Professor Ramasastri, for this nice introduction. And thank you, Professor. Yeah, thank you, Professor Tabraj Khan, for this kind invitation. It's fine. Yeah, fine. It's no. Okay. So yeah, it is my first time visit to IIT Bhubaneswar. It's a very beautiful and nice campus, and also built at the same time when our IIT Roper built actually. So what I will talk about today is mainly about the photoredox chemistry. Okay, so majorly from the radical pathway. So what we are doing in IIT Roper, so we are doing various kind of catalysis and methodology development. So starting from so starting from Lewis acid catalysis and then also remote CH bond functionalization using transition metal chemistry. We are also doing chemistry with HFIP molecule for nitrosoaring activation, then hydroamination reaction. We are working on visible light mediated reaction using diazo compounds, and also we did few works on asymmetric organocatalysis, and majorly our group is working on photoredox and light mediated reaction and methodology development. So today actually I will talk about this part where we will break carbon sulfur bond and also more challenging carbon fluorine bonds. So radical chemistry, if we go through the history of radical chemistry, so it started on 19th century when the Gomberg and co-workers, they are about to make hexaphenyl ethane compound, okay, highly sterically hindered. And fortunately, they can detect the triphenyl methane radical, which is actually the persistent radical. And from there, actually, you can see it started using lot of metals, single electron transfer process, starting from samarium iodide, mercury, tin. But most of the cases, you can see either you need stoichiometric amount of reagent, or you need some toxic reagent. Okay, so it is around 2000 and I would say 2010 onwards when the photoredox chemistry started to build up and giving an opportunity to work in much milder condition, okay, using the single electron transfer process. And definitely it is very much as an organic chemist what we are doing, mimicking the natural photosynthetic process. So not only the natural photosynthesis, but also you can see that electronically photovoltaic cell. Okay, so as a organic chemists, what we are doing, we are trying to make a bridge between the nature and the technology. Okay. So if we talk about the radical chemistry, particularly chemistry using visible light, there are two majorly principles. So either via electron donor acceptor strategy or by using photoredox chemistry. There is another one is the energy transfer process, and I'm sure next Biplav will talk about the energy transfer process. So this EDA concept, it was previously, before exploring the reactivity, it was mainly handled by the physical organic chemistry part, the chemist. Okay, and there are a lot of studies went also by the Mulliken, who actually got Nobel Prize also. But all of this study, it was majorly about the reactivity, the photophysical property, and until it started to explore using photoredox chemistry by Macmillan. Okay, and recently we know that he got Nobel Prize for asymmetric catalysis, and maybe he will get another Nobel Prize for photoredox chemistry. So similarly, the unlocking the reactivity of EDA concepts for generation of various carbon-carbon or carbon heteroatom bonds actually started to explore by Paolo Melchiore's group. And there is a very simple strategy or basic principle in EDA chemistry that you have an electron donor and electron acceptor. Okay, so donor means you can clearly see these are the electron donors, which are majorly electron rich compound, and acceptor that which are majorly electron poor compound. Okay, so what will happen that when you mix them, okay, so there is a possibility that they will form a charge transfer complex. Okay, but remember, not all the charge transfer complex can lead to the product formation. Okay, so you have an electron donor, electron acceptor. They may be colorless. You mix them, then you irradiate with light. They will go to the excited state and they will transfer electron to do the bond forming process. Okay, and very characteristic of this charge transfer complex, you can see they are generally colored. Okay, starting from light yellow to maybe the bright color. Okay, but again, not necessarily all the color complex or even charge transfer can lead to the bond formation. Okay, but the limitation of EDA concept is that not all the molecules can absorb visible light. Okay, so what will happen if the molecule are not able to absorb visible light? Then you need an external mediator or a photocatalyst which can absorb light, then transfer electron and start the reactivity. Okay, and according to the Macmillan, yes, still lot of reaction, lot of new reactivity is going on. So this field is started to explore. So what is the principle of photoredox chemistry? That you have excitation of electron from the photocatalyst. Upon irradiation, it will go to the excited state SOMO. Okay, and now what can happen? This electron can easily undergo oxidative quenching by transferring from here to an acceptor. So again, acceptor should be an electron poor compound here also. And what can happen here? This low-lying SOMO can absorb or can attract another electron. Okay, and that must be from donor, and it can undergo a reductive quenching. Okay, the advantage is that you can work in much milder condition, room temperature, and can unlock a lot of new reactivity. And not only the photoredox chemistry alone, you can mix photoredox catalysis with transition metal chemistry to unlock various new reactivity. So here actually you can see gist of photoredox catalyst. Generally we use in our laboratory, starting from transition metals based iridium, ruthenium, and also there are a lot of organic photocatalysts starting from dyes and then CZIPN and also many other small organic molecules that can absorb light and do the catalysis. Okay, so I put this picture also to show you that what are the techniques we are using. So here you can see a photoreactor. This is actually from ERF technology from NIT Rourkela. They have a joint prepared this ERF technology based this photoreactor. You have this PEN PhD photoreactor from Mark, and you have a hepatochem photoreactor from USA. And then apart from the photoreactors, you can also use LED lights. Okay, you can buy LED lights from Amazon. Okay, there are ABI light, and there are a lot of blue LED lights from Amazon. And then you can also make it in a house also, or from the market you can buy also different LED lights. So with this, actually, I will start what we are doing currently using this photoredox chemistry. Our main idea was to generate the alkyl radical. Okay, so you can see it is really debatable that which one is a better method to generate alkyl radical. There are a number of precursor for alkyl radical. Okay, so we choose actually this sulfone. The reason is that it is a modular synthons. You can nicely tune the alkyl part and also the sulfone part to modulate various radical precursor. Another advantage, the synthesis is very simple, and also the sulfones are pretty much stable. Okay, you can easily handle. Okay, and you can see these are the sulfone majorly used for the generation of alkyl radicals. And very familiar, no? I think you are familiar with this kind of, particularly these two sulfone, BT sulfone and PT sulfone, used for Julia Kosienski olefination. Okay, so these are the sulfone you can prepare easily, and the idea is to generate alkyl radical. Okay, but still it is not a new process. Okay, the age-old process is a sodium amalgam or using samarium iodide to cleave the carbon sulfur bond, and you can generate alkyl radical. Okay, so not only this, later actually Baron and Cruden recently started to explore using sulfones in a RCC or radical cross coupling reaction using majorly transition metal chemistry. Okay, so what we actually plan in a two different way, either using a photocatalyst which can transfer electron to this. Again, this is an electron poor substrate. Okay, so photocatalyst will transfer electron to generate this radical, or the other approach that could be in presence of a donor, you can form an EDA complex with this electron poor acceptor sulfone and can undergo electron transfer to generate this radical. Okay, and we can choose actually a very popular, well-known, well-established donor is a Manchester. Okay, so these were the two things or two approaches we'll show you for the alkyl radical generation. So the first one we started to explore using this secondary alkyl precursor using iridium photocatalyst and Manchester, okay, as a reductant. And this is the condition. We screened a lot of various sulfone, and we found that sulfone derived from benzothiazole works the best to give the radical, which is this secondary radical, and that could add as a Giese type reaction, as a Michael addition to this Michael acceptor. The reaction without photocatalysis can give 20% yield. I will come back later. No reductant. In dark, there is no reactions. Okay. So with this, we started to explore the mechanistic thing that what is going on, because you have electron rich Manchester, you have electron poor sulfone. So what is the first step? Oxidative quenching or reductive quenching? So we did the fluorescence quenching study, and from this you can easily see that the photocatalyst quench the sulfone. Okay, so the photocatalyst first transfer the electron to the sulfone to generate this radical anion, and then it started to decompose, forming this benzothiazole and this secondary radical. Then this secondary radical add to the Michael acceptor in a Michael addition fashion to generate this alpha keto radical, which can abstract one hydrogen atom from Manchester to form the Giese type product and to generate Hanch pyridine derivative. Okay. Yes, definitely many of you can say that this is not a good process in terms of atom economy. I agree with this, but our major goal was to check the reactivity of primary radical that are not so much reactive. Okay, so we started to explore, and you can see the second tertiary radical, and these are the different acceptor which works pretty well. And as I told you, it is a modular synthons. You can see that you can vary and synthesize various radical. Even you can incorporate difluoro containing methylene groups. Okay. So this reaction also works pretty well with secondary radical, and you can see now we are able to use primary radical, unreactive or less, rather less reactive primary radical. Okay, the yields and reactivity, I would say moderate compared to secondary or tertiary radical. So you can do intramolecular Giese reaction for the synthesis of this spirocyclic molecule. So we applied again this scope, the radical generation for the allylation reaction using this allyl sulfone. And here I must say the reactivity of the primary radical is much more higher compared to the previous reactivity. Okay, and you can use secondary, primary, lot of different radical precursor. Also, you can generate secondary radical from lithocholic acid derivative. Okay. So one thing you must notice that this reaction, when we started to optimize, we had some background reaction. That's mean the reaction also worked, give 20% yield, okay, without photocatalyst. So what is going on? Whether it is a EDA or something else. Okay, so that's mean we can start to screen or optimize the reaction condition without using any photocatalyst. Okay, so we target actually based on our observation, we target to synthesize dibenzyl compound. Okay, particularly unsymmetrical, and you know that it looks like very simple compound, but without transition metal, it is very difficult to synthesize. Either you need cross-coupling reaction or you need to do hydrogenation after the olefination. Okay, so what actually we planned that whether it is a EDA or any influence from the Manchester, we can use one radical from here and one radical from here, and then to couple two radical in a cross dehydrogenative fashion. Okay, so this was the target, but you see that what are the possible product? Naturally, all the radicals can couple with each other. So two homocoupling product and one cross coupling. So let's see how we can improve the yield using different conditions. So we started to screen using this one as excess because this is the we found that most reactive radical species among the sulfone and the Hanchester. Okay, so we don't need any photocatalyst using sodium acetate and ethanol at 365 nanometer. Okay, we are able to get up to 90%. There is side product. Please remember, there is side product of cross coupling from this radical. Okay, but we can get our desert cross couple product up to 90% yield. Okay, so what we did immediately, whether it is a EDA or something else, we studied the UV visible. And from UV visible, you can see there is no EDA formation. Okay, so what is going on? You see the absorption of the Hanchester. Okay, so it is around 365 nanometer. Okay, and that is why what happened that Hanchester itself absorbed the light, it goes to the excited state, and then in excited state, it is a very strong reductant and started to do electron transfer process. Okay, so this is the thing. You form the radical cation from Hanchester and radical anion from sulfone. Now from here, you have two pathways. Either this radical from Hanchester, it's came out of the cage, okay, and the sulfone radical precursor is here, it can catch the radical. So if this will happen, the probability of homocoupling of the radical from sulfone will be less. But there is the probability of homocoupling, the radical generated from Hanchester. And obviously we took it as an excess, okay. And there is another possibility that the two radical species can be out of the cage and then couple. And then there is a possibility of homocoupling of each of the radical. But we think actually maybe this is the pathway the radical is following so that we are getting high reactivity. Okay. So this reaction is undergoing in our laboratory. We are able to couple 3 degree to secondary radicals. We can couple a lot of radicals generating from not only the benzylic system, also from heteroaromatic system. And also we are able to couple primary radical. But throughout this list, you can see that what is missing, that the less reactive radicals. Okay, so only the reactive radical, the benzylic, either primary, secondary, or tertiary radicals are reactive enough. Okay, we are unable to find reactivity from the primary radicals. Okay, so as a whole, you can see that you can cleave the carbon sulfur bond and use this sulfone as a precursor in combination with lights and also with photocatalyst for the synthesis of various radical precursor. Okay, still this carbon sulfur bond breaking, I think it is not so much challenging. Okay, but what is more challenging is the breaking of carbon fluorine bonds. It's a very strong bond. Okay, and last couple of years, our group we have lot of interest for the synthesis of fluorinated molecules. Okay, and definitely you know that whether it is pharmaceutical or agrochemicals, you can find a lot of molecules having fluorine atoms. Okay, but you can find molecules with monofluorinated, difluorinated, CF3 or perfluorinated molecules. Okay, but what we interested majorly difluorinated molecule. Okay, so please remember not always the CF3 molecules is very much interesting, but also CF2 is very much interesting. Okay, and if you can replace CF3 with alkyl groups to convert it to CF2, it can change a lot of properties of the molecule. It can change the polarizability, the pK, and also various stability and also the metabolism of the molecule. So you can see there are a lot of drugs from aryl CF2 molecules that actually can be generated from benzo trifluoride system, and also there are a lot of drugs containing this difluoromethyl ketone derivatives that actually you can target from this precursor. Okay. And definitely you know that's another important part of the CF2 molecule. It is called the bioisosters of methoxy group. Okay. That is majorly called the point mutation. Okay. And you can see here two drug molecules. Here, when R is methoxy, you can see the IC50 value is 104, and this is the, when you replace this OMe with the CF2 group, the drugs got high metabolic stability and IC50 value also decrease. Okay, and that is why the introduction of CF2 group into the molecule is so much importance. Okay. So how you can introduce CF2 group? So either you have a neutral molecule, you add fluorine atoms. Okay. Or what you can do, you have CF3, you cut or break fluorine atoms. Okay. So we choose actually this part using photoredox catalyst. Okay. And between this benzotrifluoride and trifluoromethyl ketones, we choose actually trifluoromethyl ketones. The reason is that, first reason, academic purpose, that this is well explored, not the trifluoromethyl ketone. But what is actually the reason behind that, the reduction potential because of this carbonyl group is little bit lower. Okay, so much easier to transfer the single electrons. Okay, and another reason is that if you have, or if you can retain the carbonyl functionality, you can use for very simple transformation of your ketones for the late stage functionalization. Okay, but you know that it is not an easy task. Okay, CF bond is one of the strongest bond. Okay, very difficult to make, very difficult to cleave. The other challenge is that how to control the mono defluorination. Okay, because there is a possibility of exhaustive defluorination. Okay, so how we can control this? So we started, and you can see that it is exactly happened whatever happened for Professor Ramasastry, that during COVID times, almost 7-8 months, we tried. You see that we are getting the product, but is exhaustive defluorination. Okay, we tried to modulate a lot of reaction condition, the temperature. We can get defluorinated product, but still we are away from our goal. Okay, so yeah, exactly this molecule, and it is happened like what happened to your case also, that it was the last solvent we need to try. Okay, and another thing, so not only give up, okay, but also you have to believe in yourself, that you see the TLC. Okay, it looks like it is a common TLC solvent, ethyl acetate hexane, right? We use this common solvent for TLC. You see, it looks like no reaction, right? So either you never throw out your crude mixture until you check by NMR. Okay, and what we realize that if you run the TLC in dichloromethane after 2 times, you see full conversion. Okay, and this was the starting point when we realized that we are actually able to do the mono defluorination process. Okay, so we started to explore the reactivity and various optimization, and you see that using iridium photocatalyst, we are getting more than 80% yield. Without photocatalyst, no reaction, and without light, no reaction. Okay, so we explore the reactivity to a much reactive system. I would say much reactive acrylamide. So again, it's a Michael type addition followed by cyclization, aromatization. Okay, so you see the chemoselectivity now. The benzotrifluoride remain untouched. Only the fluorine from the ketones are defluorinated. Okay, so we can also do the reaction not only using aromatic ketones, but also using aliphatic ketones. Okay, but what is much more interesting that I mentioned before that, how we can use the simple reactivity of carbonyl compound for late stage functionalization. So you see that what you can do debenzolation using potassium tertiary butoxide in butanol. Okay, you can do simple lithium aluminum hydride reduction to form this difluorinated pyranoindole moiety. Okay, you can do reduction to alcohol, then dust-mediated fluorination to generate trifluoroethylene bridge. Okay, so you can cut fluorine from one atom and then add fluorine to another atoms. Okay, so this is the advantages of this methodology. So previously, as I mentioned, that you can see that this is much more reactive acrylamide system. Okay, now the question is, what will happen to olefin system? Can we able to add the same way what we did for this? And again, you see, we are getting 3 products. Okay, but we ask ourselves, can we generate different reaction condition to have a divergent access of all this product? Okay, so we started to optimize, and you see that using this iridium photocatalyst, we are able to get in HFIP selectively this tetrahydrofuran moiety having these acetals. Okay, and using ruthenium in trifluoroethanol, we are able to get this one as a major product. Okay, now the question is why we are interested. You see this molecule. Okay, yeah, we are not able to make this molecule, but the motivation is that this gemcitabine, it is a blockbuster anti-cancer drug. Okay, having this tetrahydrofuran part and this aminal linkage. Okay, the traditional way to synthesize this difluorinated tetrahydrofuran moiety, it's a long step process. Okay, so we thought that it may be a very good addition to a new classes of difluorinated molecules. So we are able to generate this reactivity, utilize for lot of olefinic system, and you see that the reaction also gave very impressive diastereoselectivity. Okay, you can utilize not only this cyclic olefins, also this endocyclic double bond, and you see the reactivity of this exocyclic double bond is much higher compared to the endocyclic double bond. So not only chemoselectivity, but also the diastereoselectivity remains high. We can also vary various ketones derived from this aryl trifluoromethyl ketone derivative. And when we use our second condition using ruthenium and trifluoroethanol as a solvent, you see that we are able to get this linear difluoroketone moiety. Okay, but I must say that this reaction is limited to 1,1-diaryl olefinic system. Okay, so what we are able to do, not only the HFIP acetal, you can replace or use a solvent mixture of more nucleophilic alcohol like ethanol or even water, okay, to have this various acetal part. We can cleave actually very easily this acetal to end up this beta gamma unsaturated difluoroketone derivative using TMS triplet. And interestingly, you can see we can start with this difluoroketone derivative, this linear part, linear molecule. We can do a dust-mediated cyclization to end up with another new classes of mono or difluorinated molecules. Okay, so what else? We took actually this naproxen drug, we convert this acid to ester, and then we activate these ketones. Okay, and we are able to get or modified this naproxen drug using our methodology. Okay. So what is the mechanism? What we did actually, we did fluorescence quenching as usual, and we found that only the ketone is quenching the photocatalyst. So that's mean photocatalyst first transfer electron to ketone, okay, to reduce this ketone. And the question is, what is the role of HFIP? So you see, this is the CV plot, the redox potential in acetonitrile, and you see this is in HFIP. So what is happening? You have your carbonyls. HFIP can form hydrogen bonding with the carbonyl so that its LUMO will be lowered and it will facile the single electron transfer. Very similar what does by Lewis acids. Okay. Another thing HFIP is doing that it can activate the CF bond via hydrogen bonding. So CF bond also became weaker. But what is unknown to us that how it controls the monodeformation. Maybe somehow it is able to stabilize this radical. Okay. So first, what is happening? The iridium transfer electrons to the ketones and you generate this radical anion. From this radical anion, you have this radical. Okay, so this process is called spin center shift. Okay, so you have ketones. So when you pump electron, you will form ketyl radical, right? And what is spin center shift? The center shift from one carbon atom to another carbon atom by expulsion of a leaving group. Okay, and you generate this CF2 radical. This radical add to this acrylamide, followed by cyclization, and then another single electron transfer to get finally the aromaticity after deprotonation. Okay, and what will happen here? It will add to the olefin system to generate this radical, single electron transfer, this carbocation, then intramolecular cyclization immediately, okay, which is very much facile entropically, and you will generate this oxonium ion, okay, which is immediately trapped by HFIP. Okay, and what is happening here in TFE, that this radical can have two pathways. Either it can undergo disproportionation. Okay, so if you have this radical, you will get two products after disproportionation. Okay, or what can happen? We are using Hanchester, which is a very good hydrogen atom transfer reagent. Okay, it can transfer hydrogen atom and you will get this linear ketone. Okay, so to conclude, you will see that a nice combination or friendship of HFIP and light can give you even very challenging CF bond activation. Okay, and you can generate lot of CF2 containing molecules for the drug discovery even. Okay, and you have a lot of collection of new kind of diverse molecular scaffold. So with this, actually, I like to end my today's talk. So this is IIT Ropar. So it is in Punjab. So 45 minutes from Chandigarh. And you see a very beautiful campus. You can see the Shivalik also in a clear day. Okay, and also very green campus. We have in Ropar city, we have the Harappan civilization. And so this is the entry gate of IIT Ropar, where we have either chemistry or physics, the Cuban structure, and also very nice sculpture of Harappan civilization. Okay, so I welcome all of you. Whenever you want, please write to me and you can visit IIT Ropar. Okay, so I'm thankful to my group. So mainly the CF bond activation, whatever I represent from Somen, Suman, and Saurabh, and the sulfone is majorly done majorly done by Sandeep. Okay, and he's a really skillful chemist because you see the product, whether it's a homocoupling, heterocoupling, they are very close RF value. Okay, non-polar, very close RF value. So you need a very good hand to separate via column chromatography. Okay, so I'm thankful to the funding agency and also my collaborator, because last two works on CF bond activation, we have also DFT calculation to support the mechanism proposed by us, and it is mainly from Grimme and Zhengwang. So again, thankful to Professor Khan for this kind invitation, and thanks to all of you for your kind attention.
Excellent talk, Indranil, and many nice results. So I just like, as you mentioned, like it stop at di means only mono defluorination. So like, is it not that your like LUMO energy still means comes down in such a way that it doesn't react further? Means not down, up.
There can be two things, either electronically or whenever. The major thing is that the exhaustive defluorination can happen two ways. Either you have your ketones mono defluorinated, you generate CF2. CF2 immediately react. When it reacts with acrylamide, you see the product, it's stellically hindered. Then the electron transfer will be difficult. There can be another possibility that you start with the CF3, you cleave one by one fluorine, you generate CH2 radical. Okay, so I don't think it is happening there. So it is the CF2 radical, and when the radical add to the acrylamide, you see the product, it is sterically hindered.
I just like want to add here, if you measure cyclic voltammetry of CF2H, like ketone, that can give you some idea, right, about its nature of redox potential, whatever.
Bolmer of the product, whether it is quenching the photocatalyst or not.
Okay, product. Yeah. We did also what we did. We took the product. We use our reaction condition. We got only 10% of further defluorinated product. So that's mean the single
product
electron
is quenching or not quenching anymore.
Yeah, the quenching experiment, I don't think we did. Yeah, we took the defluorinated product. We use our reaction condition, and what we observed that the further defluorination, it's only 10% yield we observe.
And maybe another point to add. So if you check the CV, so that potential might have been gone beyond the photocatalyst. It could be a chance that.
Yeah,
instead
that
of
could be
fluorine,
chance.
if you have alkyl, so
but majorly, I think, yeah, that is definitely.
sterics cannot be a reason. Sorry.
Okay, yeah, might be, yeah. But generally, for this acrylamide system, it's sterically hindered system. Although the carbonyl part is little bit away. Yeah. Yeah. It's not able to do the electron transfer further. Yeah.
Of that fluoride that's leaving.
Yeah, the fluoride actually we use B2P2 as a fluoride scavenger. So for the reaction with acrylamide, what we observe from 19F NMR and also 11 boron NMR, the formation of BF bond. But surprisingly, we did not observe any boron fluorine bonds during the acetal project. Okay. So what do you observe? We observe at minus 129 ppm the fluorides, but we don't know how this fluoride is attaching. Okay, but it can be a fluoride, but maybe aqueous fluoride or something else. Yeah.
Yeah, Indradil, very nice presentation. Like I'm attending like MSc class actually. Very clear. Yes. Yes. So one thing I want to ask, because you are using mostly iridium-based catalyst actually. So that will be in when you apply to a industrial scale, it will be expensive. It is very good of academic interest, of course. So do you have any alternative catalyst? Which
Yes, for CZIPN, the organic photocatalyst is also working.
Second thing, the 62 number slide, if you can go, the 62. Go back a little bit, it's not very far away. Yeah, this spin shifting, how to prove it conceptually? There are things like, is there a way to prove this thing?
Yeah, conceptually. Yeah, I don't know how to prove conceptually.
I think it is written there. I have seen in some of the this. Even we are also proposing something similar. So because yes, Madhu, you can go ahead.
So what I want to say, like, once it takes single electron, it can be C minus, C dot, O minus, or it can be reverse. O dot, C minus.
Yes.
That can F minus goes there.
Yeah, that is the way. That is the reason for spin. It is called spin center, but it is between the radical anion or anion radical and then enolate.
Yeah.
It will kick
To
off.
center 3 electron bond, that's we use. Right?
Yeah. Yes. It is also like this. Yeah.
Very nice presentation, sir. Sir, I am having one doubt. You, in your first some couple of slides, you talked about this EDA complex. So is it the minimum criteria that in UV it should be longer wavelength? Yeah, it just another shift.
Yeah, you should see actually a charge transfer complex. So you have individual spectra, and when you mix, okay, so maybe if you have additive in your reaction mixer, maybe you need the additive also or any other factor. But when you mix the component, you should observe another charge transfer band, mainly towards higher wavelength, and that is why you generate a color. Generally redshift. Okay.
Characterization we can do for this EDA.
Yeah, then when you observe EDA, then you can do you can measure Jobs plot. Okay, to check the stoichiometry, the ratio, the donor acceptor is forming the EDA.
Thank you.
Nice business, sir. I have doubt. Are using alkene with active with atom group? So did you use unactivated alkenes like styrene or aliphatic?
Yeah. Unactivated alkene is not working. Yeah, you mean simple alkene?
Yes.
No.
Yes.
No, it is not working till now. Yeah.
What the reason begins? So
the reason maybe you see the intermediate is the carbocation. So that is why you need at least one phenyl group or even 2 cyclohexyl or which can stabilize the carbocation. So that might be the reason that the simple olefin or monosubstituted olefin is not working.
You have generated radical from the Hens ester, and you have coupled with the radical that you generate from the the sulfone, which is linked to the thiazole ring, if I'm not wrong. So the Hens ester I see which you used typically contained the was a source of secondary radical, if I'm not wrong. So have you tried primary radical?
Yes, we are doing now, but again it is a benzylic radical. We are not able to get reactivity from simple unactivated secondary or even primary radicals. So we need benzylic system.
So please correct me if I'm wrong. Okay, you're saying that primary and secondary are unreactive radical.
No, primary benzylic radical.
Primary benzylic radical.
Yeah. Primary radical is reactive, secondary is reactive, but for the benzylic system, but not the unactivated system. The classical CH2. No?
Radical.
Yeah.
In continuation to that, the last question, you generated, especially that Manchester when you took, you generated actually two radicals.
Yeah.
In principle, at least three products can be possible.
Should be.
Not
Yeah.
more.
We observe only two products. The desired product and the product from the homocoupling of the Manchester. But very rarely, only when the electronics are much different, then we observe the homocoupling from the sulfone. When the Manchester radical is not reactive enough. Yeah.
Didn't see any eliminations. Elimination reactions.
Elimination or hydrogen atom transfer?
Eliminations involving radical intermediates.
Elimination means
when you have a radical, you proton next the hydrogen can eliminate and give you a double bond.
Okay. Exocycling. No. We did not observe. Yeah, we did not observe. No. Yeah.
Let's thank him for his presentation. The organizers. A wonderful presentation.
Thank you.
I would like to request Professor for chairing this session.
I believe we have gathered great insights from the lectures of Professor M.S. Maji and Professor Chatterjee. I wish to extend my gratitude to them and to you for your zealous participation. I'm sure we all are looking forward to the lunch so we can stimulate ourselves to gain more from the upcoming session. So I now cordially invite you to join us for the lunch at Community Center ground. Please join us for the photograph session before the lunch. Yeah, thank you. I kindly request all the participants to gather around. We are going to start this session in 5 minutes. I once again warmly welcome you all. I request all the participants to kindly be seated so we can proceed further with the next session of the workshop. I hope we are all re-energized after that delicious lunch. Let us resume session 3 of day 2. It is my immense pleasure to inform you that the session chair for this session will be our honorable guest, Professor Mukherjee from IIT Bangalore. I humbly request Professor Mukherjee to commence the proceeding of this session. Thank you, sir.
Good afternoon, everyone. Welcome back to the third session of the day. In this session, we have two very exciting talks from two of the, the future of organic chemistry in India. So the first speaker is Dr. Biplab Majhi from IISER Kolkata. So Biplab, just to give you a brief biography of Biplab, Biplab did his master's from IIT Kanpur. So that's the common thing we share. And then he completed his PhD in 2012 from one of the giants in physical organic chemistry, Herbert Meyer, from LMU Munich. And then he went on to do two postdocs. The first one with legendary Professor Hisashi Yamamoto, the master of Lewis acid catalysis, and the second one with Professor Frank Glorious, who is master of everything, in from Münster. And in 2016, Biplab joined IISER Kolkata as an assistant professor. And last year, he became associate professor. So he has been working in the area of so-called sustainable chemistry and catalysis, including photocatalysis. And today he will talk about proximity and interlocking in photoredox nickel dual catalysis. So I welcome Biplab to the stage, and then I request him to present in about 40 to 45 minutes.
Hey, good afternoon. Am I audible? Lunch acha tha? Okay, so now it is my job to keep you awake for next 40 minutes, and I'll try very hard, okay? Thank you. Okay, thank you, Dr. Mukherjee, for this kind introduction. And I also wanted to thank Dr. Khan, so for this invitation. And I'm having amazing time here, actually, last 1.5 days now. So it's beautiful campus, nice weather, nice food. So in this talk, I would like to discuss some of the chemistry, what we are doing is recently. And I'll start with this slide. So what I called simple to complex paradigm. So as a synthetic chemist, and I think everybody will appreciate that we want everything to start with simple, and we wanted to make everything complex. And in doing so, we would like to consider all the buzzwords: economics, sustainability, green chemistry, less waste, circular chemistry. So Professor Mehta gave the introduction yesterday, right, in the morning, and he has the stage for all this, right? So all of us agree, right? So you want everything from simple to complex, right? Now, in our group, so we use tungsten metal catalysis. So in addressing that, and we particularly choose these kind of tungsten metals. And the reason is very simple, because those are 3D metals. By doing catalysis with them,
things can be more greener and sustainable and so on. Now, in thermal condition, when you are doing this reaction in thermally, so we have two handles, okay? Now, one of the handle that we need to design the ligands. Now, we need to design the ligands in a simple way that we wanted to facilitate the oxidative addition, for example, or the reductive elimination, or hydrogenation, dehydrogenation. These are the very basic organometallic steps, right? Otherwise, we can use redox manipulation. So you pump in electrons to make the low valent metal complex. There you can have the faster oxidative addition, for example. You reduce the metals to go to the high valent metal complex to facilitate the reductive elimination. But this electron pump, so these are usually are stoichiometric. So we are talking about stoichiometric addition of an oxidant or a reductant, right? Now, when you add something stoichiometric, which is not part of the molecule, part of the target, so then from there, the redox reagent, so unavoidably you will produce a byproduct, right? So it can either be reduced byproduct or can be oxidized byproduct. And the byproducts is byproducts, how green they are, right? Because these are not part of the molecule. Yes or no? Okay, so that we all agree. Now, another way of doing that, so you use light as the trigger. So instead of heating things, so you can use light as a trigger. Now, what are the advantage of using light? So when we do heat a reaction, so we heat the oil bath and we heat all the solvent molecules. Now, the solvent molecules are not product, but that much heat energy we waste, yes or no? Now, let's say we need a 50 kcal activation energy. We heat all of those, okay? Now, instead of heating all of them, why don't we use light, okay? Light in the visible range. So this number I get from Wikipedia. So you see that in the visible range of the light, that have exactly the amount of energy that we typically require to cross a activation barrier, right? So it will be very easy, right? So we don't need to heat, we need to shine light and excite the molecule, cross the activation barrier, get the product, right? Now the problem here that when we do organic chemistry, most of the organic molecules, they don't absorb. Yes or no? So if they don't absorb, even though we shine light, so there is no effect on them, right? If they don't absorb, there is no excitation, no reaction, right? Now I would like to thank Indranil. So he has introduced this photochemistry just before lunch. I think we still remember some of those, right? So to facilitate this problem, so we need to use a sensitizer, okay? So we call photocatalyst. So photocatalyst is nothing but a molecule, so will do the light absorption, okay, for us, for doing the chemical reaction. Now, one of the photocatalysts, so I'm showing here, is a very big molecule of iridium complex, very expensive. Now, in this molecule, the good thing, it absorbs, okay, it absorbs around 400 nanometers, so the visible range. Now it absorbs, it goes to the excited state, cross the intersystem, and it gives a stable triplet state. Now, stable enough that we can have a bimolecular reaction, right? We need to have a bimolecular reaction. Photocatalyst excited, it has to be stable to transfer the information of light to another molecule, okay? Now this information, the productive information, so it can be either the energy that it gains by the excitation, by the light, or can be electrons, right? Okay, now I first will talk about the energy transfer, okay? Now this molecule excite in a triplet state, now it gets this surplus energy, okay, from the visible light. Now this energy, it can transfer to another molecule and comes to a ground state, okay? Now this process is called triplet energy transfer because that molecule, this is a triplet state. Now from triplet state, it comes to a singlet state and it transfers the energy, okay? Now one of this energy transfer, what we have found that if you take a naphthalene molecule to acyl naphthalene, it goes to the triplet state, okay? And it comes back to the ground state, okay? Now this triplet state, what Pramod found that if you take a styrene molecule, now that triplet state one can trap. Okay, typical reaction of a diradical with a styrene, you can have a stepwise reaction. So first interaction, one carbon-carbon bond formation, then you have a triplet state, then you should have an intersystem crossing and a bond formation. Okay, now we are excited about this reaction because now you see the starting material. So you have an aromatic flat molecule, 2-dimension, right? Now from this aromatic flat molecule, you convert that to a 3-dimension molecule. So from 2D to 3D, right? So I can show it in this axis, okay? So this is one good thing. Now, because many of the drugs, natural products, they are having 3D architecture. Flat molecules are also good, but the flat molecules are abundant. For example, here this naphthalene, these are largely abundant molecule, mostly from the coal, okay? In the coal industry, they produce approximately 10% the tar. So there you have this naphthalene molecule. Now, another thing is that, now you see that in this reaction, we form these 2 carbon-carbon single red bond, okay? Now, these 2 new sigma bond, it actually do not compensate the aromatic energy, so that we need to break, okay? Now here, this process is actually an exothermic reaction. So we are doing a exothermic reaction, okay? Now, by crossing this barrier, okay? Now, if you think that we need to do this reaction in thermal condition, it is highly improbable because you need to supply this thermal energy that will be enough to drive the backward reaction, okay? So thermally is very, very challenging to do this reaction. Now, another challenge, what I showed here, so we said that we do this 4+2, okay? Now this naphthalene molecule, it can go undergo a this position, 1 position and 3 position. So this is meta, okay? 2+3. It can have 1 and 2, 2+2, okay? 2 possibles. Now believe me or not, this meta reaction, 3+2 reactions is actually symmetry allowed. So if you do a direct signing of the reaction, you actually get this meta product, okay? Now, if you look into literature, you type in Google that arene alkene cycloaddition, there will be plenty of review will appear. And if you open the review, that all this chapter after chapter, you will see that all are this meta cycloaddition reaction, okay? Because those earlier days, so those reactions are done in presence of UV light, and then from there, so you get this meta selective product. Now, we solve one of these 2 challenges, we get this para, okay? Now, other challenge is that you can have an exo or endo. So typical like in Diels-Alder scenario. Now, we said that bond formation is sequential, like one after another. So there is no secondary orbital effect. So we don't have inherent endo selectivity. So that's the challenge, right? Now, third problem is that when you have a group, now this group and that group, so they can be far or they can be close, right? This is another challenge. So we have to get the positional selectivity as well, okay? Now, because of that, so there is only one report with the naphthalene system, and that too, that intramolecular reaction. Now, when you are doing an intramolecular reaction, so the reaction, the selectivity, everything is controlled by the tether you have, right? And the position. So this is predefined. In our case, it is not, okay? Now, if I go a little bit more depth, now this is the UV spectrum of this molecule and the red one of that molecule. If we mix, there is no charge transfer, so we don't see any change. Now, this molecule, so we wanted to do this reaction visible light. So it has a very, very small excitation coefficient at 370 nanometer. So if we excite at 370, we get little product, okay? So that proves that direct excitation is possible, and probably because we have this n-pi star transition of this carbonyl compound. Then from there, you can have the pi star. Now, to do this reaction efficiently via visible light, so you need to have the energy transfer, okay? Triplet transfer. Now, for that, we need to use a photocatalyst, and we screened several photosensitizers. So one of them is xanthone, is like a benzophenone. We get slightly higher yield. Now the better photosensitizer we come across with this iridium complex, that one I have shown. Okay. Now in this case, we get very good yield. Now exclusively this product, but we cannot control the endo versus exo selectivity. Okay, this is the drawback. Now here you see that these yields here, they actually do not correlate nicely with the triplet energy. Okay, so usually like it should be higher triplet energy to have better energy transfer, right? Now what we have found that they correlate better with respect to how they quench the luminescence of this photocatalyst. Okay, so the Stern-Volmer constant. So the better they quench, the better the yields they are given. Okay, but there is no rule as such as of I know, but this is whatever we have found. So then this triplet energy transfer actually beyond our knowledge at this point that how this is working. Okay, now we did another experiment. So to prove that this is actually a triplet energy transfer reaction, not the electron transfer. So we measured the CV, and as you can see, both the oxidation and the reduction actually fall outside the window of the photocatalyst. So there is no electron transfer. We also did NMR experiment to prove that this reaction is happening actually 1-to-1. So, and what we have found, this is the decay of the starting material and this is the increase of the product. So they are about the same rate. Okay, so then we do not have a intermediate, at least in the NMR time scale, whatever we have found. Now the scope is very broad. So we can have any styrenes, okay, but not simple alkene. Okay, styrene molecules are okay, not simple alkenes. And we can have any of these ketones. Okay, so any groups, ketones and esters. Okay, but we need to have these two positions, either ketone or ester. Other molecules so far is the drawback for this method. And we can do many more. We can functionalize this molecule, reduce it, add a thiol, do the cyclopropanation or the epoxidation reaction. Okay, so this is one story with the energy transfer. Now, other story could be that this molecule in the excited state, triplet, now this is can participate in electron transfer. Okay, so it can either accept the electron or it can give the electron. Now, what the example I saw is where it accepts the electrons. Okay, now if you add triethylamine or any amine, now you'll see that this luminescence quench. Okay, so there you have an electron transfer from amine base to the photocatalyst. Now this photocatalyst is iridium 2, okay, strongly reducing. The potential is minus 1.37 volt. Okay, so then we have a control to have this electron as per your will. When you shine the light, how much photocatalyst you will use and how much the amine you will use. Okay, now what we have found that using this electron we can reduce a cobalt 2 to cobalt 1, and using that we can do a coupling reaction between an alkene and alkyne. Okay, so E9 coupling to produce a tri-substituted olefin compounds. Okay, now this reaction we have started very early in 2019. We have published. Now this reaction is very good. You have an alkene and alkyne. You form this tri-substituted double bond, and this is the mechanism of this. Okay, so not so important at this moment, the mechanism. Now the beauty of this system is that, so as I said, that this electron donor, now we use Hanchester as the electron donor as our will, and it selectively give the reducing equivalent. Okay, so in a way that we can perform this reaction in the presence of reductant sensitive functional groups. Okay, and that we have demonstrated. So we can have all this reduction sensitive functional group, including this alkene that stays, ester stays, nitrile, fluoride, chloride, bromide, CF3, even iodide, terminal olefin, all are retained. Okay, which is otherwise very difficult to do if you have to use stoichiometric reducing agent. Now, when we perform the same reaction now this alkene and alkyne, they are tethered, okay? So if they couple with each other, so we'll form a cyclic molecule with a terminal double bond, exocyclic double bond. This reaction we can couple with a CH bond activation, okay, of acetophenone. Professor Maji this morning told cobalt catalyzed CH bond activation, right? So here we can do a two reaction in one pot. Now we produce this cyclic molecule with exocyclic double bond and a stereo center. Now this stereo center we can control by using a chiral ligand. So we have tried many chiral ligands, okay? So this slide is actually, you see the first publication we have 2019. And the second publication we have in 2022, okay? So it takes 3 years actually to publish this work and actually to get this much enhanced selectivity. We have tried many, okay? Many means we have tried many of these ligands, okay? Whatever we can afford to buy, okay? Now, this reaction is not only problematic with respect to the enhanced selectivity, it also problematic with respect to the selectivity of that double bond. Now, this photocatalyst not only transfer the electron, the photocatalyst doesn't know, right? It can transfer the electron, it can transfer the energy as well, as I said. Now, this energy transfer here it is actually occurs because it will actually isomerize the double bond, right? Typical styrene isomerization via energy transfer. Now, what we have found, if we use these photocatalysts now, which having this much triplet energy, so now this isomerization we can stop. Okay, that's the good news, but the selectivity is very difficult to achieve, and we achieve up to this much. Okay, now this is the story of this cobalt. Now we'll come back to the story of nickel. So by this 3 years journey, we actually failed many, but we learned many about this photochemical reaction, photoredox catalysis, okay? Now here, we actually do the same chemistry, convert nickel 2 to nickel 1, okay? By using this hot electron. And what we have performed here, this reaction having two aliphatic alkyl group to convert to a cyclopropane molecule, okay? Now these cyclopropanes are very, very fascinating molecules. People use this cyclopropane to test whether you have a radical reaction or not, because this cyclopropane, they undergo very fast ring opening. Now we wanted to make this cyclopropane by using photocatalysis, and this reaction also involved radicals, okay? And I will not argue that our method is better than all this reaction reported here, okay? Simon-Smith reaction, Corey-Chekhovsky reaction, and so on. But there are attempts being made to make cyclopropane from this 1,3-dielectrophile, okay? So this is a typical intramolecular Woods coupling reaction. Okay, now this reaction, when you use stoichiometric zinc as a reductant, this reaction failed in this recent report. Now Jarvo actually cleverly used methyl magnesium iodide as a reducing equivalent, okay? So where she will eliminate a ethane molecule as a byproduct, and that will be the reducting equivalent, okay? And she could do this reaction perfectly. Now the problem here that you need to use methyl magnesium bromide 2 equivalent as a reducing agent. Now when you use methyl magnesium iodide 2 equivalent as a reducing agent, so then you cannot use any functional groups which are Grignard sensitive. Yes or no? We cannot have any Grignard sensitive functional groups. Now we take up this challenge and we perform this reaction, this halide, to make this cyclopropane, okay? Now this reaction worked with this photocatalyst, triethylamine as the electron donor, and nickel bromide with ditertiary bipyridine as a ligand. Now this reaction worked well. So unless you have this photocatalyst more reducing than this, the reaction is compatible. It gives high yield, close to 80 plus minus something, but this works best. We need continuous irradiation. We need this wavelength, particularly 456. If you change different wavelength, the reaction fails, okay? We do not know why. Now, we can have different ligands, but this bipyridine is best. No ligand, no product, and you need to have also continuous irradiation. You have to shine light all the time. Okay. Now this reaction works by this method. So here you reduce this nickel to nickel lower valent nickel species. Now this nickel, instead of having a single step oxidative addition, it goes via a radical mechanism. Okay. So it first transfer a single electron from a alkyl radical which is in the close proximity, and then this alkyl radical is being captured. Okay. And we have probed this by a radical clock mechanism and also different radical trap. And we have probed that this is actually happening not a single step oxidative addition by a stepwise process. Now, once you have that, there will be another cycle of this reduction to have this nickel species, and that undergo intramolecular SN2 type reaction to give this product. Okay. Now, this reaction works beautifully, and I wanted to highlight these functional groups. So that definitely not possible when you have methyl magnesium iodide. Yes or no? Okay. Now, same principle we applied for difunctionalization of this alkene. So here you have this directing group. Now, in this reaction, this aryl group attach at the terminal position, and this alkyl group attach at the internal position selectively. And there also you can see that functional groups, so lot of functional groups that is not possible with the stoichiometric metal as a reductant or Grignard as a reducing agent. Now in this reaction, so we have to introduce another concept, okay? Another concept, that is halogen atom transfer. So as I said last slide, so if you remember, so we said that this nickel do a oxidative addition via a radical mechanism, right? Now here, this oxidative addition here from this step to that step, this oxidative addition of this alkyl iodide is very slow, sluggish process because of this ligand environment. Okay, now if that's why we need to use a halogen atom transfer reagent, and this is nothing but this amine, okay, diisopropyl ethylamine. After quenching, it will form this radical cation. After deprotonation, it will form this radical. Okay. Now these radicals are very good in abstracting this halogen atom from this electrophile. So this is the that step, halogen atom transfer, to form this alkyl radical, and that can be trapped by this process, and to give this molecule, and this molecule is nothing but the ammonium ion and iodide minus. Okay, stable molecule goes out of the system. Okay, and we of course we also need to use this in stoichiometric amount slightly excess. Okay, to facilitate this halogen atom transfer and to have this reaction meaningfully. So as you can see, so if we don't use this halogen atom transfer reagent, so the yield drops from 85 to 27%. So that is the effect so of this halogen atom transfer reagent. Okay. So this slide, so I just now demonstrated how beautiful this photoredox chemistry can be, how good we can do. Okay. Now the problem I do not discuss again. Okay. Deceiving. So the problem here, we need to use this iridium. Okay, as a photosensitizer, a derivative of it. Now one can argue, one can optimize this reaction with organic photosensitizer. That can be done. Now other problem is that this nickel or this cobalt, so the loading I never tell in the slides, okay? And those loadings are 5 to 10% always. Okay, so I'm talking about a turnover of 10 to 20 at max, not more than that. Right? So we have a low turnover. Now the low turnover means there should be at least some process which is not efficient. Yes or no? In a catalytic cycle, because you see that a lot of steps in a catalytic cycle, at least some of the elementary step is not good. Okay, and that's why the catalyst is being consumed. Okay, is dying. Right. So we need to address that challenge also, and not only that, we need to somehow irradiate this iridium. Okay, iridium is not sustainable. Okay. Now this challenge I wanted to demonstrate with this example. Okay. Now this is CN coupling reaction. Okay, this Buchwald-Hartwig CN coupling reaction, and if you know, so this is actually changed the pharmaceutical industry how we make the amines. Okay, aryl amines particularly. Now in 2016, so this is the palladium catalyzed reaction. In early 2000, there is nickel catalyzed variant appeared, okay? So more sustainable than palladium, okay? Now this nickel catalyzed reaction also challenging because it required a very designer ligand system and also need stoichiometric of alkoxide as a base, okay, to facilitate the reactive elimination step, okay? So even though palladium is expensive, but the nickel as a whole with the ligand and the base and the condition, so all together is not good, okay? Now in 2016, Macmillan published this paper, so where he introduced this nickel chemistry with photoredox chemistry to do this CN coupling reaction, now at room temperature without ligand, okay? So he has solved many problems of that, okay? And then afterwards, Barron actually published this same reaction using electricity as the reducing equivalent. Now, from these seminal papers, there are a lot of reports on these CN coupling reactions, okay? Now, majority of those reports, they change the substrate, change the photocatalyst. Nickel is the same. Now, all of those reports, when we studied, they have one problem in common. First problem is that nickel loading is as maximum is 5 mole%, not lower than that. Now, electron-rich aryl systems are not working. When with electron-rich aryl system, so you need to have more loading. So that tells this oxidative addition could be a problem. Okay. Now, this could be a generalized, very simplified mechanism. Okay. Now, the mechanism is as follows. This nickel is being reduced by this photocatalyst, as I said earlier. It goes to nickel 0. Okay. Now, this nickel 0, this is a resting state. As I said that if this is electron rich, so the reaction is slowed. You need more of the nickel. Okay. So this is the resting state 1. Then after oxidative addition, transmetallation. Now this is a nickel 2. This is another resting state because the reductive elimination from nickel 2 step is slow. Now when you design a catalysis, so there you have at least 2 resting states, two steps. So they are bound to happen byproduct, okay, derived from catalyst. And the problem here that in the photocatalytic condition, this step, even with the help of ligand, can be facilitated. But the problem with the photocatalysis is that once you add the ligand, the photoredox reaction do not occur in this case. Okay, so these all reactions are ligand-free process. Okay. Now what happened is that since this is a slow step, this step is fast and fissile. You form nickel 0, and this nickel 0 actually agglomerate, and it forms nickel black. Now once it forms nickel black, it goes out of the system, no catalysis. Okay, that's the reason. So you always need a lot of nickel loading because शाम तो चला जाएगा बस थोड़ा तो बच जाएगा रिएक्शन के लिए, सही है ना? Okay, so majority will go and you have tiny amount of nickel which is remain in solution, that is actually doing the catalysis. Okay, so what we thought that this problem of these two catalysis problem when they are not talking with each other because they are not synergistically operative, so we thought of putting those two catalysts together, okay, in one system close by, such that this catalyst 1 and catalyst 2, if they are in close proximity, so that we can have this photoredox communication better. Okay, as I said that we need to have ligand to stop this nickel black formation and to facilitate the oxidative addition, right? So that's why so ION took a help from Professor Banerjee. We get this COF material from Professor Rahul Banerjee's group. Now this COF material, so he highly porous, so it has very high surface area and it has a bipyridine in it. Okay. Now what ION did, so ION first load this iridium inside this pore, then he load the nickel. Now this material have the iridium and nickel, okay, inside this pore in proximity. They always together. Okay. Now when they're always together, so we have very good redox communication between those two. And when we perform this photocatalytic reaction, now this reaction working very nicely. We have very, very low loading of nickel, only 0.2%. We can go down also. And this reaction, we actually do lot of control experiments. We need light, we need nickel. If we heat, it does not work. Now, this iridium loaded catalyst does not react, but only the nickel loaded catalyst, they actually perform this reaction. Okay, please keep in mind 36% yield. So that means that cob material can itself act as a photocatalyst, even though it's not efficient. Agree or not? Okay, we have to keep this in mind. The cob material is itself as a photocatalyst, but it is not efficient. That's why we need to have the iridium, okay, to facilitate this reaction. And if we mix them physically, so no catalysis, and if we have the polymer of this cob material, there are also no catalysis, because we need to have this order structure where this nickel and the iridium are in proximity in a defined position to have the catalysis. Now the good thing is that that this reaction now is faster than the homogeneous system or heterogeneous system. So we measure the rate, it's about 15-fold rate increment. Now this is in this loading, so you get only 5-6% of the product in a homogeneous condition. And another good thing is that this material is heterogeneous. Okay, so we can recover and reuse, recover and reuse, recover and reuse. We did 10 times, recover and reuse, recover and reuse. Okay, till ion is tired. And after 10 times, we check that iridium is intact, no leaching, almost nothing. Nothing is being leached, but the nickel is leached a little bit. Okay, so 0.3, 0.4% nickel is leached. Okay, but still after 10 times, this catalysis is more than 80% yield it is giving. Okay, so that's very nice. Now the scope is broad. You can have any aryl halide. You can take any heteroaryl halide. So this is we have tested aliphatic iodides, any aryl amines, alkyl amines, even these molecules. So those are looks interesting. Sulfonamide, we can do this reaction in gram. We can do late state functionalization. We can use this gram scale to make some very simple drug molecules. So these all work beautifully in our head. Okay, now last part. So as I said, this reaction works very nicely. Okay, but still we need to use iridium. Yes or no? And as I said, that you have to remember the photocatalyst, that cob backbone, it can act as a sensitizer, but is not efficient. Okay, so if we make this backbone efficiently as a photosensitizer, then we don't need to use iridium. Yes or no? Okay, so that is what we tried, and we tried that if we use all sp2 conjugated cob, okay, so that will absorb light and it could be excellent photosensitizer. Okay, now Ion took these two building block, a pyrene and this bipyridine, and he do simple Knoevenagel condensation reaction, okay, to make this cob. Okay, now this again a porous material, it has a surface area around 600. We can now do metallation with nickel to make this nickel loaded cob. Now we tested this cob whether it can act as a photocatalyst and a redox catalyst or not. Okay, now we some of the characteristics. Okay, now this cob molecule, so it absorbs anywhere from 300 to 650 nanometer. It has a very broad band. Okay, now if we excite this using a visible light, so this is the emission spectrum, so it emit around 460. Okay, now what we did, we load nickel cord first and aryl bromide. Okay, so we make this in hand. Okay, now this is the normal one. Now once we make nickel, now if you shine light, so then this emission from this excitation that will be transferred to the nickel, and we expect that the amount of emission should be lower, right? Yes or no? Because of intramolecular quenching of the luminescence. Okay, Now, what we did, so when we have this much percentage loading, we actually observe the lowering of the luminescence because of the intramolecular quenching. Now, this is the control. We can load more nickel. So then this quenching will be even more. And that is what we found. The more we load nickel, the more is the quenching. Okay. So this quenching is intramolecular energy or electron transfer, that we don't know what is it. Okay. But it quenches. Okay. The luminescence. Now, this is the quenching. Now we perform the same experiment with this COF and this bipyridine nickel bromide. Okay, two separate systems. Okay, bimolecular now instead of intramolecular. Now there also we have seen quenching. Okay, but not as good as this. Okay, now when we did for pyrene itself, there also we did little quenching, but not as good as any of those. Okay. Now this information, when we translate with respect to the Stern-Volmer quenching plot, now you can see this is the quenching for the intramolecular process, and these two are these two intermolecular process. Okay. Now because of this interlocking of this photocatalyst, that is nothing but the whole ligand backbone and the redox unit, intramolecular so we have very fast photoredox communication. Let me put in this way. Okay, very, very high quenching. Okay. Now for an application, so we tried this reaction. Now this is a CO coupling reaction. Okay, earlier we have CN. Okay, this is a CO coupling reaction. Now CO coupling reactions are reported by Macmillan, Knonik, Seerberger, and lot of people. Okay, using this photoredox chemistry. Okay. Now general mechanism here is that this photocatalyst, what we have shown as a COF, the earlier report used iridium and organic photosensitizer. Now in this case, the photocatalyst, it actually transferred the energy to this nickel 2 state to get it excited to facilitate the reductive elimination. Okay, in this case, no electron transfer. From nickel to carbon oxygen reductive elimination is slow. Now that step is facilitated by this energy transfer. Okay. Now, if you remember, that reaction we can do by heating. Okay. This reactive elimination, we have to heat 150 molecules, solvents, oil bath, everybody. Right. Now here, instead of heating everybody, they are only heating this complex by using this photosensitizer. Okay. Doing the same chemistry, we are crossing the activation barrier for the reactive elimination. Okay, now once we tried this reaction, we get 91% yield. Okay, using this COF as a photocatalyst, close to 1 mole% loading of nickel. Okay, it's a challenging reaction. Now there we have compared this our standard reaction, this one, with respect to other known system. Okay, now this is particularly highlighting. So this is the report by Macmillan. So he also did the same reaction. Now there you need nickel bipyridine 5 mole% to achieve this 85% yield of this product. Okay. Now we can do the same reaction in a heterogeneous matrix using much lower yield, much lower loading. Okay. And what we have seen that our catalyst is actually 6 to 7 times better than the homogeneous reactions. Okay. Now the scope is again very broad. Okay. So you can have any carboxylic acid ester, so you can do this coupling reaction. You can have this naproxen, and you can use any of this aryl iodide, and you can make this ester of naproxen. Okay. Now, I wanted to do more. Okay. So then he attempted this CS coupling reaction. The same material. Now we use this aryl benzene and then this thiophenol. Okay. So not so like attractive substrate choice, but still this reaction works. This reaction gives very high yield, and in this case, so if you take this homogeneous control, so this reaction is actually performing at least 70 times better than the homogeneous control. Again, the scope is very broad, so you can have any thiol group, so aryl, heteroaryls, aliphatic with any chain length, they all work beautifully. You can have any aryl groups, so aryls, all functional groups, heteroaryls, and you can do some interesting molecules to demonstrate, okay? Not only that, so ion tried this CN coupling reaction, same catalyst. Now we are converting this aryl iodide directly to aniline, and we use this azide as the coupling partner. Now this is a reductive amination. So this azide coupled there, and then this triethanol amine that actually reduce this azide to aniline in a single step. So again, this reaction works very beautifully. So we get very high yield with our COF catalyst, reusable. And again, we get around 50-fold better reactivity than the homogeneous reaction, okay? Now ion is not bored, so he tried the borylation reaction. Same catalyst, condition is different, again working nicely. So much better than the homogeneous control. Ion did the carbon phosphorus coupling, CP coupling reaction, phosphonylation reaction, again working very good, much better than the homogeneous control. Ion did the CC coupling reaction, again working much better, okay? And then we said, okay, we'll stop, okay, we'll communicate this work. So this photocatalyst, it works 8 different cross coupling reaction, very low loading, high yield, reusable. Now, finally, so this is the research topic we do in our lab. So this part I talk now. So we did a lot of this homogeneous chemistry, thermal condition with fast low transition metal, and particularly I work a lot on manganese. Okay, so that can be a separate topic, separate talk, and we are not discussing here. And then this is the most important slide. So this is an old picture of my group in 2021. So we are in Duos. There we have taken the picture. Now some people already left the group. So Satyadeep graduated, Kuheli graduated, Akash graduated. So I am very happy actually for these talented students. Okay, so those actually who work, who bring the idea, and he came to my office and tell that, sir, we need to do this work because this is important. So I'm very, very grateful for them. And I also would like to thank this funding agency for direct support for our research and also for their fellowship. And finally, I would like to thank you for listening to me. I'll be happy to answer any questions.
Thank you, Biplov, for the wonderful demonstration of finding different modes of catalysis. So there will be questions. Any question, anybody? Yeah, there is.
Biplov is really splendid. So I have one information I want to know, like when you're doing this photoredox combination, combining with the cobalt or your nickel. So are this chemistry we need really anhydrous condition, means like oxygen or?
So
I mean sling technique or?
Yeah, anhydrous sometimes is not important, but sometimes because our reactions are all reducting, okay, reducing. So we need to exclude oxygen.
We need to exclude
oxygen. Degas. Degassing is important. Water can be okay, little bit. Traces of water, not a problem.
When we do reaction with photocatalysis, we also observe like it's always undergo dehalogenation. Okay, like iodo substrate or bromo substrate. So you also showed there, like when you use a di-pair, like diisopropyl ethylamine, is that mechanism generally working there to dehalogenate, like carbon dot next to nitrogen, and that attack the iodine radical generate to the aromatic, and that take proton somewhere. That is the way, or?
So there could be two way. Okay, so this whatever you are saying, this is direct halogen atom transfer from aryl. Okay, so now Leonori has shown that from aryl you can have the halogen atom transfer, but most common is that you have a direct reduction of the aryl group. So you single electron transfer to the aryl, then mesolysis of the halide. You have an aryl radical, and that aryl radicals are super reactive. It will abstract the hydrogen atom from solvent or anywhere. You don't need to have amine.
Between these two paths, which one you think more feasible? Because it's always confused.
If you ask me, so I would say that the second pathway will be more feasible than the direct halogen atom transfer. But Leonori has shows that this with amine as a that, so you can have direct halogen atom transfer from aryl.
And this radical, aromatic radical, aryl radical, after let's say direct, you get the CX bond breaks and you get aromatic radical. Is this really free or like it's a complex? It's really radical.
Okay.
If you have any.
So this is also this is also something we do not understand. Okay. Now this aryl radical. So if I generate in presence of this B2 pin2, okay, we have the borylation. Now if you want to do a Giese reaction, for example, it does not happen. Okay. So something is inside the cage. So we don't understand much actually. There's no clear picture. Okay. Giese reaction won't happen. Okay. Same, but in principle it should happen, right? So you have a aryl radical that should act to the acceptor, but it doesn't happen because the other reactions are faster. Homocoupling and the hydrogen atom transfer from solvent or other molecule.
Thank you. Really, thought process is really nice.
Yeah.
For example,
quinolines are known actually. So that reference quinolines are known. I put Frank Glorious published in Science. Here.
Oh, okay. How about anthrazines? You tried or?
Anthracene we have not tried, but anthracene we thought that thermal dissolvers are known with anthracines.
Of course, very facile.
Yes.
But in your conditions,
we wanted to do something which is not thermally. Because anthracene, the aromatic energy is lower,
right,
so the product is more stable than the because
then
two sigma bond compensate the breaking up aromaticity. So now we are trying with other acceptor actually than styrene. Okay.
Yeah, the styrenes cannot tolerate any substituents. That was another.
Styrene tolerates substituent. Any substituent you can have. You have no beta position.
Yeah.
Beta position styrene no.
Okay, it's only 1,1 di substitute.
1,1 di substituted.
Okay, thanks.
I think interested to check if under photochemical condition goes to 1,4. I don't know if that will be interesting.
Yeah, that will be interesting actually. 910 is like that. Orbitals are so exposed.
Very nice presentation. I enjoyed it. You that COP material, you had the 1 iridium and 2 nickel. If that in rational band, you could have a more. There are many sites are still available.
Yes.
You could have loaded more. Is there any?
Yeah, it's a good question. It's a good question. We actually do all the permutation combinations, and with this combination, so we have the best result.
How it is comparable of iridium versus the your styrene based one? Which one is better?
Iridium versus styrene. So, like iridium is very good for that CN coupling, whatever I showed. The styrene is very good for the CO coupling. Other reactions will happen with both the system. But the CO coupling is very difficult. So, and I do not disclose all of the facts. So we have very particular base has to be used, particular concentration. And
the last question.
Sir, this is very nice presentation I see. And sir, I see that you are taking 4 transition element: iron, cobalt, nickel, and manganese. Can we take a copper and
yes.
zinc?
Yeah, definitely copper. One can take copper. Just we are not doing.
Because with copper and cupric are there, na?
Yeah, with copper there are plenty of beautiful chemistry are reported.
Is not taken.
We have not taken yet.
You are not a research area in that field. Okay.
Not yet.
Okay, sir. Thank you.
Are sensitive to oxygen. So just I wanted to what is the technique that you adopt for deoxygenation? Is it a typical nitrogen balloon pressure or argon balloon pressure?
Yeah, so yeah, it's a good question. So we do 2 techniques, okay? First, like simple one, we purge argon for 10 minutes before adding the substrate, okay? Now, these are for the simple reactions, okay? Now, For simple reaction, when it does not work, so we have to do Fitch pump throw. Fitch pump throw. So Fitch pump throw is the best. We freeze everything and then we vacuum it and we allow it to come to the room temperature.
Okay, so the interest of time, we have to skip the question and probably take it during the tea session. So let me
during tea.
Yeah, so please join me thanking. I also take this opportunity to felicitate Viplav on behalf of the. All right, so. Ready? Right, so we have our next speaker, Dr. Tirupati Barla from IIT Bhubaneswar. So if I shared my MSc alma mater with Viplav, I shared the postdoc one with Dr. Barla. So Dr. Barla did his MSc from Osmania University. Then after a short stint in Hyderabad, in industry, actually, GVK Bioscience, he went on to complete his PhD from IIT Hyderabad, working with Dr. Devendra Mahabatra. And then after another short stint, this time in Sai Life Sciences, he went to Professor E.J. Gore at Harvard University, where he spent about 3 years as a postdoc, where he worked on various types of catalysis there. Currently, in 2018, he joined IIT Bhubaneswar, where his group is working on total synthesis of complex natural products. And today he will talk about construction of spiro and fused bicyclic skeletons.
Yeah. Okay. So thank you, Professor Shantanu, for your kind introduction. And at the outset, I would like to thank organizer Tabrez Khan for the kind invitation. And after going through the several talks, it's kind of responsibility on me to go through I keep the motivation and the work in the same line or same level. So we are quite young group working from 2019, I would say, because I got student in 2019 onwards. So here, our research area mainly focus on the total synthesis of natural product for biological importance. And side by side, we are also working on the novel synthetic methodologies. So these synthetic methodologies, if we get chance, we also would like to implement these methodologies for the total synthesis of natural product as well. So why this total synthesis of natural product is important? Because if you see the current drugs, number of drugs taken consider around 1881. So the total natural products playing a key role among unaltered natural product around 3.8% and natural product derivative around 18.9%. So like that synthetic compounds, they are around 27%. In total, so the origin from the natural product is around 61%. So this is, you would see the major contribution coming from the natural product for the drug development and the discovery. So with this motivation, and we would like to continue total synthesis as a part of research, because I also trained chemist as a total synthesis during my PhD. So far we have started with small molecules and we were able to achieve some of them. So these are the newly isolated antimicrobial compounds, and looks like they are small, but when we accomplish the total synthesis, the spectral and analytical data of the compound we synthesized was not matching with the isolation. So this is the first synthesis, and student and myself was eager to see the result, but at the end we end up with the different compound than the isolated compound. So we went on communicating. So as we mentioned, like proposed structure, and also we have synthesized the diastereomer of it, because this diol will be easily incorporated by changing DHQ and DHQD method. So we convinced the reviewers this is not the real configuration of the compound, which could be maybe anti-diol, because this stereochemistry is fixed among all the families. The cyclohexene part, this chemistry is fixed. So none of the natural product having a opposite stereochemistry over here. So then maybe we are working on the synthesizing these compounds. Hopefully we will be finishing and will communicate and will assign the real configuration of this natural product. And one more molecule like this one. So Berkelactone M, this we have taken because the isolation group, they did not assign this stereochemistry over here. So this hydroxy, they mentioned it as kind of rest, either up or bottom like alpha beta. So we wanted to take this as a challenge, and we would like to confirm the absolute configuration by synthesis. So hopefully we will finishing very soon and will communicate in very soon this work. So, but today talk I will be highlighting the chemistry all over the chemistry of 2-keto 1,3-indene-diones. So this particular compound, if you see carefully, this compound having a diverse centers like nucleophilic centers as well as electrophilic carbons within the molecule. And also the reactivity in terms like this is maybe much more acidic hydrogen when you compare with here. And also the reactivity also over here, and it will be different. So we would like to explore the reactivity with this compound with different methodologies. The original motivation for this compound or design is coming from this original paper, which was published in 2019. So they have used the tricarbonyl compound with the arine insertion reaction. So arine insertion, arine can be in situ generated with the fluoride source with the O-triplet TMS compound, because fluoride is high affinity to bond with silicon. So this is OTF is a very good leaving group. So accordingly, you will generate arine intermediate. This further go on react with nucleophilic centers of this compound. So this was the mechanism they have proposed, and accordingly they were able to get the benzene substituted 5-membered rings. And one more work Professor Govardhan Mehta and group published by using indene dione. So they used a similar methodology, similar arine precursor, and this particular compound participated insertion reaction, and they are able to get the 7-membered carbocycle ring. So in combination with both the indene dione as well as the triketone, so we would like to see we wanted to see the reactivity of this particular compound with the arine moiety. So we were fortunate enough to get the bicycle compound with the endo-exo-isomers. You see the endo-exo-isomers, they are actually luckily separable by column chromatography. And we are also measured the single crystal X-ray crystallography to confirm whether we have right compound or not. And then we search the literature whether this particular skeleton have any importance or not. So you see these naphthocyclinones, Professor Hussain also highlighting the dimeric naphthoquinones. They are quite challenging to synthesize this particular compound. And even though they isolated in 1974, so far there is no total synthesis for this particular compound till date. But only one attempt was there from Suzuki and group. They were able to generate a core of this compound, but not in total. And one more, another compound like Hengel-Harkinone or maybe epoxide of it also related to the compounds having dibenzo bicyclic moiety. So the Suzuki method is quite interesting. So they have used dithiolate, and this particular rearrangement of the starting material is compulsory to get the bicyclic moiety. So the mechanism is very interesting. So sodium thiolate is adding here and as kind of 1,4 addition, followed by this gas is evaporated, and this further goes on react, and this intermediate particular they are isolated, and one more equivalent of sodium thiolate is added over the other moiety, and this intramolecular reaction resulting in the dibenzobicyclic moiety. So if we see the method when we compare with the literature method, so this particular orientation for the starting material is very, very essential. So otherwise this may not go up to the dibenzobicyclo stage. So but with our methodology, and we were able to synthesize many of compounds after standardizing the condition. So as I mentioned, the major minor compound were easily separable, even though, but we wanted to increase the one of major isomer further, and we were fortunate enough to found the cesium fluoride in combination with acetonitrile and 18 crown 6 as a additive. We were able to get 3.7:1. This was the best we have seen that. And after synthesizing, after standardizing the condition, we have prepared several arine compounds, arine precursors, and accordingly we subjected them for the arine insertion reaction, and we were able to synthesize many of the dibenzobicyclo. So here the difference is this part, and we have seen so many groups like halogens, electron withdrawing, electron donating groups. So most of them giving satisfactory yields. And I would like to highlight here the furan compound, and thiophene compounds also sustains, and we were able to get the dibenzobicyclic compound with thiophene moiety. And next we went on screening to the Indian ketone moiety of this side by keeping electron donating, electron withdrawing group, and naphthalene skeleton as well as benzene. So we were able to synthesize many of them with this methodology. And here, this particular compound, when we have a substitution over here or here, this the regional isomers isolable around 1:1 ratio. So this arine regioselective was not controllable, but if the arine is symmetric, then we were able to see only endo-exoisomers only. So, and other part also we have screened and the electronic effect of Indian moiety, and we have also synthesized this particular compounds, and they're also 1:1 ratio. So after synthesizing, we went on screen, looking at the literature, whether we can implement this methodology for any of this natural product. So this particular compound, rubiolatin, was isolated by Tan and co-worker, and there was only synthesis was reported for this molecule, and this is showing a very good anti-tuberculosis and anti-cancer activities. So with that, we have synthesized the required arine precursor, and we have subjected under standard condition. We were able to synthesize this 1, 2, 3, 4, 5 sequence rings with 6, 6, 5, 6, 6 skeleton of the rubiolatin. And for that, this double bond was epoxidized by using H2O2 in basic condition. And this particular compound also confirmed by single crystallography. So with this motivation, we wanted to see the gram scale synthetic utility of this particular method. And also we have received some comments, some advice. So most of the natural product at the bridge, they don't have any substitution. So, but with that method, we able to, we are seeing this ketone there. So our next task is to, whether we can remove this carbonyl, because most of the natural product doesn't have any substitution over there. With that motivation, we able to synthesize this particular carboxylic acid from furan derivative. So then this was further converted into reductive active ester, followed by radical mediated elimination gave the bridged unsubstituted bridged compound. And also we converted the particular carboxylic acid into amides, esters, and Weinberg amide. Of course, this can be further converted for other functionalities. And like that, we have prepared many of such derivatives. And with this, we propose the mechanism, and similar to the existing literature, And beautifully, we isolated some of the intermediate, and we have fully characterized this particular compound as well as this particular compound. So this evidences supports the proposed mechanism, and with this we were able to also see the spectroscopic evidences for the formation of the intermediate also. During the reaction, we have screened and we have in situ measurements for the NMR spectroscopy to the intermediate formation, and they are also isolable. And this work was published in JOC with the nice front page. And I should thank my student Geetanjali for the design. After that, then we would like to explore further reactivity of this compound. So whether this can be utilized for other alkynes such as DMD or dimethyl acetylene dicarboxylate. So with this, we screened some of the initially inorganic bases, and we were able to see the spiro compounds there. So this particular result encouraged us, and whether this reaction can be conducted in organocatalytic base like maybe DMAP or DAPCO or triethylamine, some organic bases. And we were fortunate enough to found the DAPCO with 20 mole percentage and was able to produce the required compound with at 80 degrees centigrade. So, of course, this particular compound also confirmed by single crystal X-ray crystallography. And next, we moved to the synthesis of various substitutions on the indane, and we were able to synthesize spirocyclic compounds. So I should highlight this spirocycle also present in various natural products like fretriamycin and some more antibiotics. I did not show it, but this skeleton is also very, very important for the synthetic community. And with that, the similar substrate like furan and as well as thiophene moiety is also subjected for the spiro compound preparation, and we were able to synthesize very useful compound. And one more advantage here, when you have extra carbon here, there is a chance to synthesize. Initially, it's a 5-5 spiro. Now it is like 6-membered ring with the spiro moiety, and there we were able to synthesize some of the example. And next, we just proposed this is a proposal, and by using the DAPCO. So initially, DAPCO might be coordinating with the indane triketone and followed formation of the salt. This can be reacting with the dimethyl acetylene dicarboxylate. And of course, this intermediate also, we stopped the reaction in between and we characterized this intermediate. And next, we, anyway. So the next task was to see the further functionalization of furan moiety. As we know in the literature, so the pyridic acid mediated spiroketalizations are known. So we have applied the similar conditions, whether we can spiroketalize this furan with having a hydroxy over here, and we are fortunate enough to see the lactal. And the lactal was having a diastereomeric mixture. Then we subjected the lactal moiety for further oxidation. So we were able to see the bis-spiro compounds with this furan. And here, and as I mentioned, this is a 1 carbon and the homologous of triketone. When you have 1 more carbon, you will see the 6-membered ring with the similar result. So, and one interesting result I would like to share here. So actually, we wanted to remove the hydroxy by hydride replacement, but we were unable to do it. But we could isolate the exocyclic double bond compound. And interestingly, when we treated the phenyl, so there is no such protons, but we were able to isolate this fulvene skeleton. So I would like to share a story with the students actually. When a student trying to isolate, and since she was using TFA, she was quenching the reaction with sodium bicarbonate. So this compound is going into the water. So we realized, the compound is highly polar. Why it is going into the water? So she could not realize. So this is having a kind of phenolic or alcohol moiety that is forming a salt. And after several trials, I suggested let us don't quench with the bicarbonate, try to isolate directly. So then the NMR spectrum is completely different from the earlier spectrum. And also the compound is highly colored in nature. And when we see the spectrum, we were missing these protons and also spirocarbon carbon also missing in the C13. This is quite challenging to say whether this compound is there or not. It is kind of almost one and a half month we screened several things, and with extensive NMR studies, we were able to assign the compound as this fulvine skeleton. In the literature also, the compounds having this fulvine skeleton are highly colored compound. And when you change this chromophore, especially hydroxy to nitrogen, they are kind of using as a dyes also. So this was the mechanism we proposed. Maybe this is forming like this. The hydroxy may be protonated with TFA and followed by when this particular compound, when it is spiro attached with the cyclobentadienyl compound, this might not be stable. So that is the reason why this is opening and forming a enolate, and this is further reacting here, forming a 6-membered, and the proton shift might be happening followed by the highly intense colored fulvine skeleton. So this is a different result we found recently. With this, we have synthesized series of dibenzo bicycloskeleton with the triketone with the arine insertion, and also spiro compounds with the DMDO, and the developed methodology is having a high substrate scope, and this methodology may be implemented for the synthesis of some natural product. And now we are exploring some more methodologies with this particular moieties. Maybe asymmetric version also we have started a little bit. We'll see, hopefully we'll present some results in the future. And we have basic facilities and like NMR 700 and 400 and HPLC and all other required facilities, except single crystal facility. And of course, I should thank my students. Some of the previous student, he now moved to Israel, is a postdoc, and some BSMS students along with my PhDs. So with this, I would like to close from my side. If there is any question, I'm happy to. Yeah.
Thank you, Dr. Barla, for finishing well ahead of time. It's a lot of questions. I'm sure there will be a lot of questions on the mechanism of the reaction. Can you hold the slide?
Yeah, okay.
Slide 36. Post it. 36. They can do that. Okay. Press 36 and enter.
Yeah. Yeah.
What happened to the ester groups? They're there or gone?
Oh yeah, Esther was there. Sorry, I forgot. Yeah, Esther was there. This mechanism I draw in the last night maybe. Yeah, Esther is there.
They are lost in camera, not in
Camera. No, not in the. Yeah, sorry. So Esther is there, and overall skeleton is this one.
Okay, let's see if there is any question.
Yeah, please.
Yeah.
Yeah, nice talk. So
Thank
I
you.
have a question regarding the arine insertion reactions. So your tricyclic products are having multiple nucleophilic sites, right? So two possible enolates, although it is sterically hindered, and an OH. So how did you control the mono-selective addition of arine?
Yeah, I mean, if you see the substrate, one of the hydrogen quite acidic, right? So that might be controlling for the initial enolization. After adding, anyway, we are using two equivalent of base. So after adding the insertion with arine, that might be further going for the forming the 7-membered ring. And since it has a base, one more equivalent, then intramolecular aldol might be taking place to form the bicycle.
Did you observe the final insertion of arine to the OH bond? Because your product is an alcohol, right?
Yeah, tertiary alcohol.
OH insertion is
No,
much
no.
facile than CC insertion.
No, we haven't.
Did not
observed.
observe. Good, thank you.
Thank you. That we maybe it's because of tertiary, so yeah, but we haven't seen any traces even.
I have one small query.
Yeah.
So you use one naphthalene derivative having 3 hydroxy group phenolic, like 1, 2, and 4. So how you get that molecule?
Yeah.
On naphthalene, like you are doing, I don't remember the slide number.
Okay, so
You wrote like 1, 2, and 3, 4 hydroxy naphthalene.
Can you minimize the small window? Okay, so this one.
Yeah, this one.
Yeah.
12J.
Yeah, this one. Yeah.
How you get that molecule?
So this was actually reported already. So we have followed the similar synthetic strategy. So it's already reported. Actually, this interview is reported. Yeah.
And I'll check.
So Gordon Mehta actually, in fact, they synthesized.
So Tirupati, that structure you have proposed that structure assignment was basically wrong, right? By the isolation group.
Yeah, the initial total synthesis, yes, yeah.
Okay, so now it is matching with your.
Now we are working to synthesize the other diastereomers. Hopefully, we could able to synthesize the natural product.
Okay,
again.
then we will match it.
Yes, yes.
So Devendra group has already to prove 12 structure wrong, right? So
Yes, yeah.
we are
He
heading to
works,
that one for more
yes,
structure.
yes. He works on the kind of reassignment, many of them. Yeah.
Can you please go to that mechanism in 37 or
Sure,
something?
36.
36.
Yeah, yeah.
Yeah,
Oh,
here,
sorry. Yeah, sorry.
yeah, you're proposing the breaking of that CC bond leading to that C triple bond O system, right?
Yeah, yeah, this
Yeah,
one.
maybe
Yeah.
mechanism can be considered alternatively without that intermediate. I feel, you know, the when water you're showing as leaving can be olefin can be generating, and that CC bond can be you know, pushing the electron towards it and protonating the double bond can be the driving force.
Okay, okay.
That's what I'm saying.
Become carboxylic acid. Instead of C triple bond O plus, it become carboxylic acid.
Yeah, what I'm saying is, see, it can lead to the double bond. Water elimination can lead to the double bond.
Yeah.
And now you can forward the CC bond connected to the carbonyl. And that double bond will be protonated by H plus.
Okay, okay, yeah.
So that you now get the ring expansion.
Exactly, yeah. Of course, this proposal last night I made this slide. So sorry for that. The extras are removed, but this was.
Yeah, you can consider, of
Sure,
course.
sure. Thank you. Yeah, definitely. Yeah. Thank you.
Any other question? Any question from students? Okay. Okay. If there is none, please join me thanking Dr. Varla for wonderful talk in this area.
Thank you. Please join me for the speaker. We'd like to invite Dr. Tabriz Khan to felicitate Mukherjee for chairing this.
With the conclusion of extremely insightful lectures by Professor Biplab Maji and Professor Barla, We now come to the end of third technical session of day 2 of the workshop. We'll now break for a blue ocean tea break, which I'm sure will keep us spirited for the session ahead. I invite you to kindly take your tea and reassemble in the hall in another 10 minutes. Thank you. set us all in motion again. We shall now resume the workshop for the final session of the day. It is my immense pleasure to invite Professor Perucharathan from IIT Bhubaneswar to chair this session. Thank you, sir.
Good evening, everyone. This is the last session of the today's symposium. It's two things are there. One's very difficult to share the last session, and of course speakers too, because the time is running. I have to keep the 40 minutes time also, and the speaker too. Okay, because it's the last session. Okay. And first of all, thank you to Professor Khan for giving this opportunity to chair this session. Let me introduce the speaker. The first speaker is Professor Prabal Banerjee. So he clearly told me that don't give too much introduction. So then I will give only few introductions. So he did PhD with Professor Ganesh Pandey, CDRI. Sorry. NCL Pune. Actually, NCL Pune, and he did 2 postdocs with US as well as Germany. And he has a lot of awards. So just mention about only one. 2021 he was the bronze medalist CRSI. And with this small introduction, let me welcome Professor Prabal Banerjee to talk about electro-organic synthesis. The one small thing is that since the whole lecture, there was no electrochemistry involved. So he's the one going to talk about the electrochemistry. Okay.
Thank you, Peru, for your kind introduction. At the outset, I would like to thank Tabriz and his team to invite me to come over here again. And I think this is the first time I'm talking here. And yeah, it is the last session. I can see people are less also. So it's okay. Let's start. So today I will be talking on electro-organic chemistry. Whatever the few development we could make in our lab to making cyclic and acyclic scaffold. And normally before starting, okay, they're sharing, I think. Before starting, normally I tell something about our institute, especially about the gate that Indranil already has told that what is implicate and all. And again, I also invite you all, if somebody of you visiting that site, please come and see our institute. Coming to back to the business, what I'll be talking today, and I'll just quickly go through the sphere of our study. Then I'll introduce you to electro-organic chemistry. Then six work I'll discuss today in three different areas. Two is for generating reactive intermediates from electrochemistry and their application. Two is small, again, the strain ring activation, our original chemistry doing another way, and two, phenol oxidation. And then we'll go the future aspect also. So what we do in Roper, this is the area we have started working with small ring. I have worked with cyclopropane, aziridine, epoxide, oxaziridine. And we have shown reactivity of two standing in presence of each other. So many chemistry has been done. And presently, we are working on cyclopropane monocarbonyls. And this is a part of a standing system, but it itself became an area of our study, that extensive study we are doing. And this is electro-organic chemistry and some medicinally important compound. Here I should tell, whatever the molecule we make, we found collaborator, and some of the molecule became active. In the COVID days, the antiviral development, we have some hit molecule, it had reached to some stage, we have filed patent and some publication, and also to project we got. It was not related to our synthetic work, but when we get involved to the medicinal chemists and biologists, it yields something. This is the some development we have done in the beginning. We have worked with do not accept as cyclopropane, and we could do many annulation reaction, atom transfer reaction, dearrangement, many things using this. And presently, as I told, we are working with cyclopropane monocarbonyl, taking it as a handle. We could do very interesting transformation, and presently we are working on organocatalysis of that using this, and we have many results. We hopefully the coming year it will come to all of you to see what I am talking about. There are some hiccup, and that part get clear, that the gate will open. So so today, as my title the talk says, I will be discussing on electroorganic synthesis. Now, chemist as can tell, or any technologist and all, we should do something which is good for human being, or we should excel ourselves. But at this process, we should not do the work such a way we are not keeping the same resources for our future generation. We should able to keep the level playing things for our future generation to do work the way we are using the resources. That means I am talking about sustainability. If we are making the use of the resources in too much way, the conventional way what we are doing, the organic transformations, so that need to be looked upon. So in this way, there are many new developments are happening. One of these is electroorganic chemistry. It is, if you can see some of the points, bullets I have given, you can see this is comparatively more greener. I am not telling it is complete green. There is some more issues has to be overcome to make it completely green, I can say, because I can tell it's 9 principle it follows out of 12. There are some more development has to be done, some technological development. So if you go through the history timeline, electrochemistry, electrochemistry is not old. If you see the development of battery, it happened at 18th century. Now, at 1834, the organic chemists started looking upon it, and the Faraday electrolysis came. Then within a few years, the Kolbe electrolysis came. Now you see, 19th century, there was development. Then Siemens fluorination came. Now you see the timeline from 1847 to 1975. No more significant. There are some little development, but the notable development, it took 130 years. That this the groundbreaking discovery by Sono, it came, the Sono oxidation. It's a tremendous reaction for the alkylation just alpha to nitrogen. Now, after this late 20th century, it started development. Many new reactions came. Notable that chiral electrode came. Then the little reductive coupling. Then molar anodic coupling. Then this thing Osida cation pool reactions. Now 2000 to present, and as I can tell, I come next slide. It started in more effective way by the organic chemists to use it because of the other technical development, the metal mediated electrosynthesis, development of flow electrosynthesis, and development of microreactors. And these things and some new development of the organic chemist was feared to use electrochemistry because of this operational problem. Then the new instruments and all made people to work on this. So what is electroorganic chemistry? Electroorganic chemistry is synthesis of organic molecule by applying electric potential or current. So that means what are the things are there? So you see the two variables we have, potential and current, and we have anode where normally oxidation takes place, cathode reduction takes place, and you need to use electrolyte, solvent, and additive to enhance the rate of the reaction. This is all we need. So the 2015 to 2020, fourth person who made enormous contribution to this electroorganic chemistry. You can start with Organo. He has done a lot of work on phenol oxidation, and one of the example, just it is a different example, not phenol oxidation, it's generation of cyanide. Then you know this Professor Baran. The electrocene make the groundbreaking change among the organic chemists to use electroorganic chemistry. And also he has shown the use of this chemistry in total synthesis. Then Professor Song Lin, he has also done notable work. One of the example, just for your curiosity, I put, and Ivan Lee. So they made enormous contribution these 5 years. Now all over the world, people are trying to adopt this technology in their lab. So what are the modes of electrolysis? You can do electrolysis at constant potential. You can see this way your potential is constant, so your current is decreasing. So this is not good one. If you can do it, good way to do electroorganic chemistry, constant, not good way, constant potential. If you do at constant current, you see the potential should vary, but potential vary means the ion concentration vary. That the plot is that's what with the concentration. Now you see the concentration of the reactant decreases. So it's better way to do electroorganic chemistry. You should start with constant current. There are another one which is alternative current electrolysis. This is very new way it has come. Some experiment it will be very useful. You can see when you see electrode passivation. So you change the polarity, then the passivation will decrease. So it's like that, reduction, oxidation, reduction. There will be a time gap like that. So we will not talk much about that. I'll show you just 2 examples what I am talking about. One reaction Professor Molar reported, you see the addition of this NH, it has been done at constant current. The current they have made it 6 milliampere and the potential and concentration vary. Another reaction by Daniel Little, the Bayer-L coupling, this has been done at constant potential. So that's what I was talking about. Now, electrolysis can be done 2 ways, either direct or indirect. Direct electrolysis means we are talking about oxidation. Suppose we are talking here oxidation will happen at the electrode surface. That means it is heterogeneous in nature. But if you can do indirect way, that means you are using a mediator. Mediator will get oxidized at anode, and it will oxidize the substrate to the intermediate to product. Take one example. We are talking about this toluene things to generate the toluene radical. You see, when electrolysis is done at direct mode, the potential you see that this 1.2 volt. Now, when it is done with in the presence of the mediator NHPI, you have to the potential is half. So you are working on in less potential, so your reaction will be more cleaner. So another mode type is paired electrolysis. Paired electrolysis is of 2 types. One is parallel electrolysis. What I am talking about, you see, anode oxidation of one substrate is happening to corresponding benzaldehyde here. One example I am giving, and the cathode another substrate is getting reduced. And divergent means same starting material. In cathode it is getting reduced to sorbitol, and in anode it is getting oxidized to gluconic acid. So now in our lab, how we have started. The title said the urea is the seed of our lab to start electroorganic chemistry. I'll tell you how. We are working, we have done a lot of work. I may not tell lot, but we have 4 or 5 publications we have on urea derivative, and this molecule came to blessing for us in many reasons. If some time I will discuss that. So Majid was working on this project, the strain ring chemistry annulation reaction. That time Deborsi joined, and Deborsi was taken to lab to initiate the electroorganic chemistry in our lab. So when he was helping Majid that time, and he started exploring what are the other reactivity or electrochemistry of urea derivative is known. Then he found out in a urea derivative there was one paper where generation of the azaoxylyl cation was known using carbon platinum things, and that undergo a 4+3 cycloaddition reaction. How things are happening? Double deprotonation and double oxidation to generate the azaoxylyl cation. Then he told, sir, these things are known. Then we started looking more closely what else is known. He found Professor Jeffrey was also working not using electrochemistry but using PFA, the hypervalent iodine reagents. So he also report the generation of diazoxylyl cation, then 4+3 cycloaddition reaction. And another work, this work, he reports, he found some of the product which is generated from isocyanate as a side product. That means in oxidative condition, isocyanate is getting generated. No, that's why a side product. No other work was known, not electrochemically, but hypervalent iodine. Then as all of you know, isocyanate is an intermediate. Professor Madhu was presenting. Lot of chemistry is known, but you see the synthesis is you have to use phosgene and other things, and this rearrangement you all know. This is a textbook rearrangement to generate the isocyanate, and the reactivity morning it was discussed. Many addition reaction with amine, alcohol, dimerization, many reactions are known. So now from this point we take thought like this: if we take dibenzyl oxyurea, we do oxidation in one of the nitrogen like this, then this lone pair should come and this nitrinium can go away, we can generate isocyanate. And for that, we have taken dibenzyl oxyurea derivative like the double things like this. So one of the things will get oxidized to make the isocyanate intermediate, and this will add to the isocyanate, and different 4 different molecules we could make. What are those molecules we could make? We make 10 example of benzimidazolones, quinazolinones, oxazinone, pyrimidinone. So this molecule we could make using the same putting 2 urea moiety and electro oxidation. So one of the urea moiety is getting oxidized and another one is adding. Even we can change make oxygen simple, so oxygen is getting added. So now we wanted to see how the reaction is happening. So we have to prove, this is the first example, electrochemical condition, we could trap the isocyanate and prove trap detected by HRMS. So if we are when doing the reaction in standard condition using TFP, so we found this HRMS and this HRMS. So that means that isocyanate is generating. So we have done other experiment, radical scavenging experiment, radical clock experiment, other control experiment. Then we found out radical is absence of radical intermediate. Then the CV, please pardon me, this CV was taken using in the beginning, we was not having any CV machine. We did in ICA 2.0 and that CV was not that stable, but value is correct. We have standardized with ferrocene, then we have seen. So what I wanted to tell here, you see this is the oxidation potential of 1A, that by this urea moiety you are taking. So when we add ferrocene to it, you see the potential is decreasing. Even after we adding base, mean ferrocene or substrate and base, you see the catalytic current is increasing. So that means all the things are necessary. So and based on this, we propose the mechanism. So the water is generating the base, deprotonation happening, then 1 electron oxidation, again deprotonation, another electron oxidation is giving this species. And this species, as I told earlier, nitrinium is going away. We have tried to trap this nitrinium to prove. Many way we have tried, but we could not trap it. But we found a paper where they found they explained the nitrinium can can dimerize, and ultimately it gives nitrogen and methanol. Now come to this isocyanate. That this isocyanate, another urea moiety can attack this nitrogen lone pair or that nitrogen lone pair. So one will be 7-member, one will be 5-member. So 5-member was more 5-exo cyclization was more favored. So we got the 5-member product. And as I told, we are so this all about isocyanate, and this we get interested to generate other intermediate. Suppose other reacting pieces like azomethane halide. So azomethane halide, it may be stabilized or non-stabilized. So this was done, why I got interested, because in the PhD we use this chemistry, the azomethane halide chemistry, to generate non-stabilized azomethane halide and do total synthesis. Then that point of time I thought let's try electroorganic way to generate azomethane chemistry. At that point I have decided if I succeed I will dedicate this work to science. So that this azomethane halide, this non-stabilized azomethane halide, the two way I have shown, and as you know it can undergo different type of cycloaddition reaction, and it has many use. We have a review also where you can see we have nicely demonstrated. So what we have done? We use the DiTMS compound. So in electroorganic electrooxidation, it generates the nitrogen radical cation, which after 2 TMS loss and 1 electron loss, it gives the azomethane halide. In situ, it undergo a 3+2 cycloaddition reaction. It generates different pyrrolidine moieties. We could make many examples, but still this reaction needs more standardization and more closer look, because yield we could not improve much. At the most 64% we got, but this reaction goes spot to spot. It's a very nice reaction. But we show the reaction can be done we have done this radical scavenging experiments with TEMPO and BHT. You see the reaction goes. That means the absence of radical intermediates is implicated. Also, we have done the reaction in gram scale where yield is okay, 70% you will get. And the CBE, you see, this is the CB diagram of this DiTMS compound. When we are adding the dipolariphile, little bit catalytic current is increasing, the oxidative current is increasing. So this is the only thing we could found, the both of the things, what are the change it is there. The mechanism is like that. So when DiTMS compound, that is nitrogen lone pair, 1 electron oxidation, it generates the nitrogen radical cation. Then due to the beta silicon effect, 1 TMS goes, followed by 1 electron more oxidation gives the iminium cation. Again TMS plus goes away, generate the azomethane halide, and which undergo a 3+2 cycloaddition reaction. Now the generation of reactive intermediate we have discussed already. Now I will coming back to our strain ring chemistry, and the cyclopropane ring, if you see, it looks strained, but the internal orbital angle is 104 degree, so it is kinetically inert. That means it has to be activated, and with this we have done many things using this. So these things, activation by Lewis acid, Bronsted acids is very well studied. And this organocatalysis activation and annulation, as I told, we are working on. But when we come to the aryl activation, means we want to activate the aryl ring and activate ring opening reaction by functionalization or cycloaddition reaction we want to try. There was one example where photoredox chemistry has been used, where aryl activation has the activation done by photocatalysis, and 1,3 bifunctionalization has been done. So what we wanted to try? We wanted to try take simple aryl cyclopropane, and as I told, this this has to be activated. So we want aryl activation, and followed by we wanted to try basically cycloaddition reaction. But all the time we are ended up with this beta hydroxyketone, because the little bit oxygen whatever was there, it is forming the endoperoxide, which is cleaving and forming this derivative. So this is interesting compound, no doubt about that. But we continued this study. We made different example, and also we do radical scavenging experiment where we found if you add tempo in the standard condition, complete shutdown of the reaction happen. That means radical is there. Now, when we are doing the reaction after many type of the freeze dye and other things, removal of all oxygen or that possible by us, complete shutdown of the reaction happen. And if the aryl ring is not there, reaction was not going. Then CB is very interesting. You see 1A, 1B, where the aryl ring or there is a methoxy group, you see the oxidative peak. But when there is a nitro group, this peak is absent. So that means the electron cloud has to be available for oxidation, easily available for oxidation. So based on this, we propose a mechanism. So the aryl ring is getting oxidized at anode to getting the aryl cation, and which is in turn is forming this species where oxygen is getting trapped, and it is forming the endoperoxide. The 5-member endoperoxides are very unstable. Then that get cleave to give the 1,3 oxyhydrolate product. Now we told I show you the activation of 3-member ring using aryl activation. Now we wanted to study the same activation of the 3-member ring using a heteroatom handle. What we are talking means, suppose we have this species, cyclopropyl amine. This is the usual reactivity, intrinsic reactivity. This lone pair will go there and this will open. And metal mediated reaction, those are very well studied. Now if we want to use the nitrogen lone pair and oxidize the lone pair and generate the do radical chemistry, this radical intermediate we wanted to capitalize, then we look up the literature. There was, redox chemistry. This was known where there is the tosyl derivative. With benzyl, working with the benzyl is easy because you have to work on much lower voltage. But when there is an electron withdrawing group that tosylate, no report electroorganic chemistry was there. The nitrogen activation, oxidation, and 3-member ring opening. So we took this idea. So idea like this. If you take this derivative to deprotonation followed by generating the N-centered radical and followed by opening and C-centered radical, and this can be trapped by a dipolar file. Eventually, we are talking about a formal 3+2 cycloaddition reaction to generate the amine substituted functionalized cyclopentane derivative. These are very important molecules. So we succeed this one. We made different examples. You see, we could generate a all carbon quaternary center, even reaction worked with triple bond also, and the other double bond remain intact. And we have tried to prove the mechanism. So both the radical scavenging is complete shutdown of the reaction was observed. That means reaction there was radical involved. And in the standard condition, when R is tosyl is replaced by CO2, COCH3, this reaction was not going. That means we have to work in different potential. The carbonyl, the amide and the sulfonamide reactivity is different. The availability of the nitrogen lone pair is getting getting difficult. Then this experiment is very interesting if radical propagation is happening. So we did the reaction for 1 hour, then switch off the current. If at all it's a radical chain reaction, it should go to the completion. But it didn't happen. Some product formation observed, after that it remained the yield there only. That means constant oxidation cycle, this has to be maintained. So another thing, we trapped the radical, the C-centered radical, what I talked, where it is C-centered radical generated and it is attacking here. So this we tapped and prove this we detected, and ultimately this product was formed. And another interesting observation, control experiment we did is the divided cell reaction. If we put our reaction mixture either in cathode, either in anode, no reaction happen. So that means this indicates a paired electrolysis. When both cathode and anode things are involved in this transformation process. So based on all these things, and also the CB, tell that adding up ferrocene, the catalytic that oxidizes. You see, this is the normal 1A, but in presence of ferrocene, this catalytic current density is increasing. So based on all these things, we propose a mechanism. So base is taking the proton, generating the N minus, and which is getting oxidized indirectly with ferrocene, generating N-center radical, where after ring opening it is forming the C-center radical, and which is adding to the double bond, and which is forming a radical which is getting reduced at cathode to anion. And this getting protonated, we detected this compound. And also our yield is little bit low due to maybe this problem also. And this anion is getting a 5-exoteric cyclization to give the cyclopropyl amine derivatives. Now we discussed generation of reactive intermediates, reacting species, then our own stranding activation using electrochemistry. Now, side by side, we got interested in phenol oxidation. So before going to that, let me tell you the paracetamol in COVID time, it became the drug of every pocket. Anytime you can feel feverish, because we all are sometime mentally we are feeling feverish. So सब लोग तो जेब में एक डाल के रहते थे. So that means, but if you see as an organic chemist is synthesis, it's very cheap drug. Okay, I am not telling it's expensive and all, but these are the three commercial routes. And you see the global demand of paracetamol is increasing. See the curve. Now, all these things is not straightforward. There are a lot of wastage, lot of byproduct generation, and these all are polluting our environment, and which is in turn is getting threat to the human life. So I'm not telling that immediately thinking a greener approach for cost reduction, but thinking about the future environment as a whole, as an organic chemist of the 21st century, we should think about an alternative method. And what we thought, see, this is paracetamol. You see closely, if you look from the color coded, this is phenol. And you count the number of carbon, 2 and 1 nitrogen. So this can come from the acetonitrile moiety, and 1 oxygen we have to add, it is moisture which is there. So what we thought, we can oxidize the phenol like this, and we do use the Ritter reaction, which is well known. We can we are thinking about anodic oxidation, nucleophilic paraselective, nucleophilic attack, and it could give the paracetamol. So actually, if I go to the backstory of this reaction development, we are doing a CH activation reaction. We had a ethyl group here, and we want that benzylic position to be oxidized. My student Majid called at night, sir, that reaction to hua nahi, wo phenyl ring mein lag gaya. Bola, what you are talking? So they gave me the NMR. Then we found out it is happening like this. Next day we did reaction in the phenol. Then we found paracetamol is forming. So then we started the project of development of this method. And this reaction is so paraselective. When we block the para position, when we block the para position, here if we have the methyl group, that example actually I forgot to put here. If the methyl group at the para position is blocked, then you do the reaction in the standard condition. That this doesn't go in the ortho position. It go to the para position, benzene ring become quinone. So it is not getting the aromatic stabilization, but it is going to the para position. So we have done this reaction in gram scale also. Yield is around 70% in the gram scale. So what is happening basically? The phenol is getting oxidized as anode, and 2-electron oxidation is giving this species. This chemistry is very well known because if the Watt-Goebel has done lot of biphenyl coupling, lot of good chemistry he has done, but somehow this product he didn't observe, or his because this reaction is very interesting. If you see the mechanism, we need to have water. Water has to be added, then only it will form the paracetamol. Then if we add water, suppose 3:1, like you want to put more water, the reaction get more facilitated. But what happened, it's so sensitive to water quantity, we used to use that the syringe, the micro syringe, and drop wise water. 1 drop is maximum. Best thing is we have found just use distilled acetonitrile, not dry, distilled acetonitrile. The moisture, whatever present here, that is the best concentration of water it suits to give the product, and best still now our observation. If you want external water, this reaction is becoming sluggish. So this is very interesting. Water is needed, but the concentration of water is very determined. So that was our paracetamol. We made many derivatives of paracetamol. This need to be tested, but the testing and all we have not thought. The interesting now, one of my friend was telling you make orthocetamol to see how its reactivity. I told these things is nothing, but these things we can think of. Now with so we have discussed paracetamol here. Now here so this nucleophile here was acetonitrile. Now we thought if this nucleophile may be a heteroatom like sulfur. Why sulfur? If you see the market side of sulfur, there is also a steady increase in the market side. But if you see the frontier things, it is the fertilizer industry, chemical processing, metal manufacturing, and all. And market side is increasing, no doubt about that. But we wanted to look the sulfur drug, what are the available. So if the sulfonyl bearing drug, these are all, I think all of you know, this is proton pump inhibitors. So, and another drug you see sulfoxamine bearing drugs. There are many drugs where these moieties are there. So, and also the drug size of sulfoxide drug size, this also a increasing thing, and the market size is increasing, that demand is there for a new methods. So based on this thing, we thought if we use the same in a phenol oxidation, use the nucleophile a sulfide, aromatic sulfide. When this is needed, a benzyl group, I'll come to the mechanism. And if we use the same way, this will add, and it is ending up this sulfoxide. So making a heteroaryl sulfoxide, no metal, is very interesting observation. The way we do, we make different types of molecules, and again we wanted to prove the mechanism of the reaction. With tempo complete shutdown we observe, that means there is a radical involved, and we detect the benzyl alcohol. As I told, this is very important. So this part is going away as a benzyl alcohol, and we made sulfide used in the standard condition. So this is forming first, then sulfoxide is forming. Then divided cell experiment we have done. So reaction mixture in anode chamber, it is giving the product, cathode chamber, no reaction. So only anodic oxidation is involved. And again we have done the time based study. So after 1 hour, if you stop the current, So the trace amount of product is there, no further improvement of observed. That means the electricity is needed. And the CV, you see again interesting thing, this is phenol. In presence of this, the current, you see it was here, it is going there. So both of the, in presence of both the things, using the current we are standardized, this oxidation is feasible. So again that as I told, phenol is getting oxidized to this species, and this sulfide is attacking, and the OH minus which is getting water getting reduced and forming OH minus at the cathode, this is attacking here, and this part is going as benzyl alcohol, and this sulfide is generated. And this sulfide is getting oxidized again in anode to form the sulfoxide. Now what we can do further? But these all the reaction what we have done in batch processes. Batch processes for doing a new reaction is okay. But electrochemical reaction, if you do in batch process, the main culprit is the electrolyte requirement. Because your cathode and anode side here, ion have to move, you have to add electrolyte. And if you scaling up, more electrolyte will be required. That's a major problem. If we do it in flow, your cathode and anode will be nearby. So the ion movement, you can minimize the electrolyte requirement. Sometimes no electrolyte is required. And what I'm talking about, if we can do it in flow, so we can minimize the requirement of supporting electrolyte, and other all are the benefits of flow. Others are there, but electrochemistry, this is the main thing. So what we are thinking now, presently we are in the process doing this reaction in flow cell, generate the sulfoxide, and as I told, sulfoxamine drug. So we now at this stage, if we add different amines in oxidative condition, we can generate sulfoxamines. And at the same time, we are in the process of standardizing this same type of chemistry to make this pantoprazole, omeprazole, and other things. So this is our near future things we are trying. So what we show you today is six different electrochemical reaction which has been developed by us. We are working on many other projects. We have some results, some these things, and please remember, I showed you the standard condition. So there are a lot of variable to standardize a electrochemical reaction. Lot of variation of the cathode, anode, electrolytes, and current, potential, and so many things. So these six work we could do because whatever has been done, I have presented. This is our recent photograph when Majid got graduated. So he is Deborsi, who has, as I told, our story development. He and Majid, now he become paracetamol guy. So this they are majorly their work, and some part I have discussed from the Rakesh. And yeah, this was another photograph when one of our senior colleague Asit visited us recently. So all work, whatever has been done by them. What I am presenting, if I do some mistake, it is my problem. Whatever they have done, they are correct. They have done their own way. So blame is mine. And I wanted to thank the funding agency, the generous funding from ACRB, DST, and some part from BRNS and our IIT Roper, so that we can do whatever we have done. And this is our department building. It looks very nice. I again ask you to go through our building. So now coming inside, I'll ask later. So thank you very much for your kind attention.
Thank you, Prabhu, for the nice lecture. The floor is open for the discussion.
मैं कितना टाइम लिया? कितना टाइम लिया? Bye.
Yeah, fantastic. Yeah. So I have some questions regarding the flow setup.
Yeah, tell me. See, these are all whatever we are doing. These are our imaginary way. Some part we are doing some jugaad. We have not started flow chemistry. I need 45 lakhs rupees to buy the stylish electro that flow reactor.
Yeah, the jugaad, I think that's more interesting actually.
Yeah, that you tell me.
So, like the electrode you put very close. And
No,
then
that is a micro reactor. You have to have a flow path. From there, your things will go.
So that micro reactor you made yourself or that?
No, that we are buying.
That you purchased. Okay.
Other thing, the syringe pump, those were.
So like you are flowing the solvent to the syringe pump.
Yeah.
With some concentration of electrolyte.
Mm-hmm.
And then the micro reactor you purchase.
Mm.
Okay.
Thank you, sir. This is very nice presentation, sir. Sir, actually, I found so many electrochemical process you are explained.
Yeah.
But which one is the best exam that is cost effective for a researcher can adapt that process for formation or preparation of antibiotics and analgesic drugs?
Paracetamol, you need phenol and acetonitrile electrolysis only.
Only electrolysis. You are explained the so many processes. So
yeah, that is the reaction mechanism. What is happening inside.
Okay.
But process is you do electrolysis, you get paracetamol, you get nice solid compound.
Nowadays, the laboratory, the doctorate or whatever chemical laboratory, and pharmaceutical laboratory, they are processing employed this process.
No. This is in R&D, our R&D stage. We have to make them, see, no chemical industry will change their process just you publish a paper, okay? They have to do, first of all, money matters. They have to be understood that is a profit. Then they will see other parameters.
Okay.
So this is very initial stage. We are working, we have to show them it is profitable. Then we have to find out some company. That's very later stage, we'll see.
Sir, you are explaining the 5 processes. I do not remember that processes. The 5 processes for preparation of the product.
Paracetamol. Okay.
What are these processes? What is the difference between comparison? If we study the comparison study, then what we see the basic difference between them?
See that may. Can I go back? Yeah. You see, here it requires steps actually. Basic difference. First of all, these are all this amino alcohol was needed. Both these processes, the same type of processes. Here they are doing putting the hydroxylamine. The nitrogen was put in that through that reductive amination and other things. So it needs different steps.
Lastly, you point out the limitation, hazardous and environmentally corrosive. Why it is environmentally?
See, if you are doing more, see here you have to use H2F2. It's not easy to use in laboratory condition. And multiple steps, there are orthoisomers, there is isomeric. Here itself you get orthoisomer, means you will end up with mixture of product.
Sir, if this process is hazardous and environmental corrosive, why we employ this process for the preparation?
No other new process was available, that's what. So that was the cheap, because starting material was cheap. And they could make it reaction open flux and other things. But still now our Indian or other Chinese company, they don't bother about the hazard. They just dump it here and there. Now they started treating.
Thank you, sir.
Yeah, there's your slide number 39, that requirement of S-benzyl.
39.
Yeah, that's right. 39. Yeah, this when you are knocking out the benzyl group, so when you are carbocation generating, so why not use a simple thiol?
That doesn't work. That first step doesn't work. We have tried with dithiene, thiol, that doesn't work. Disulfide, it doesn't work. The disulfide itself we have added. If that also can do our job, but that doesn't work.
So, very nice work. Here.
Okay.
Yeah. So in these systems, everywhere it is passing through radical, many places I could see. So could you try to monitor it through EPR spectrum?
No.
Spectroelectrochemistry, like many systems are azo-containing compounds and those might be colored nature. So how, like, to predict reaction mechanism, if you follow the spectroelectrochemistry, it might give some another clue.
Yeah, we can do it. Can you help me on this? You have this facility here? Because we don't have that facility in our place.
EPR we don't have actually. So just I was.
Yeah, because in our region there is one EPR machine was there in IIT Mohali, that was also accessing problem. So we are having lot of problem. Indranil also knows. EPR is the issue in that region.
Another question is when two reactant, if you are taking, you are saying that current is increasing, right? So it might be acting as a supporting electrolyte. What could be the reason? Is it means like redox reaction?
Most of the cases, the larger increase what you saw, so you see those are mediated. Ferrocene, if you add, those are mediated, so catalytic current will increase. But the other case, substrate, sometime two substrate, if you see our reacting substrate. This case, really I don't know why it is happening like that.
Yeah, so that is the concern. I mean, electron, like current is related to electron, number of electron total transfer during the redox process. Something must be happening if you just follow the EPR and then this one.
The detailed same question yesterday I was talking in NCL. Some electrochemist was there. They gave me some suggestion to look after this. So I will look after closely. If we can explain this is the reason the catalytic current density is increasing. The quality of the manuscript and
it is not little bit. If you see, it is
here it is more. Yeah. Because the earlier example where you so little increase was there. Here it is more. Yeah.
Thank you.
Prabal, Yoshida also, Yoshida has done a lot of work in this electroorganic chemistry. One paper I saw in Yoshida's work is that he generates cation alpha to carbonyl, and then in the presence of DMSO, it gets oxidized to ketone.
So it's a recent paper.
That was there in JAX quite some time back. So in this case, you have generating a cation, which is para to the carbonyl, and also you're generating a sulfoxide. So did you observe a quinone byproduct in this? What is the limiting factor? Yield is sometimes good and sometimes low. Did you observe the quinone product? Is that the reason why the yield is affected?
We have not observed any quinone product. Maybe we are neglecting. I look into it very closely.
Yeah, Yoshida's work.
Yeah.
Thank you.
First of all, thank you, sir, for such an insightful talk. So, in one of the slide, you have showed that flow cell you have designed, or
we have. Yeah, that's what we want actually.
Yes, sir.
Yeah.
Yes, sir. So the design like you have made, or you have bought it, or what?
These are as he was asking me. No, this we are trying different way to get the thing. We have no success till now.
Okay.
So propose route. That's what if you see that tell.
So then you are using catholyte and anolyte. Like it follows the same mechanism of redox flow batteries. Like they are using external two different tanks. One is catholyte, anolyte. So are you following that mechanism? Like You are.
If you tell me that one, I also learning from you. I have just started these things. We have not. We are building it up. Maybe next time I'll be able to tell all these details.
Okay, thank you, sir.
Yeah, please. No. Electricity just we have started. Now we use DC power supply. And no. That with electricity electrodes, it is not our job. Those are all coated electrode. You use 2 times, everything falls up, falls down. Now we make electrode our own. We cut it. We get vials for the magnesium vials, copper, graphite. We cut it and we use.
Okay, please join me in thanking Professor Prabal for the wonderful talk. And on behalf of the organizer, a small token of memento to Prabal.
Sorry.
We move to the next speaker, Dr. Vijay Krishna Gari, and he's the host speaker. So hope most students will be there because you are a teacher. Okay. And he did PhD IIT Madras, Professor Sundararajan, and later he went to actually he joined IIT and before he moved to IIT Bhubaneswar. With this brief introduction, I request
Thank you, Dr. Chairlatan, for introduction. And I would like to thank Dr. Abrej for giving this opportunity to present my work. Actually, by looking into the theme, I thought like, okay, I'll be discussing something about the green chemistry and all. But later I realized that in yesterday's plenary lecture, so Professor Mehta has discussed in detail. So my job is easy. So simply I'm skipping that an introduction part and directly I'm going to my present work. Basically, we are making different functionalized polymers. So there, like we are using these functionalized polymers for doing some catalysis. Making some membranes for gas separation, or also we use these polymers for self-assembling and then drug delivery systems and all. We also use some functionalized polymers, resins for separation chemistry. And today in my talk, I'll be discussing more about the first topic, that is chiral and achiral polymers for organocatalysis. If time permits, I will be discussing the other parts very briefly. Okay. So I don't think the audience need any special introduction about the ionic liquids. So let me skip on to the next one. Like basically our work, 90% of the polymers what we use is polyelectrolytes. So we call them as polyionic liquids. So the main idea of using these polyionic liquids is like you will be having all the good properties of ionic liquids as well as the polymers. So you can combine these properties. So this polyionic liquids is quite some time. It has been used in different fields, starting from nanotechnology, sensors, catalysis, drug delivery, and the energy, especially like batteries, lithium-ion batteries, whatever we are using, are the gel electrolytes that we are using in lithium-ion batteries are based on these polymers. So I will narrate like how our curiosity-driven reactions has taken us to the next level of making these helical polymers. First, what we have done is we prepared a simple polyionic liquid by using a controlled technique. And this polymer we used for very basic organic transformation reaction, that is Diels-Alder reaction we have done. And it is well known reaction, and even the simple Lewis acids will catalyze the reactions, or ionic liquids are also reported. So just we has reproduced this reaction by using our polymer polyionic liquid. So the yields conversions seems to be quite similar, but what we have observed here is the regioselectivity is improved in this case. In the case of its identical monomer, ethyl methyl imidazolium, where we got like 58:42, and that has moved from 58 to 76. So something is happening with these polymer systems. So that's what we understood, and the mechanism is the same as that of the ionic liquids. Okay. So the next one is like how they are going to happen if you take the polymers to the resins. So what we have done is the same kind of monomer that we have used, and used some cross-linkers and prepare this cross-linked polyionic liquid. And then this cross-linked polymer we have used for the preparation, and then used repeated the same reaction, how it is going to happen. So this either when it is homopolymer or a cross-linked polymer, more or less we got the same kind of regioselectivity over there. So this encouraged us to work on how about the enantiomer selectivity. Okay, it is giving reasonably good regioselectivity. Can we get some enantiomer selectivity if you can induce the chirality into the polymer? So that's how like we initiated doing some chiral polymers. Okay, and the chirality, if you see, like first we introduced the chirality at the anionic site. So first we prepared the chiral monomers with the ionic liquid monomers with chiral anion, and then we polymerized and we got these polymers. So what we observe is like when you take this polymer, when they are achiral in nature, so they are like random coils. Once you induce the chirality into the system, so we can see that there will be a good helical morphology into the polymer systems. So that's what we have observed here. So for example, if you see this is a chiral polymer with bromine or hydroxy as a counter anion. It can be vinyl imidazole or DADMAC based polymers we have taken. So they are like chiral systems in that when you see the CD response was not that great. But once you introduce the chirality into the system, you can see very good response into the CD, that too with when you change the counter anion with different enantiomers, then you will get the opposite loops that you can see over here that clearly says that, yes, these are the helical systems and having opposite handedness they are having. That's what we observed. Then we thought of using these chiral helical polymers for carrying out the catalysis. So simple Bailey-Hillman reaction that we have done. Of course, we got the enantiomer excess, but it's very less, like hardly like 25 to 30% enantiomer excess that we could get. But the interesting thing is like when you are having a different kind of helical systems, we got opposite enantiomers. So that enantiomeric switch that we could get by using these helical systems. So this is initial encouraging results that we got. And similarly, like same kind of this helical chiral polymers, we thought of using them as resins and then see how that is going to work. So the same principle we have used. Again, we use some cross-linker and we prepared cross-linked chiral polymers now. So previously, they are achiral polymers. Now you convert them into the chiral polymers, but now they are not homopolymers. They are heteropolymers. So their morphology is completely different as that of the homopolymers. So you have to carry out this reaction as heterophase. Okay, it's not like a biphase what we have done in the previous case. Okay, the advantage of using either a homopolymer or a resin is that you can carry out these reactions in multiple times. So recyclability will be there. Recyclability and is there like 4 times that we have done reused. And here, if you see, like conversion seems to be quantitative, but the enantiomeric excess has dropped down drastically. Previously, it was at least like 30% we are getting, but here we got only hardly like 7-8% we could get when it is in the resin form. So from this, what we realized is like, yes, we need to have some helicity into the systems. Okay, so when it is in a homopolymer, when you take the chiral polymers, homopolymer, so we are having the helical nature, that helicity is really playing an important role. Once you convert them into resins, what is happening is like you are having the polymer, chiral polymers are attached in between the other functional groups, so that you are not having the helicity. And since the chiral polymer losing the helicity because of the 3D network, so that enantiomer excess was not as expected, or it has gone down. So then what we have taken as a next project is, okay, let us prepare a few more helical polymers, chiral polymers, and then get a better helical structures. So that encouraged us to prepare some of these chiral monomers. Now this time we want to have the chirality at the cationic side. Previously, if you see that, those are the chiral polymers or the resins where the chirality is at the anionic side. So maybe we thought if you are introducing the chirality at the cationic site of the polymer, then you may be having a better arrangement of these polymers, and you may be having a better helical nature. Okay, so with that, what we have done is like we prepared this polymer, okay, chiral polymer, but the counter anion is here when it is a chloride. So almost like okay, it showed good specific rotation, and when you're having different enantiomers at the main chain, so they showed like opposite specific rotations, -100 and almost like +100, close to that. So that shows that the chiral center is intact to the polymer, but how they are arranged, what is their morphology, basically that you can understand by looking into the CD or the TEM or SEM. So when we have taken that, the CD, recorded the CD, so almost like the response was not there as expected. Then we change this chloride into the corresponding hydroxy. That is the beauty of for these ionic liquids. Okay, I'll be discussing more about this. You can play around these polyionic liquids. You can play with their counter anions or the alkyl side chain groups or functional groups, so that you can tune their properties as per our requirement. You can really do the tailor-made polymers as you required. So that's what we have done here. Just we knocked out the chlorine. We did simple anionic metathesis. So you get the hydroxy counter anion. Then you can see that, okay, very good response that you see. And when there is a change in the enantiomer centers here, so you get the opposite loops. Okay, for example, if you are getting the first one, if it is response is here, the other one is in the opposite loop. So that shows that when you change the chirality into the system, so the morphology is completely different. Then the hydroxy is replaced with chiral anions. In those cases also, the helical response was quite good. So then if you see this, in this case, the functional group, what we have used here is the ester. So just we want to see how an acid system will be working, but really we are surprised to see that when it is an acid functional group, so the response in the CD was not as great as we expected. So from this, we understood that definitely the functional groups also playing very important role, whether it is in a cationic, the main chain or the side chain. And yes, of course, like in which solvent that we are taking, that also played very, very important role, because these are the polymer systems which has to align. So it will really take long time for the polymers to go into the solutions. So we want to see like what is how the solvent is going to influence this self-assembling. So we have taken these chiral polymers in both like water and methanol. You can see that the response was great in methanol, in water compared with methanol, saying that, okay, the alignment is much, much better in the water as compared with the methanol. Okay. And as we said, like when we have taken this acid functional systems, so it had a good orientation, morphology. So we thought maybe we can have some salt effect maybe there. So we studied how this varying amount of the salts were added to check, but we didn't get good response over there. Then we are curious to see like how these polymers, chiral polymers that we have synthesized will appear in the SEM. So some of the cases we got some helical systems. So you can see these are different chiral systems. Basically, like they are the SEM images, but what happens is like these polymer systems will be having a good orientation or assembling when they are into the solution. So, but when you take that for the SEM image, basically like you have to take the solids. So that's why the arrangement may be not that great as we are expecting. So we want to use the TEM, that too, like cryo-TEM will be giving a exact morphology of these systems. So you can see that when the polymer are a chiral completely, like the TEM also is like featureless. Slowly, when you are changing the counter anion to the hydroxy and the other chiral centers, you can see that there is a good change in the morphology towards the helical nature. And this is very interesting to note that. So when we change the counter, means this chiral center into the polymer, in one case, like we got the right-handed helical structure, and the opposite enantiomer is giving the left-hand helical nature. So by using these kind of helical systems, either right-handed or left-handed, one can tune the outcome of the organocatalysis that happening on these helical polymers. So this is the take home from the first part of my talk. Yes, the chiral polymers can be prepared by introducing the chirality either at the cationic site or the anionic site. And the helicity is very, very important in order to have the enantiomeric excess in these reactions. But one thing is very important, that the counter anion or the cations, so they are playing a very important role. And of course, we have to come to a conclusion how these functional groups are chirality in these systems are playing. For example, if you're having amide groups with or only alkyl groups here, or we want to convert them into hydroxy and see like how these functional groups are really influencing the helical nature of the chiral polymers. So my PhD student Tilottama is working on this. So except these 4 and 2. So remaining 16 into 3 or 4 sets of chiral monomers, and then the polymers she has prepared. I have shown only the polymers. First, we'll prepare corresponding the monomers, and then change the counter anions here. X I have showed that will be chloride, then has to do the metathesis to hydroxy, and then different chiral anions that we'll be using to prepare a set of chiral polymers. Okay, so this study is underway. Like she has prepared 16 into 3 sets of these polymers, and we are studying how these functional groups are influencing the helical nature of these polymers. Fine, I have shown like these chiral polymers and all, but we need some tools, right? We need some tools to convert these monomers into the polymers. And what kind of tools that we use to polymerize this? Okay, so converting a monomer into a polymer, like anyone can do, like it's a child's play. Basically, that's what I say. Like, but the main important thing is when you are converting a monomer into the polymer, the important thing is like we should have a good control, and it should be reproducibility should be there, and at the same time, like there should be narrow dispersity. So hence, if you are doing a radical, simple radical polymerization, or if you throw the monomer outside, even thermal polymerization can happen. So that cannot be having a good control. Dispersity will be very high. So for that, we need some controlled techniques. So there are n number of control techniques. what we follow is a radical control technique that to raft process. This is what we use, reversible addition fragmentation chain transfer. So this is a good controlled technique process by using which one can get a good control over the polymers. The advantage of the raft technique is we can carry out these reactions in water, and you might have seen like we have prepared a different kind of chiral monomers and polymers. So there you will be having acid, amide, esters, different functional groups. So it can vary from acid to the base. So they should be the whatever the agent that we are taking, the technique that we are taking, it should be stable at that conditions. So these are very tolerant to different functionalities. Hence, we choose this one. Okay, and this is also not like that simple. Like, okay, you have chosen one technique, but so which kind of raft agent or CT agent that you are supposed to use for doing this polymerization? So when you take these monomers can be classified again into further like low activated monomers and more activated monomers. So based on that, like when you're having the double bond conjugated to carbonyl system or aromatic systems, you call them as more activated monomers. And such a conjugation is not there, you call them as less activated monomers. So in that case, like less activated monomers, you need to have this low chain transfer coefficient. Only then you'll be having a good control. So basically, dithiocarbomates or xanthate-based raft agents will be suitable. So for this, okay, we prepare a different kind of raft agents. So I say like these are the tools. So they can be like morpholin-based systems or immerjolin-based systems. So these are switchable raft agents. Just by changing the conditions, we can use them for the polymerization of both less activated monomers and more activated monomers. So these are another set of raft agents that my PhD student Haribabu has prepared. So they are like monofunctional systems or difunctionalized systems. So here, why we have prepared this many number of raft agents is like, so though dithiocarbonates will be good for less activated monomers, but again, you have to play around with different functionalities. Okay, maybe if you go back, I can tell you like, so when you are having different Z group and R group, so this is the one like you call this as a leaving group. So when you are having different leaving groups, they should be in a position to reinitiate the process, polymerization process further. So hence they play a very important role. And same time, the Z group, what we take, so you call that as an activating group. So that will dictate how the polymerization will proceed when you change from a monomer to the monomer. Okay, so that's the reason why we go with different functionalities. So when you are having this difunctionalized system, what happens is like one can prepare different architecture. So I'll just quickly run through this. So we prepared different less activated monomer. So vinyl acetate is one such less activated monomer. So once you prepare the polyvinyl acetate, from this you do hydrolysis, what you get is polyvinyl alcohol. Actually, this is extensively used biodegradable polymer for most of these drug delivery systems. What they use is this biodegradable polyvinyl alcohol. So this is the starting material. For this, the main challenging is to have a good control, and one can prepare the polymer with high molecular weight, say like more than like 1 lakh, 2 lakh Dalton molecular weight. If you can produce with low dispersity, that will be the great. So we are in the process of searching a suitable raft agent for getting this, and yes, we are having good control, that I can say. So 1.1, 1.2, so we are having very good control. Similarly, other less activated monomers we are preparing here are like NVP, N-vinyl pyrrolidine, or vinyl imidazole. So this is our starting material for making different chiral polymers. So part of my first talk. The idea of making this difunctionalized system of raft agent is one can get the block copolymers that can be like ABA block copolymer or BABA block copolymer. So for example, if you see like when you are adding the monomer A and B, then what you get is ABA. So inside the monomer will go and inside. So when you change the type of the raft agent by same sequential addition, so instead of getting ABA, what you get is BAB. So like you can have a different architecture based on that, your applications also will vary. So that's what we have been doing. So we prepared some block of polymers. So why we need these kind of block of polymers? So they can be used in different applications. They can be like elastomer preparation, especially we use this ABA kind of block of polymers. And even we can use them for making some self-assemble systems. So this is pinipom, polyanvinyl pyrrolidine and vinyl acetate block of polymers. So you can see that slowly, like by changing the selective solvent, you can make them into self-assemble. And these block of polymers, especially when you take like amphilic systems, so they will try to self-assemble. For instance, you simply take one is polystyrene and polymethacrylic acid. So this is hydrophilic and hydrophobic. So they will self-assemble into micelles, vesicles, reverse vesicles. That depends upon the hydrophilic mass fraction. Okay. So when you are having more than 45% hydrophilic mass fraction, they form spherical micelles, 25 to 45 vesicles, and reverse vesicles. So we also like used our functionalizer system to self-assemble. As you can see, like how they will self-assemble in TEM images. As a proof of concept, like they can be used for storing the materials. As a proof of concept, what we have done is we use this kind of polymer for water, dye entrapment or water equation, I can say that. So this is the Bengal dye, which is present in water and DCM. Now, what we have done is this amphilic polymer we prepared, which will be having solubility into the DCM because thanks to the long alkyl chain. So the moment we add small amount of this amphilic homopolymer into the DCM, so you can clearly see that water will become colorless and the DCM will be becoming colored because this dye, whatever is there, it is entrapped into the these self-assembled systems. So not only these kind of polymers we can also use for making some membranes. Okay, we use these imidazoline-based systems for making different kind of membranes. Okay, so the main idea of this is like ionic liquids are known for this gas separation, but so that the copolymer will be giving the stability when you prepare the membrane, and the ionic liquid is the one which will take the ionic liquid. So if you can have more than like 50 to 60% of the ionic liquid into this membrane, then it will act as a very good membrane for gas separation. So we are working on that. And these kind of polyionic liquids also having good ability to stabilize the metal nanoparticles. For example, you know that ionic liquids are known to stabilize simple nanoparticles by electrostatic means. The polymers stabilize by steric stabilization. But these polyionic liquids, so they'll be stabilizing in both electrostatic as well as steric stabilization. That's the reason why, they will be having a good lifetime, and we can arrest the aggregation. So we prepare different kind of nanoparticles, okay, which will be into the solution. That is the beauty of this. And same time, you can tune the properties of the synthesized nanoparticles. Okay, even you can tune the size of the nanoparticle as you can see as per the requirement. So when you prepare these nanoparticles, how you prepare, that is also matters a lot. Like, for example, if you are taking simple ex-situ preparation or in situ preparation, so they also will make a huge difference over there. So, and one very interesting property that I would like to bring to your notice is you can prepare these pill stabilized nanoparticles, and you can take them to a tour from aqueous to the organic and organic to aqueous, again back. So this is around cycle that you can take them. For example, these are the silver-based nanoparticles stabilized by polymers, so they are completely homogeneous in nature. So depending upon the size of the nanoparticles, you can see that they'll be having different colors. So next, what we have done is like you play with the counter anion, you kick out the chloride or hydroxy, which is hydrophilic, then you convert them into entriflates. Once it become entriflate, that is, will be hydrophobic in nature. So what is happening is you can see that now they are in water. Now I am adding entriflate and a small amount of the organic solvent, that is ethyl acetate here. Now you can see that the aqueous portion is becoming completely colorless, means the nanoparticles has moved from water to the organic layer because the organic layer containing the polymer. So the polymer is taking your nanoparticles. So this is not like only one way. You take these nanoparticles from aqueous to the organic, but you can take back also. It's a round trip. How to do that? Again, you do a simple anionic metathesis from entriflate to again bromide by adding simple lithium bromide. So again, as you can see that the nanoparticles will come down thanks to the polymer having the bromide as the counter anion. So this is very interesting phenomena that you can observe. So by this, what we can do is like you prepare these black polymers, you can stabilize the nanoparticles so that you can control their activity. So wherever you want, like if you want to block these nanoparticle or stabilize by core or shell, that can be as per your requirement, we can make it. Okay, what is the main idea? Why we are using these nanoparticles? This is not like fancy to just stabilize the nanoparticles and see. So there is some purpose for doing this. You might have seen that the properties are varying when you are stabilizing these nanoparticles with the polymers. That's what really we want. We want to tune their properties. The lambda max is changing, its surface plasma resonance is changing. So that means, so there is some changes are happening once you stabilize the nanoparticles. So if you see this, these are old reports. When you take simple nickel nanoparticles, so it will be reducing both carbonyl group and olefinic groups here. But when we used our pill stabilized nanoparticles, okay, we don't need any external KOH, but reactions are a bit sluggish. That's what we want, because once the reaction is sluggish, what happens is the catalyst will be having a discrimination power. So it can discriminate these two functional groups, and selectively it is reducing the carbonyl group here and without reducing this. So that's what, so though this is a nickel system, why this is happening is thanks to the polyionic liquid which we have used. So that is really playing an important role here to tune down the activity of the catalyst system. Okay, so which can be used for several times and reused and recycled. Of course, like hardly I will take a couple of minutes to complete. So just I'm running through what other work that we are also doing. Apart from that, we also preparing different PEG-based dendrimers. Okay, and these dendrimers we used for doing some cancer cell line studies. And we also prepare some PLGA-based biodegradable sutures. So having gentamicin into that. So as you can see that these are the material used for preparing the sutures. So after say like 40, this is after 42 days, you can see that some whole cavity is formed onto that material. So those cavities are because of the leaching out of the gentamicin drug which we have taken, and slowly it's degrading also because this is a absorbable sutures. So this is one set of system. And finally, we are also using the different functionalized polymers for the separation chemistry, especially the lanthanides and actinides, which we have done some a couple of projects for IGCAR and UGC DAE. Actually, this TBP or CMPOs they're well known for liquid-liquid extraction of the lanthanides and actinides. So being a polymer chemist, what we have done is we hook up these kind of monomers into the polymers, and then prepared the resins, cross-linked systems, some MIPs, and then we use them for the separation of these lanthanides and actinides. And one good success story is this: we could separate the uranium and thorium by using our resin systems. Okay, this is a sequential separation. This is the HPLC, so you can see that the first fraction we are having only the thorium, 99%, and the second fraction we are having 95% purity. You can see small amount of the thorium, and in the third fraction we got more than 99%. So purity of this one. So we could really separate these uranium and thorium successfully by using these resin systems. So this was our successful story. We gave like half a kg of our resin to the IG car. So with that, I would like to conclude. Yes, in IIT Bhubaneswar, we use to prepare different kind of functional monomers, task-specific ionic liquids, and then we prepare different raft agents as a tool for polymerizing. So once we polymerize, what you get is a chiral homopolymers, black polymers, or the resins, and we are using those chiral polymers, homopolymers, resins for different applications. So with that, I would like to thank all my students. This is my past research group, 6 PhD students, and this is my current research group. And they are my collaborators. And I also would like to thank the funding agencies for the support. And thank you all for your attention.
Thank you for the nice presentation. The floor is open for the discussion.
Water? Yes, please.
Yes, interesting talk on imidazolium-based polymers. I'm particularly interested to know this. What is N value? N in the first part of your talk.
Okay, N?
N value. N is equal to 1,000, like 100.
Okay. Yes. Basically, here what we have prepared is like 50 to 100 DP, degree of polymerization. So 50 to 100 repeating units we have taken. So when we speak about the helicity of the systems, that is more than sufficient. That's what we have done. We studied by varying different molecular weights, and we optimized that around 50 DP is enough.
Second one is what is the physical appearance of these polymers? Like liquid, gels or solids?
Yes, these are imidazolium systems are solids. They are like powder.
It's like powders.
Yeah.
Powders.
Amorphous. They are amorphous.
The last question is that these nanoparticles, silver nanoparticles. So there is normally in the literature it is reported that carbines, typical energetical carbines also stabilizes different transition metals in nanoparticle size. So what kind of bonding interaction we can imagine between the particle surface area with these imidazolium salts?
As I have told you, like you will be having both kind of electrostatic stabilization and steric stabilization. And this is more like, since you are having a long polymer chain, you will be having more like a steric stabilization. And within that, you will be having electrostatic. So when you see these SEM images of some of our field stabilized nanoparticles, you might have observed some good morphology and all. There you can see that nanoparticles are embedded inside the polymer. It is not like nanoparticles are more like polymers are here and there. It is the other way. Like you are having a polymer, and in that you will be embedding your metal nanoparticles. That's the reason why they will be having more stability, and the lifetime also, like shelf life is more.
Thanks.
I just want to ask one thing. So now you have been into this helical polymers, and these are basically a single helix polymerizing. A single helix, right?
They are double helix, what we observed in our
Can't
case.
we all? Can you take this idea forward and make double, triple helix kind of thing?
No, what we got is a double helix, sir.
Oh, you got double helix.
What we got in all our cases, we got double helix only.
Double helix.
Yeah.
Achha. So these are double helix. But the pictures that you showed is like single helix. If I'm not wrong. Oh, I see. Yeah. Yeah. So what is the driving force for making this double helix?
Yeah, actually, you should give some more time. We are studying that only, like what kind of interactions are there, how the functional groups are affecting that. We are studying.
I see. So these are also having this kind of major group, minor group, everything.
No. So
Not
this
like
is simply you are having this. If you see our polymer system, you are having different functional groups. Same time, the chiral group is there. So you are having one kind of electrostatic interaction, whether the hydrogen bonding is driving or electrostatic interaction is driving, that we are trying to establish.
Okay, thank you.
There is no more question. Please join me in thanking Dr. Vijay for the nice presentation. Thanks. On behalf of the organizer, I am handing this moment to Vijay.
Thank you.
Thank you. I would like to thank taking time. Okay, please join me and once again thank you for the speaker of the last session.
I would like to request Dr. Kaushik Samanta to felicitate Professor Perucharalathan for chairing this session. Thank you, sir, for the gesture. With the extremely insightful lecture by Professor Banerjee and Professor Curry, we now come to the end of the final session of the two-day workshop. Before concluding the workshop, the organizing committee has arranged for a panel discussion with the eminent experts. I request all the participants and delegates to kindly join the session on how to make an impactful manuscript, research proposal, and statement of purpose. I would like to invite Professor B.K. Patel from IIT Guwahati, Professor Shantanu Mukherjee from IIT Bangalore, Professor Akattu Biju from IIT Bangalore, Professor Indranil Chatterjee from IIT Rupar, and Professor P.C. Ravi Kumar from IIT Bhubaneswar on the dais for the panel discussion. So please come on the stage for the panel. Please. We are sorry to inform that Professor B.K. Patel is leaving. He has some urgent work. So I would like to invite Professor Madhusudan Maji to join the panel discussion. Thank you, sir.
It would be nice as we have some of the eminent experts, as you must have witnessed in the last 1.5 day. Okay, so these eminent experts, they are not only, renowned for their research, but they are also affiliated with several, on the editorial board of several journals. So if you have any queries related to, how to draft your manuscript, how to write your research proposal, how to, draft a very impressive statement of purpose, anything you have query, we have the expert in front of you. You may feel free to ask and, make a, good point on organizing this panel discussion. Yeah.
Good evening, sir. I'm Manisha. I'm from MSc Chemistry, IIT Bhubaneswar. So I have a question regarding that how after few months we are going to face PhD interviews, even interviews regarding job placements and all. So how to reduce the phobia of giving an interview? Means we know all the concepts and all, but when it comes to facing an interview, we on the interview table we forget everything. There is a certain phobia for communication. So sir, how do we reduce this phobia?
So there are few tips. One thing is that you can talk to your seniors who have cleared such interviews, and then you can ask them to give a take a mock interview for you. So they can take a mock interview and types of questions they ask. So you can practice. There is a word, practice makes man perfect. So you have to actually practice interview also. Okay. So when you practice more times, what happens is that you get little comfort. So that actually reduces a lot of stress, initial stress. Most of the thing that you say is because the initial stress level will be very high. So when you make a small mistake during that time, the stress level shoots up so high that everything goes blank. So you have to really practice, even interview also. So the only people who can help you in this is the senior students who have cracked those interview situations. So the more you talk to them, the more tips you get, just like the one that I said. So there may be many more tips. This is something which I think can help you. Another thing is that you can go to that institute a day before, and then you can also get yourself comfortable with the place where you'll go sit. And then if you talk to the people who have interviewed, before interviewed, so they will be able to give you some tips. Like most of the time in interviews, we ask the students like which topic you are comfortable. You have to be very careful in choosing your topic. So you have to choose in topic in such a way that you are really very comfortable. Okay. So these are some of the things. I would like to give it to some others. Yeah.
I want to add two things here, like what I observed during the interviews. First of all, like who are sitting here or your professors or anywhere, we want you to answer. It's not that you can sit down, please. So we want you to answer whatever we are asking. So we start with something very simple. The question is, as you told, like you know many things, but when you are appearing for the interview, you feel like you are blank. You ask why. Okay. I think one answer will be you are scared, like who are sitting there, maybe like what type of questions will come. So first thing you keep it in your mind, like the people who are there sitting for your interview, they want you to answer. Okay, first, okay. It's not that we are going to ask something which you cannot answer. We want to ask something which you can answer. Okay, so we start with very simple thing, but most of the time I found like student, because they are scared or this thought already preoccupied in their mind, so that give you the trouble. Okay, as PC also mentioned, like feeling comfortable. I can ask you like, yeah, here we are almost 2 days going to over. How many professors or how many like your faculty member here you have interacted? Okay, maybe you want to talk with them, but you feel like if I ask, what will happen? It's like feeling yourself comfortable there. Okay, if you can make that situation like you're comfortable there, and I am sure that you can answer the question much easily. Okay, at least I did during my student life. I don't scare much. Okay, I know something. Okay, they will ask. I take like few second pause. Okay, or deep breath. Then I say, okay, I know this. I start slowly, and in the throughout the interview process, your professor also help you. Okay, like you know something and you start, okay, from there, and then slowly you approach your answer. Okay, so in this way you can, I think you can answer at least partly, and then you get some hints, you end up. But most of the time student, what they do, they feel I don't know, like, yes, no, on off situation. Interview is not on off situation. It is something you approach, we help, it proceeds slowly, and you want to know your thought process, your approach is good or not. It's not your answer. Sometimes your answer may be wrong, but your thought process is good, you're also given the marks. So you need to approach, and you think again, like we are sitting there in the interview not to like prove you don't know, rather we want you to answer something. Okay, so that is very important. At least I would say like this one. If anyone else want to add, please.
Yeah. So yeah, in addition to what Ravi and Madhu said, so what I feel is that when you plan for attending an interview, before that you consider at least 5-6 institutes in the country. Don't rely on one institute or one research group in a particular department. So just keep your options open, multiple places, multiple research groups, and that will help you in a different way, such that say in one place, if you are not really interviewed well, you can understand what are the difficulties or where you went wrong, and that you can help in the next place. And in many places, as Madhu correctly said, so we did not expect a student to answer to all the questions. So the way you attend the question or the approach, that is more important. Rather than completely answering. And we also never ask any difficult questions. Many times students feel that interviews, they ask sometimes the structure of natural products or very difficult, complicated questions, but we ask from the very basics. So for an PhD interview, maybe a second or third year BSc level, we start. So you can imagine the very basic level we start, and then depending upon how you answer, the question can be to the advanced level. So be confident, be pleasant, and just make sure that the people sitting on the other side of the table are very friendly. So that also will relieve some sort of tension out of you. So yeah, that's it. Indran.
Yeah, do you know Don Bradman, the famous cricketer?
Yes, sir.
So when one journalist asked him that, so what is your lifestyle before going to the pitch? And he told that he spent a very natural lifestyle. Okay. So the first thing you have to do, you have to be relaxed. Okay. Second, there are two kind of people who are nervous. One, he or she doesn't know anything. They will never be nervous. You are nervous, your heartbeat and pressure is high because you are serious. Okay. So you are one step forward. Now about how to relax, what you can do, you can talk to yourself in front of the mirror. Okay. So that you will feel that you can speak very naturally, normally, and you can see also your body language. And the best thing is practicing that, like what we are sitting here. So you with your batchmate, you just try to have a mock interview. Okay. So it is better with the batchmate, and then what you can do, you can choose different topic so that many people, suppose 5 people have 5 topic, and then you gather all the knowledge. Okay. So yeah, one interview cannot change. I don't think it will change your life much. Okay. And throughout your life, you will have to give a lot of interview. So first things, you have to cool down, relax. Okay. And then you will, I think you will succeed.
Yeah, almost everything is covered. So you are in your third semester, right? So how many?
Third semester has been completed, sir.
Okay, very nice. So how many courses you have taken so far?
So in the total all
MSc here, IIT.
MSc,
So far?
I think so, nearly 15.
15. And every course is, I'm assuming, 3 exams per semester?
3 exam. In some there are 4, 5 or.
Right. So let's say approximately you have written 50 exams so far in IIT, right? You know, when I got into the IIT, I used to have this, I was afraid of exams. When I finished IIT, I was not afraid of exam anymore. That's what IIT system does. Every course, they will have 3 exams, 2 quizzes, 1 term paper, presentation. And then by the end of 4th year, you were thinking, oh, exam is just natural thing going to the class. Okay, so, but what others said that you are worried because you are serious. That's what Indranil told, right? So if you do not care, you wouldn't worry about it. Like, okay, I mean, whether I pass or fail or succeed, doesn't matter. Then there is no worry. You are worried, you want to succeed, right? And then exactly what Madhu said, like most often when we ask a question, we do not expect the final answer from you in the first attempt. We want the approach. That's why hints are given. We want to see whether you can take the hint and proceed further. We can give more than one hint. If we see that after taking the hint, you are answering everything or your thought process is right, that's good enough. Okay, so don't worry too much. Just relax. You have written enough exams than many other people. Okay, possibly those who are interviewing you. So there is no need to be worried so much.
Thank you, sir, for your advice. And there is one more question regarding organic synthesis. Like sometimes if we are synthesizing an unknown molecule and it has many chiral centers, so how can we determine the R or S configuration of that chiral center? And it is a newly synthesized compound, so we don't have any literature regarding it. So sir, how are we going to know the stereochemistry of that molecule?
Okay, so well, I'm assuming that you are starting from your achiral compound. Okay, achiral starting material can be 1 or 2 or 3, whatever. You are going to the final compound with multiple stereocenters or 1 stereocenter, right? If that is the case, then so there are 2 types of stereochemistry, right? One is relative, other one is absolute. So relative stereochemistry, you can try to establish through NMR by NOE and all, checking the J value, for example, or other things. So you can figure out there are ways. When it comes to determining absolute configuration, X-ray is one of the simplest way of doing that. To have a heavy atom, checking anomalous dispersion, that's the best way of doing that. There are, of course, more sophisticated probes like copper and so on in X-ray diffractometer, which can give without even heavy atom. So that's, again, simplest way of doing that. Another thing what we do is also try to see if we can convert the product into something else which is known in the literature, and then compare that optical rotation with those compound. That's the second way of doing that. And third is if the compound itself is not crystalline, maybe it's a liquid compound, you can try to derivatize with something which will make it solid, and we can crystallize it and possibly containing a heavy atom. So these are some of the common method. Now there is a another method people use, so-called vibrational circular dichroism, and then compare with the calculated one. I have seen literature, people use that. They're not always foolproof. It is coming up, this technique, but the main problem is most of us in India, we do not have access to a VCD spectrometer. So that's the limitation. And yeah, and many times I see that they have shown a compound that calculated VCD spectra, and then the experimental one, they say it's a match. I mean, to me, it doesn't look like a match. So I don't know how they do that. So that's a powerful technique, but it's probably still upcoming. I don't know if anybody else thing to say.
Thank you, sir, for your advice.
Thank you.
Good evening, sir. This is Vidyantu Kumar, and I have a question that why India is not getting Nobel Prize? Is there any reason or anything in we are lacking?
I don't know if I'm qualified to answer that question. I don't know if anybody else has any. I think that's, yeah, I don't know if
Are we
can
lacking
answer
in
that.
anything?
Huh?
Are we lacking in anything or like?
It's a process. It's a very difficult question to answer. I don't know. I mean, I don't know how to answer this question.
Yeah, sorry, maybe I can try to answer that question. So one reason, if I criticize all of us in general, so we do only incremental science. Okay, so that's one reason what to answer you in a different way. So the conceptual developments from our country is still lacking. So the moment, but now it is a very good sign. We are moving towards that direction. So at least I can tell you organic chemistry in our country is really flourishing. So it was not the case maybe 15 years ago. So now it is there is a change happening now. So I hope in the next 10 years, this following others' work will change, and people in our country also will start thinking about conceptual things, and that probably will change in the next outlook in the next 10, 15 years, possibly. Yeah, maybe you can add.
Sir, I have one question. I am a state government lecturer in Odisha, in chemistry, lecture in chemistry in Jajpur district. Actually, when I faced the interview, different assistant, you already passed that position, assistant professor in chemistry in different university, NIT and IITs. I know that all professor are tell that the paper is your godfather for selection of the process. Is it right for the paper? If the publication is more, the impact factor is more impact factor publication you have, then you will get more chance. Is it correct? If another skills also have, if the analytical skill and every skills are there, if in students, then why it will be considered for a paper? Because I see that the experts in the not in there are chemistry in different fields, environmental, industrial, organic, and analytical, so many environment fields there. But the expert are the only 2-3 which are organic, inorganic, or physical, whatever may be. But if you as a candidate is from analytical chemistry or in environmental chemistry, there is no chance for that candidates. So what is for this process? You suggest me which process if we adapt for getting the assistant professor in chemistry in everywhere? Very typical question, sir. Please answer me.
It's indeed a very difficult question. Probably I am
You sir already passed that process, sir.
Yeah, no, I'm saying this is like I took the microphone just to say something, not to answer your question. Rather, I want to place it in like this, that what I say to my student.
Yes.
Because already 6 PhD produced from our group, so we used to discuss the same thing, and what I used to say them, whatever you already asked to the point, like whether number of publication, impact factor important. Yes, it is important. Okay.
More impact factor.
No. I'm saying it is important, but it is not only thing which is important.
Yes.
That many times, like as an applicant, we miss. Okay. What I would add here, there are 3 factors I give my student as to achieve that target. One factor is how you have grown, means gone through, starting from schooling, how you have learned BSc, bachelor's, master, PhD, postdoc, if postdoc required. So that is one thing, how you have gone through, okay? What did you learn? That is one thing, your background and CV is one third. Second thing is, you have published, you have learned, how much we understand the subject. Like as a candidate, I'm talking, I'm not giving you an answer, rather what I tell to my student. So the understanding the subject, like when we face the interview, we get several questions, okay? Also before that, you also face the interview in the department level. There will be thorough processing, okay? We are giving talk, we are also demos teaching. After teaching, how we are teaching, what are the questions we are asking, how he is approaching, all this process comes, and that actually how that one third I mentioned earlier, like how one
Sir,
can.
actually they're emphasizing in paper, on paper, not a demo, anything.
No, I think I don't know like what you are telling, but this is very important for like way I have gone through. Okay, so that is also we need to take care. Like, and also the if you are going to a research institute, so what proposal you are writing?
Now, when I go to the before in 2019 in IIT senior technical officer, yes.
Yeah.
Okay. Okay, sir.
Yeah. Okay. Thank you.
Okay.
Maybe just one sentence to add to you. So what my feeling is that publication is only one criteria among many. Okay, so just to answer you, in addition to the publication, before going for any interview, you should make sure that you can be a very good teacher. So you should be planned for a particular topic in case the interview committee is asking you to demonstrate a subject or demonstrate one topic in organic chemistry or whatever, just to test your teaching aptitude. So, and also if it is a research institute, as Madhu mentioned, a solid research plan for the next 5 or 10 years. So these all will be tested in addition to the publication. So what I feel is that publication is just a criteria to shortlist you, but many other things will follow before the. Yeah, yeah, yeah.
Good evening, sir. Myself, Gunta Rajesh Patro from NIT Trichy. I am final year. I am interested in organic synthesis. I seen some students have good skills, but due to their mails, they are not shortlisted, and professors are not replied them. And some students have less skills, but they are selected for PhD and like good professor. So professor, what the professors are noticed in our mail? Which things, sir?
I can, so you are mainly concerned about the emails, right?
Yes, sir.
Yeah, so say suppose in our department, so I get several emails addressing Dear Professor Mukherjee, and I'm sure Shantanu is getting several emails addressing Dear Professor Biju. Okay, so the reason is when you apply for a position with any professor, you have to ask yourself how serious you are rather than sending out emails to many professors. So you have to see what the research group is doing, the research interest, and draft an email to that particular professor specifically rather than sending 20 emails a day. Okay, so if you really write an email to me indicating my research and your passion for doing something related to that, I'm definitely, I will respond to your email. But if it is just, if I see that I'm very passionate about synthetic organic chemistry and all these things, probably I will not respond to that email because I'm sure that the same email perhaps will go to Shantanu also. Okay, yeah.
Thank you.
Yeah, this is something I was discussing this afternoon with somebody. Yesterday, I got an email. Dear sir, I am interested in your research. I want to do summer project. Thank you. Okay, that's the email. Okay. Now you can imagine. I mean, see, all of you are laughing. You realize that this is not a good email, right? So one thing what Biju told, that is one thing. Then there is another type of email I get addressing to me, addressing to my research. I did the email once, I did the email twice. I do not understand what this person want, what sort of position they are looking for. Is it a summer project, project assistant, PhD, or anything else? There it is not clear in the email at all. It is not written anywhere what I want. Okay, so you have to be, when you are writing an email, first of all, your subject should be important, very small and crisp. You cannot have a very long subject so that half of it is visible, other half is not visible. Interested in a PhD position, interested in summer project, looking for a postdoc position, something like that. When you're writing an email, first sentence should be, Dear Professor X or Dear Professor Y, I am writing to find out a possible PhD position in your lab. That's the first sentence, so that I know, oh yes, well, this person is looking for a PhD position or a summer project position or a postdoc position. It should be clear in the first email. Okay. Then when I read that, after that, I have to see whether a position is available in the lab or not. If I do not have it available, then it doesn't matter. I have to write it back telling that, look, I do not have a position available at the moment. But if I have to go to scroll down to 3 page to find out what this person is looking for, I may not have time at that time when I'm reading the email. Okay. So an email should be very short. First line you write what you are looking for. Second thing, you in 2-3 lines you describe where are you, what you are doing. Okay. And of course you attach your CV, which should be properly formatted. Every information should be there. If you are doing an MSc, which semester you are in, what's your CGPA, if you have done any project already, with whom, in a bullet point, not in a text format. Okay. And second paragraph, so you said who you are. Third paragraph, again you write in 2 to 3 lines that why you want to join that particular professor's lab, that you are interested in that particular work or that field of research. Within that, you really like that recently published work or the paper published last year, and you want to contribute. Okay. And then if you have any idea that, okay, this group, they have published something, and on that topic, I have some idea. And you write that I feel this is something that can be done. I am interested in doing that. So, but email should not be more than 2 to 3 paragraphs and very crisp. Do not need to write history or literature there. But importantly, first line, address properly. Do not CC it to other professors. Okay, that's not uncommon. It's very common. Okay? And BCC, of course, is not uncommon. Sometimes I do not see to whom the email is sent because all the names are in BCC. Okay, so these are some of the points you need to remember. And what you other thing you said that somebody who is more skilled did not get a position, somebody who is skilled. I mean, I don't know how you are determining who is more skilled, who is less skilled. I think that is something that's probably, it's a relative thing, of course. And yeah, that's probably difficult. And then depending on the interest, maybe the person, if you are sending email to, let's say, you send 5 email to 5 different professors, very clearly, like what I just mentioned that way, unfortunately, none of them have any position available at that time. It just happened to be at a wrong time. They do not have the position available. They do not have funding. Or that year, that department is not having an interview. Your another friend who you think is a lesser skilled, they may be writing to somebody who happened to have a position at that time, and they would be interested in looking at this candidate, interviewing that candidate. Okay, nowadays, based on the email, nobody offers a position. Now, everybody is familiar with online interviews, so that if I am interested in somebody, whatever position there is, if it is a project assistant, I set up an interview online, and everybody has mobile phone, internet. Within a few hours, we can set up an interview, talk to the candidate for half an hour, and see if that person is, I feel there is a compatibility, whether that person is good enough, they have that urge to do research and so on. So that's what I felt an email should be like. Is it clear?
Yeah, and another thing, do not do copy paste. Okay, it's easy to find. Also, what the best way, I think, you just draft one email in Word file. Okay, and check the consistency. Okay, that's mean font. Actually, this will give you give an impression. Okay, how serious you are. Because sometimes no email that one paragraph is here, then lot of space, something is there, something is there. And also there are a lot of copy paste, and I can see I got a lot of emails So just copy all of my research area from website and then in that email. Okay. So yeah, so best is that you wrote a draft email in a Word file, then a single font, space, everything should be very consistent, and then you can copy paste that to the email. Okay, so this way I think, yeah, it will be good to throw the email after that, and then rest, yeah.
So whatever needs to be told, it's already told, but I just want to add one more point that nowadays all of you are very comfortable in text messaging. So when you're text messaging your friends, there are some short forms like they use DA or something like that. There are some short forms. So never ever use these short forms in a formal email. So yes, SMS language. So please take care of that. Your email is the first thing that we see, and the moment we see your email, we are judging you based from everything that you have written. So you have to create an impression about yourself through your email. So ensure that there is no spelling mistakes. To help you with that, now there is Grammarly software which you can freely download. You can install in your browser. It will check your grammar and everything. So I suggest that you please do that and take care of your email. Whatever mail that you write, ensure that it's absolutely free from these mistakes. Okay. So I think that's it from my side. Anything, Madhu, you want to add?
If you have no more questions, we would like to end this panel discussion session.
Just 1 minute, please. Why your maximum academic research are for publications, not for the product oriented? Actually, we find out some problems and we solve that and we publish it. But why not it is always in India is that it is product based? Maximum research we are doing for the academic purpose, but it is not exactly for the product based. And you do the some thesis work and it will be closed. That's all. And you will do patent applications and not exactly the giving the product. You'll get the patent numbers and that it will be. Why our academic research is not a product based research? Why it is only in the for the publication sake?
So, well, we are all in academia. We do basic science research. Okay, that's the number one thing. Other thing is that it depends. So not everybody's research has to be product oriented. Let me give you a simple analogy. Okay, one person makes bricks, other makes building. You can't ask the person who is making bricks that why can't you start making building? That's not that person's expertise. If they start doing that, let's say you want to make a house and you know somebody who make bricks, would you give that person the contract to build your house? You won't do that, right? Because he has never done that. Similarly, I mean, if we have an expertise, somebody has an expertise to develop something, be it a reaction, be it a method, be it a device, anything. So that person will do that, okay? But they do not have the expertise to take it to the level of launching a product on marketing that. So yeah, I think not everybody can do everything. And then at the end, I mean, well, let me put it this way. Let's say you are joining somebody's lab for your PhD and you are asked to do things which are already done so that some product can be launched. But that does not ensure that you will get your PhD degree. Okay. Would you be continuing PhD there? Because you won't get a degree. You may get some money when the product is launched. Okay, so we get a lot of students. I mean, most students, they want to do a PhD. They want to learn new things. They want to eventually go on doing maybe postdocs and academia or industry, whatever. So they are going through that training process, right? So major part of our job is to train people like that. So I think, yeah, I don't know if somebody has to add something.
So just to add what Shantanu told, so if you are really interested in doing PhD on applied research, I would suggest the CSIR labs. That is one of the best options. But most of us sitting here, we are doing just basic research. And just to add, say you have seen the classic synthesis of Prabal today, the paracetamol, right? So that was just done in a lab. And with that technique, one can easily extend it to say several gram scale or even kilogram scale with the help of a chemical engineer in a pilot plant scale. So if you are interested in related research on applied chemistry, so you have to choose the research group accordingly. So say for example, if you want to do research with me or anyone sitting here, we are just doing basic research. So once we prepare a molecule or develop a method, there ends our knowledge. So beyond that, as of now, we are not doing. Yeah.
Good evening, sir. I am Smruti Rekha Padhi. I am an integrated PhD student at IIT Tirupati, and my PhD will start from next year. So my question is, what are the skills I need to have before starting my PhD?
First of all, we don't know what is your research area going to be. Okay, so that like if you decide about your research area, you can sit down, please. If you decide about your research area, accordingly, you need to know, you need to read maybe some publication. What are the techniques they have used? So you have to be familiarized yourself with those techniques. Okay, it can be any instrument or I don't know what else required for your research. So that is not a general, but I would say depend on which research area you are going to choose. Okay, of course in general you have to, let's say you are working in organic synthesis. Okay, there are some basic things like you learn already how to use the ChemDAW, the soft skill, sci-fi searching, you are reading enough literature, you are on track. Okay, and then you need to be expert with few basic characterization technique as well, like NMR you have to be really expert. Okay, mass spectrometry, IR. Okay, all these things you need to really learn. Okay, CD also probably. So some other skill like chromatographic skill, okay, maybe sometime HPLC. So this you cannot get in before PhD. Okay, you will learn slowly, but at least spectroscopic technique you need to know some basic, the theory behind them. Okay, that really help you.
So for doing a PhD, I think a few things are very important. I feel I always tell my students. One thing is that you have to be, you have to persevere. So it is not like your MSc practical where everything is set. You just have to follow the procedure to get the product. So here you are exploring something unknown. So you are expected to expect that always that the results won't be positive. So you have to develop a frame of mind that you have to keep trying many things. You have to keep trying. So trying should not be blind. So that's where actually you have to develop literature knowledge. So from the day you join your lab, you know this is the area your lab is working on. So you have to start building your literature knowledge in that area. Of course, your guide will help you to choose a specific topic. So reading literature and relating with what has been done, what is currently going, and what can be done, you have to build an image of all of this. So this is a process. It takes a little time. So with time, slowly, you will start to understand things better, and there will be a time that you will have a clear picture, and you will try more trials based on the literature and discussion. So another thing I would suggest is that discussion. You discuss your problems with your colleagues, your guide. So discussion, I always encourage my students to discuss among themselves. If I get an idea, I just come to board, I just call up everyone, and then we discuss. We discuss every day, because this is a practice that builds up with time. Actually, what I would say is there is one technique in Japan called Kaizen technique. If you find something very difficult, you do a very incremental act, which is very easy to do, but you have to do it every day. So when you do that over a period of time, you will be able to do impossible things. So the secret is you have to do a tiny bit towards your goal on a daily basis consistently. Then over a period of time, you will see the change is enormous. So that is something consistently you have to put a little act on developing your skills. And of course, hard work you have to definitely do. You have to give sufficient time in your lab and do more trials. Number of trials should be more. And with all these things, I think you can do a successful PhD. So this is what I felt, and it's helping. This is the things I tell to my students. It's really helping my students. So I would pass on the mic to Biju and other people.
What I suggest my student that it is easy to become a machine. Okay, so for example, the chromatography technique, any fundamental textbook, whatever spectroscopy, you all learn during your masters, or you will learn more. But what is not familiar to you is the machine, how to handle, how to do the column chromatography. It may not be familiar. Okay, a machine, what you can do if you are like a machine, so you will do always, you will play with these things, no? Whether chromatography, reaction setup, but when you enter into the laboratory, you will see that it is very easy. Yeah, maybe it will take time, but you will learn things. But what is the major thing you require is the fundamental things, that how you understand the subject, how you realize what you want to do here. Okay, so if you are strong in pen and paper, okay, I think you will learn all the techniques soon. And another thing also, it is very much required is the observation. Okay, so observation means observation by doing your reactions, and also observation by watching the other people, that how they are doing, how they are learning from their mistake or their technique. You can develop your own technique. Okay.
Thank you.
With all due respect, as we are running late, we would like to end this panel discussion session. Thank you, sirs, for your kind words and insightful suggestions. Please put your hands together for Professor Shantanu Mukherjee, Professor Biju, Professor Chatterjee, Professor P.C. Ravi Kumar, and Professor Madhusudan Maji. Thank you, sir. Guys, please be seated. Guys, please be seated. With some extremely profound and insightful lectures by our honorable guest, we now come to the end of this mega event of learning, memories, and an extremely fruitful interaction. We, on behalf of the organizing committee, would once again like to extend our heartiest gratitude to you for all your enthusiastic and keen participation in making this workshop a grand success. I would now like to invite Dr. Snehashish Chaudhary, Associate Head of Department of Chemistry, School of Basic Sciences, IIT Bhubaneswar, to say a few words as a concluding remark for day 2 of the workshop.
Hi, good evening. So yesterday, when I was there in the dais, I was listening to others, and one person told, "Sir, last 2 years, I am in 5th year, and maybe last 2 years I didn't get anybody to interact because of COVID." Then I realized at least I should stay in, should not speak in the dais at the beginning day, because at the end, then nobody will be there. So why I should not be there on the last day to talk to and say thanks to my all colleagues, friends, and of course the invited speakers, delegates, everybody. But I thought maybe nobody will be there that time. But I should stay with my convener
as a discipline head till the end, although I am a physical chemist, not an organic synthetic chemist. But what I understood, all organic chemists till the end only believe in one thing, that is the percentage of yield. Okay. Even last part, the panel discussion, everybody wants to get how much percentage of yield we can get as a student collectively. So I hope this is a very successful event. Dr. Khan planned at the end, and all of your participation. I was thinking that it maybe take some time. What I will do here, there is so since I committed, I will be there at the end, and I should tell my fellow friends, Dr. Khan, please come, and officially Dr. Khan can only conclude. It is not me. But thank you all being here. And Dr. Khan, just well, they all are tired now, so we should not take too much time. Okay.
A very good evening to all. You know, it's a mixture of emotions as we, come to the conclusion of this workshop. Let me tell you, I really idolize the people sitting in front of me. There is no class on asymmetric synthesis which goes without taking the name of Professor Santanu Mukherjee. There is no class on NHC mediated catalysis which goes without taking the name of Professor Biju. I really admire all these heroes and ask our students to really follow their work. So my duty is now to present the vote of thanks. So as a professional, we have to balance both emotionally as well as professionally. So keeping the emotions aside, I would like to now present the, finally vote those people who were instrumental in making this workshop successful. So, but before thanking them, I would like to express my appreciation to all the speakers for their valuable contribution to this workshop through their fantastic lectures over the last 1.5 days. My deepest gratitude goes to all the participants who attended this workshop and helped us to make this event a successful one. I'm extremely thankful for all the kind wishes and positive comments received from the participants and delegates. This makes me very pleased of our volunteer team and all my colleagues who contribute to make this workshop a good. Especially to appreciate and acknowledge the efforts of all our volunteers, I wish to call each one of them on the dais one by one. They definitely deserve an applause. So please join me in thanking them. So first, from the transportation team, I would like to thank Mukesh Kumar Nayak, Mr. Suvam Panda, Mr. Rahimuddin Khan, Mr. Lalit Mohan, and Soumya Ranjan Mishra for fantastically, doing the coordination and for the fantastic management. So transportation team, I think they are busy. Okay, no problem. From the guest house reception team, I would like to thank Abhishek Vishwakarma, Abhay Vishwakarma, Subrata Sahu, Samina Asmin, and Pulkit Kumar Gupta. Thank you for your coordination and for making the stay of all our guests comfortable. From the boys hostel reception and room allotment team, I would like to thank Chinmay Parida, Samir Kumar Mandal, Dipun Kumar Penti, Bhabani Malakar, Pavan Kumar Kola, Mantri Achyuta Rao, and Madhav Chandra Maiti. From the girls hostel team and room allotment, I would like to thank Tilotima Baisaki, Haripriya Patra, Subhashri Barik, Bhavika Gupta, Ipsita Roy, and Saswati Somya Mahapatra. Thank you all for your amazing coordination and for making the stay of all the participants comfortable. From the registration desk team, I would like to thank Abdul Salam, Sakshi Singh, Hari Babu, Archana Patnaik, Riya Ghosh, and Amrita Ray. For the flower bouquet courtesy, I would like to thank Nupur Deshmukh, Subhashri Kar, Paramita Jana, Manaswini Ghosh, Sonali Ghosh, and Anvesha Monty. For the banners and standees, I believe, in my opinion, he is the hero of this conference, Mr. Tonish Kumar Sahu. I would request you to please come forward for designing all our, beautiful banners throughout the campus. I also appreciate the support of Mr. Rahimuddin Khan in various forms. He was the biggest all-rounder of this workshop. So thank you both Tonish and Rahim for supporting me for the past 1 month. I'm also extremely thankful to Rajat Rajiv Maharana for all the technical support. From the dais and podium, flower decoration and audiovisual management team, besides the CITSC, I would like to thank once again, Tonish Kumar Sahu, Rajat Rajiv Maharana, Pulkit Kumar Gupta, Manaswini Ghosh, Arishika Das, and Sanjini Patra. For the food arrangement and coordination with the caterers at the CC grounds, I would like to thank again Rahimuddin Khan, Manaswini Ghosh, Riya Ghosh, Abhishek Vishwakarma, Subrata Sahu, Tonish Kumar Sahu, and Abhay Vishwakarma. Last but not the least, a heartfelt thanks to all my dear faculty colleagues for extending their support in every possible way and being the pillars of the organizing committee. Thank you all. Thank you very much.